Good morning. Well, it's nice to have you here.
Morning.
I haven't gone to China since the pandemic started.
Yeah.
I only knew a few words, but now I forgot already.
Maybe after the pandemic, you have to come to China more often.
Yeah, so
Usually, when you come to China, where do you go?
many places. Beijing,
Many
Nanjing,
places.
Qingdao,
Mhm.
Hangzhou, many places. Very beautiful. We have the original chairman now, so the copy will move away. When Ali was very comes, then I will.
Okay, good morning to everybody. I'm Francesco Tafuri from the University of Napoli, and I have the pleasure to chair this session with Ali. And so the first talk will be online by Professor Xinxian Zhu from Chinese Academy of Science, and the talk is Laser ARPA Study on Electron Phonon Couplings in High-Temperature Coupled Superconductors. Thanks so much.
Okay, I should start. Okay, thank you, Chairman, and thank you. Let me thank the organizers for organizing the conference and also for the invitation. Today, I'm going to talk about our work on the ARPA study on couplings in high-temperature cool-phase superconductors. I'm Pingyang Zhou from National Laboratory for Superconductivity in Institute of Physics, Chinese Academy of Sciences in Beijing. So let me first thank my group members. I think all the work I'm going to talk about today are really done by them. Also, I want to thank my colleagues and collaborators. And in the last more than 10 years, we have been developing these ARPAs in our group. We have very nice collaborations with Professor Huang Chen's group and also Professor Zhu Yanqu's group. Also, for the single crystals, bismuth 212, we got it from Dr. Jianda Gu from Brookhaven National Laboratory, bismuth 223 from Dr. Chen Tianlin from MPI in Stuttgart. Also for CCOC, single crystals, we got it from Professor Changqing Jin in our home institutes. And for theoretical collaborations and discussions, we have many discussions with Professor Tao Xiang, Professor Kai Choi, also Professor Chen Wama. And here's my outline. And after a brief introduction, I'm going to talk about two things. One is about the how to dope a modern insulator. The second one will be the main topic of today. It's just the study of the coupling in cool-phase superconductors. Eventually, I'll give a summary. And as you know, and ARPAS, angle result photon emission, is a very powerful tool to study high-temperature superconductors and other quantum materials. And usually, people use zinc combination as a light source to do ARPAS. But in my lab, we are using VUV laser, just a vacuum ultraviolet laser as a light source. So usually the photon energy is about 7 eV. By using laser ARPAS, I think it has many advantages. Most importantly, just the N resolution can be much improved from the usual 5 to 10 millivolt in synchrotron ARPAS to better than 1 millivolt in our laser ARPAS. Also, the photon flux is very high. Usually, it's about 2 orders of magnitude higher than synchrotron. That means you have a high data quality and also high efficiency, and also some other advantages. I think the laser ARPAS is really powerful technique to study high-temperature superconductors. And in the last about 16 years, our group has been developing laser ARPAS and for many years. And at the beginning, we developed the laser ARPAS. Then we upgrade the laser ARPAS by using some tunable laser. The laser can tune the photon energy between 5.9 to 7.1 eV. And second one is the spin result ARPAS. That by using spin result ARPAS, using VUV laser, we can greatly improve the energy resolution. So actually we can achieve 2.5 millivolt resolution. That's really one of the best in the world in the spin without RPS. Also, we have developed one system called time-applied RPS system. And in this case, we can really measure two-dimensional momentum at one time. So actually you can see from the surface on site. So this is just the measurement of the momentum from 1D to 2D. The fourth one is the one we just developed. This is ultra low temperature RPS. And in this system, and we can cool down our sample to 0.8 Kelvin. That's, I think so far, this is only one RPS system in the world which can cool down the sample temperature to lower than 1 millivolt. Also, we also further improve the energy resolution from 1 millivolt to 0.1 millivolt. And by using this RPS, we can really see something we cannot see before, and we can do something we cannot do before. That's like previously, people already observed this binary splitting in bismuth 212 because it has two copper layers. So that means it has two Fermi surface, bonding Fermi surface and antibonding Fermi surface. But for a long time, people don't know whether this signaling gap on the two surfaces is the same or not. So I think by using our laser RPS, we can really measure very precisely the signaling gap of the two Fermi surface sheets. And we can see the bonding and the bonding Fermi surface, they have very different, signaling gap. And actually the difference is small, it's only about 2 millivolt, but you can see the difference. And by using laser RPS, we can really see the just different gap structure on the sheets in bismuth 212. And also by using this RPS, actually, we are able to just extract the so-called pairing Elias function. The pairing Elias function is really just a fingerprint for the pairing group. I think it is very important to extract the pairing Elias function. But this usually in conventional semiconductors like a lead, it was done by using tunneling spectroscopy. But in high-TC Cool-free semiconductors, because it has a anisotropic gap and an anisotropic structure, and I think we have to use RPS to extract the function. And I think this first time we can extract the pairing the function in the cool-free semiconductors, and it has a structure like it has a peak around 50 millivolt, and it has a very flat, just high energy feature here. The third one I would just highlight is just the we just finished. This paper was posted online last week, and here we just using laser RPS to study bismuth 223. Why should we study bismuth 223? Because in high-TC cool-free semiconductors, it has been found that actually TC depends sensitively on the number of copper planes in the cell. And when the number of covalent planes is 3, it reaches maximum TC. Okay, this is the maximum TC. Then it goes down with the further increase of N. Also for the bismuth 223, for the 3-layer cool-free semiconductors, it has a different phase diagram. Usually, the usual phase diagram is that you have, with the increased doping, TC goes up with the maximum and it goes down. There's a usual phase diagram. But in bismuth 223, it's 3-layer cool-frees, the TC goes up, reaches the maximum at the optimal doping, then keeps constant with further increase in the optimal region. And I think by using this RPS, we have for the first time detected the 3 Fermi surface sheets and gathered the signaling gap on the Fermi surface sheets. And in this case, we really have provided the direct evidence on the composite picture proposed a long time ago by Steve Kilson. In this case, because we have 3 layers of corporate ortho planes, the inner one, is heavily anodoped. The doping is about 8%, but it has a larger signaling gap, about 60 millivolt. So it acts like a strong pairing strength source. On the other hand, the outer 2 planes are heavily overdoped, about 30%. Actually, it shouldn't be superconducting. But actually, it can act as a strong phase coherence source. So this combination, composite picture means you have the strong pairing strength layer and also have strong phase coherence layers combined together, you can really reach high TC. So this is, I think, in this work really provided some strong evidence to show that the composite picture is really right, and it also is a good way to enhance TC. So now I come to my one of the two topics in my talk. Just the first one is about the momentum resolved visualization of electronic structure evolution in doping of multi-insulators. As you know, this is a generic electronic phase diagram of high temperature superconductors, and the parent compound is the multi-insulator. Then you can dope the system by hole or electron. Either way, only when the doping level reaches some threshold, you can reach, or you can get high activity. Either way, either electron doped or doped. The long-standing question is, how can the multi-insulator be transformed into superconductor by electron doping or hole doping? I think this is the question we want to address from our RPAS measurements. And also, as we know, without for ultra superconductors, the parent compounds actually half doped, half filled. So without correlation, it would be metal. But because of the strong electron correlation, this band splits into upper band and lower band, and by the on-site Coulomb U. And in Coupled superconductors, because in the middle between the UHB and the LHB, there's another band called just derived from oxygen. So actually, the real gap is between the charge transfer band and upper band. So it's delta. So that's why usually, strictly speaking, high temperature superconductors, the parent compound should be the charge transfer insulator, not the multi-insulator. But loosely speaking, we still call it a multi-insulator. Then the question is how to, if you dope it, how to produce low energy at the long states. Okay, so if you have a parent compound, the chemical potential is located within a gap. If you dope the system by holes, there are two ways. Either like the conventional insulator or semiconductor, just the chemical potential jumps into the conduction band. Okay, or just the chemical potential can be pinned and you form new states other than chemical potential within the gap. This is two pictures here. Also, basically for the electron doping is the same picture, but either you form some new states in the upper band or within the gap to form some income states. So there are some prominent issues related to this doping process. The first, in order to understand these processes, we want to understand how does the chemical potential shift, whether there is a shift or not. Second, how does the model gap collapse, whether it will collapse or not. Third, how does the low energy electron states emerge? So we have the electron states, whether it's this way or this way. Okay. So for this purpose, we just carried out some doping dependence measurements on the parent compound of Coupled superconductors. Here we measured on so-called CCOC, just the calcium, copper, oxygen, chlorine, and it usually has two forms. Either you have one copper plane within one unit cell, the single layer CCOC, or you have two layer corpuscle planes within one cell, you have double layer CCOC. Double CCOC and single CCOC basically they are same. A double layer CCOC is more conducting. It's insulator, but it's more conducting. So easy to measure the system at low temperature. So we can absorb some more, just absorb some more rubidium on top of it to get a doping. So that's why we worked on this double layer CCOC. So I think a long time ago, 20 years ago, Professor Jack Shen's group already did some pioneering work on studying the electron structure of the parent compound CCOC. At that time, they just identified so-called underlying Fermi surface, just not on the Fermi level, but below the Fermi level. There is some so-called underlying Fermi surface. That's 20 years ago. And now, by using some more advanced systems, actually we measure this system, and we found actually this system contains two underlying Fermi surfaces. Just one we call alpha, the other one called beta. This is the, I think we should consist of two underlying Fermi surfaces. And for the double layer CCOC, it's the same. It's the same as the single layer CCOC. Only the states is closer to the Fermi level than the single layer CCOC. So that's why we work on this double layer CCOC. Then usually, how do we dope the experimental compounds? And in our RP system, we just dope the system by depositing some rubidium on top of the surface. And in this case, it can dope the electrons into the CCOC system. So by gradually increase the deposition, we can increase doping. So then this is the measurement of the Fermi surface. So without doping, there's no special weight at the level. When you increase the doping, you start to see something near the pi zeros or pi points. So this special weight just increases with the increased doping. So eventually you can form some Fermi surface near the pi zeros or pi points. And later on, you can form some states along the direction, eventually form the large Fermi surface. So actually you can really see that by depositing some rubidium on top of the surface, you can really dope the system by electrons. Actually, eventually we can reach the electron doping level up to 0.12 electrons per copper. And also we can see that when the electrons are doped into the system, it first forms some electron states near the antinodal pi zero point. So then let's check on the band structure evolution. So here is a band structure we measure along the nodal direction, along diagonal direction. So this is a panel compound. You already have some bands, just the charge transfer band. Top is about the 200 millivolt below the Fermi level. This is the charge transfer band top. If you dope electrons a little bit, just a little bit, you already see that the band will shift down by about 1 millivolt, 1 eV. Okay, then you start to see something formed. This is good chance, because in this case, this is a gap region. RPS usually cannot see the gap on top of the chemical potential because the Fermi function is cut off. But by dope electrons, actually, now we can expose large area of the shielding gap gap here, and we can see something start to emerge in the gapped area. With further increase of the doping, you can see that the in-gap states get stronger and stronger and stronger, but it's still away from Fermi level. It does not reach Fermi level. Eventually, when the doping level reaches about 12%, 0.12, this nodal states reaches Fermi level. This is basically along the nodal direction. We can see how the low energy electron states that evolve, it appears and evolve with the doping. On the other hand, if we look at the electron states near the pi zero nodal region, okay, this is a parent compound. Okay, it already, because in this case, its top further is away from the Fermi level about 500 millivolt. Okay, again, if you just dope a little bit of electrons, okay, this charge transfer band jumps down by about 1 eV. Okay, then actually here you can start to see this area. You start to see something already reached the Fermi level, the Fermi potential. So this actually is the upper band bottom. Then you increase the electron doping further. You can see this electron states near the Fermi level just stronger, eventually form some electron-like bands here. Okay, when you reach about 12%, you can see clearly an electron band here. So this is basically I put them together. You can really see when you dope electrons to the parent compounds, how the electron states evolve with doping along the nodal direction, also along the pi zero nodal direction. So you can really see that the electron states first appear at the Fermi level and near the pi zero points. But when you go along the diagonal direction, although it appears in the capital region, but it doesn't reach the Fermi level. And only when the doping level reaches 12%, it reaches Fermi level. Okay. So basically from this experiment also, now we can also measure the chemical potential shift with the doping. So here just because by using some core level, the kind of calcium 3P or oxygen 2P, but by using core level, we can measure the chemical potential change with doping. So we can really see that at the beginning, when you dope the system by a little bit, only slightly, a little bit of electrons, you already see the chemical potential jump by 1 eV. Then it keeps increasing slowly, gradually, with further increase of electron doping. So this is the jump. Even altogether, it has about 1.3 eV chemical potential change here. So combining the chemical potential jump and the observed electron structures, we can just establish an experimental picture of electron doping a corporate parent compound. So this is the method results. You can put the chemical potential for different doping level. Okay, for the parent compound, chemical potential is here. We dope electrons to the system a little bit, the chemical potential jump to here, and keep increase. So you can really see the charge transfer band. Charge transfer band eventually is at the beginning is very strong and becomes weaker, eventually disappears. And the income states from the beginning 0, gradually increase and eventually becomes very strong. Is the same case for the pi 0 region. So then we get some experimental picture of doping the modern insulator. Okay, I think that if you compare with the theoretical proposals just proposed a long time ago, I think it's quite a difference, because at that time people thought that if you dope the system, usually the income states just limited to some small region. But actually, in the real case, we can see that the spectral rate spreads all over the entire capture region. Okay, so this is different from the usual thinking that just the income states is limited into some narrow region. But actually, it spans over the entire capture region. So this is just the work we have done on doping the modern insulator by electrons. Also, actually, we also did the work to dope the modern insulator by holes, by slaughter holes. But because of time limit, I'm not going to talk about it in detail. But in this case, we use the bismuth 212, starting from about the 6.6% doping. Then we also dope electrons on top of it to reduce the doping to 0. Okay, so we just we start from co-doping about 6.6%. We put electrons on top of it to reduce the doping level to 0, and we can also establish the experimental picture of co-doping parent compound. And you can really see that in this case it's quite different. You cannot see this region just in this region because of the just chemical potential is here. Okay, it's a very different evolution picture compared with the electron doping case. Then I move on to the second topic of my talk today, just the electron-proton coupling in corporate superconductors. And as we know, the high temperature corporate superconductors that exhibit some unusual superconducting properties. First, the TC is very high. Usually, the maximum TC now at the ambient pressure is about 135 Kelvin for mercury 1223, and at a high pressure it can reach 160 Kelvin. The second most important part is that people already know that the superconducting gap is D wave. It's not the usual S wave in other conventional superconductors. But even in spite of this unusual properties, people already know that electrons still paired. The question is, what is the pairing glue? Do we need a pairing glue? What is the pairing interaction? There are two main groups of ideas. The first idea is that there's no glue. No glue is needed to pair the electrons. Okay. The second group of ideas is that there are glues. It can be phonons, magnetic mode, spin fluctuations, spark fluctuations, or some quantum critical fluctuations, and many others. So there are glues, but what are glue? What is really the glue to cause the pairing in high temperature superconductors? And usually for me, you cannot produce D wave superconductivity, and also from the isotope effect, near the optimum doping, the isotope effect is nearly zero. It's the weakest. But I think it's still too early to fully inject the electron coupling in corporate superconductors. And we still want to know, is there electron coupling in corporate superconductors? How strong is the electron coupling? And then what role does the electron coupling play in high-intensity superconductivity? So this is, I think, RPAS is a very powerful tool to really probe directly the electron coupling or electron mode coupling in quantum materials. Because in this case, usually, if there is an electron coupling or electron mode coupling, usually it shows up as a kink, just as the slope change, so-called kink in the dispersion. So it has been found that in many cold-doped superconductors and also electron-doped superconductors, there's the nodal kink. On a nodal region, there's 70 millivolt kink present in different materials, like bismuth 212, 201, LESCO, or many others, and in various dopings, and also above TC and below TC. But still, it's controversial whether this mode is due to phonons or some other modes, some magnetic mode. It's still under debate. But the people already see that there's a 70 millivolt nodal kink in corporate superconductors. Also, there's another kink called the antinodal kink, just near antinodal region. But this kink is observed only in bismuth 212 in different state. So 40 millivolt kink. So only in this material, only in different states near the pi zero antinodal region, there's a kink called a 40 millivolt antinodal kink. But it also is still under debate whether this kink is due to phonon or due to magnetic mode. So it's still under debate. Also, in the high TC superconductors, there is a famous so-called peak dip hump structure in the different states. You have peak, you have dip and hump structure. This is considered as a hallmark of superconductivity in bismuth 212. So it has been used as a fingerprint of superconductivity. Okay. So then, if we give a summarize of all the previous electron coupling RPAS studies, we can find out that different materials in nodal and nodal region, below TC, above TC, there are 70 millivolt, 40 millivolt modes. And just the previous results are sporadic. And also the origin is controversial. And how the nodal 70 millivolt kink evolve into 40 millivolt kink and then the kink isn't clear. And in our study, actually, I'll just give a conclusion here. Actually, in our case, we see this 40 millivolt kink, 70 millivolt kink are coexisting in different materials, in different dopings, at different temperatures, actually in all materials. Actually, it's really ubiquitous. Okay, it's really ubiquitous. So basically, this is a conclusion of this topic, and I later on just to give you some the data to illustrate this conclusion. And previously, people used the kink in dispersion to identify this electron mode coupling. Okay, but this method has some shortcomings. Mainly, it depends on the data quality, on the statistics. When the data statistics is not good, or when the mode coupling becomes weaker, it's hard to make a conclusion. Also, when there are more than one mode coupling here, it's also very hard to really identify. So then, actually, there's the electron mode coupling has some more just really characteristic of mode coupling. If you have here, I just give you simulation results. Here you can see a kink. Actually, you can also see some other weak feature here. If you do second derivative, you can really see the band goes this way. Is the band this way, also this way, and this way? Because actually there are two flat bands associated with one mode coupling. Okay, and if you have two mode coupling, you put two modes in, you will see two flat bands on either side of the main band. So this is a more robust feature to identify the mode coupling than the usual kink from dispersion. So I think this is a more decisive and more robust method to do. So that's why when we come to the real data, like this data will take along the direction. If we do second derivative, you can really see this two flat band here. Okay, so this is very consistent with the simulation. That means there are two mode couplings here. So by this way, we first measure along the direction, the real original data here. We do a second derivative and see the two flat band here. Okay, so this is a bismuth 212 overdoped TC73 millikelvin data. If you go to bismuth 201, just overdoped, heavily overdoped, not superconducting. You made the real data, original data, you do a second derivative, you can already also see two flat bands. That means two mode coupling here. And you can also do a simulation. You put a two mode coupling, one at 40 millivolt, one at 70 millivolt. You do a simulation. You can see the simulation is very close, similar to the observed band here. So this means along the direction, these two mode couplings, 70 millivolt, 40 millivolt mode couplings are coexisting. It has both mode couplings along the direction here. Okay. Then if we move on to the another region, okay. In this case, just the band here, the band bottom actually is smaller than the photon energy. Here, band bottom is actually photon energy is larger than the band bottom. Usually, the usual methods of kink can work because it doesn't cross the band. But use our methods, second derivative, you can still see two flat band here. Okay, that means two bond coupling here. You can use bismuth 201, heavily overdoped, non-superconducting. You can also see two flat band here. And you can also do simulation. If we have two mode coupling here, even though the photon energy is larger than the band bottom energy, you can still see two flat bands. That means in both bismuth 212 and bismuth 201, near the another region, we can also see that two coexisting 70 millivolt, 40 millivolt mode coupling here. So this is a totally new. Previously, it's never observed before, but now we can really see that these two mode couplings are coexisting. They are always together. Then if we do the momentum dependence, we just go from the nodal direction and gradually to the another direction. You can see that these two modes coupling, 40 millivolt, 70 millivolt, they are always present along all the momentum cuts from nodal direction to another direction in both 221, and 201. Okay, and also you can see that the mode energy does not change much with the momentum change. So basically, they are constants when we move from the nodal direction to another direction. It's a very small change here. Also, we also measure the many other bismuth 201 with different doping from heavily underdoped to heavily overdoped, non-superconducting. A lot of samples with different doping levels. You can really see that the two modes, 40 millivolt, 70 millivolt, are all there. Doesn't change much with the doping. Also, bismuth 212, the same thing, from underdoped to overdoped. We can also even see that these two modes also exist in bismuth 223 samples. So they are really different materials. So I think from the previous observations, it becomes clear that this 40 millivolt and the 70 millivolt mode couplings are really due to electron-photon coupling. Because even in heavily overdoped samples, we can still see these two modes. And in high TC, Cooper semiconductors, usually these modes are associated with the oxygen phonon modes. We have the so-called the buckling mode, B1G buckling mode. It's about energy about 40 millivolt. We have this A1G mode. We have this breathing mode, half breathing mode and full breathing mode. This is about 7 millivolt. I think there's two phonons. One is about the B1G buckling mode. The other one is about breathing mode. So that's two phonon modes we have observed. Then we come to the temperature dependence. We also did this temperature dependence in bismuth 212 and bismuth 221 along different moment cuts. What do we see that we just warm up from low temperature to high temperature above TC and or even above T star, the so-called pseudo temperature. And we can still see that these two modes actually above TC still exist. So the coexisting 70 millivolt, 40 millivolt modes are present not only in sequence states, but also in normal states, and even above the pseudo states. Okay, so this, but also it's very interesting to note that this energy scale does not change with temperature. Okay, just energy scale you also should not change when you cross TC or cross T star. It does not change, the energy doesn't change. This is very unusual because in the conventional picture, when the sample in normal states, if you have an electron phonon coupling, the phonon has the energy of sigma, and in the sequence states, this mode, the scale should change, move up to the sigma plus delta. So the S-wave semiconductor, it is the case that the mode energy should change from the initial phonon energy sigma to sigma plus delta plus the sigma gap. And even in the dual semiconductor, the similar analysis also indicated that the kink energy should move from the initial sigma to the sigma plus delta and 0. But why we don't see this? So this, but in our case, we can measure both bismuth 212, 221, and we don't see any energy shifts across DC. So this is quite unusual. And in the literatures, there are some discussions, but so far we don't have any theory to explain why the motor energy doesn't change with temperature across NTC. So eventually, I'll come down to the famous Piketty pump structure. Actually, a long time ago, for a long time, people think that in bismuth 212, near the anode region in sequence states, people will see the peak dip hump structure. Usually one peak, one dip, one hump. But actually, by our laser RPS measurements, if you have a very careful inspection, actually it's not one peak, one dip, or one hump. It's one peak, one dip, two hump, two dip, one dip, one hump, one dip, one hump, one dip, two hump, two peaks, two dip structure. So actually, because now we know, just we have coexisting mode coupling, 70 millivolt, 40 millivolt. So actually, you have produced two dip and two hump structure. So actually, EDC is not just composed of the one dip, one dip peak dip structure. It's a peak double dip double hump structure. So this can be seen in bismuth 212, in bismuth 201. Also, it can be seen both in the sequence states and in normal states, even another direction. So previously, people thought it can only be observed in bismuth 212 near another region in the sequence states. Actually, it's present everywhere. It's present in normal states. It's present in another direction. So this is basically the characteristic of the electron phonon coupling. Electron coupling with two modes. It will produce peak double dip double hump structure. I think we have some new understanding on this feature. So I think we should reconsider this the electron phonon coupling in high temperature semiconductors, and people usually neglect this effects by saying that okay, phonon mediated pairing cannot produce S-wave, D-wave superconductivity. Actually, if you look at the literature, already many people are discussing actually phonon-mediated pairing can also produce D-wave superconductivity. There's a paper in 1996, also a recent paper just 2020. Already people are still working on theories of electron coupling on high temperature superconductivity. Since my time is up, I just give my summary. And today, I've mainly introduced two topics. The first one is about if you dope the modern insulator by electrons, how the electron structure will evolve. I think this one will provide key information in testing the existing theory, also in establishing some related theories in the future. The second topic is that actually we have really observed ubiquitous mode coupling, electron phonon coupling in covalent semiconductors. Mainly just 70 millivolt, 40 millivolt mode couplings, just coexisting, are present in different materials and different dopings, different temperatures, and it's really truly ubiquitous everywhere. But it shows very unusual time dependence. And also we have discovered that actually it should consist of peak double dip TOPCon structure. I hope this work can stimulate further work on studying the role of electron coupling in high temperature semiconductors. Since my time is up, I just conclude here, and thank you for your attention.
Thanks so much for this beautiful presentation. Time for questions, please, Antonio.
Where I can see the speaker.
Hello?
Zoom. Hello? Zoom.
Yeah. Yes.
Okay. So thank you for this beautiful talk. We are here in Bodrum and in the 2022, and your results are really fundamental because they show that you have the paradigm of single band superconductivity is completely wrong. So the strongly correlated paradigm with the strong correlation a single band is completely wrong. It's completely in opposition to your experimental results. It's like when Galileo disproved the classical structure of the universe. All your results concern multi-gap superconductivity. All your results, you have very multiple bands. And you cannot explain these results with the standard paradigm of strongly correlated single band model. This is completely wrong model. So that's why you cannot your bismuth is two-band superconductor. You make a surface superconductivity on top of a good insulator that is interface superconductivity. You make the system of three layers bismuth. These are multi-gap superconductor with Majorana exchange interaction. So it's beautiful, very beautiful work, but you have to change completely the paradigm of your interpretation. Thank you, Zhu. Beautiful.
Okay. Thank you. Yeah, I think I hear you. Yeah, I think those observations, I think should be explained just in different way, particularly for doping the modern insulator. Yeah, whether we can still use in the existing some just a cartoon picture, I think that's a doubt. I agree. Yeah, I agree. Yeah. Also, I want to point out that the low energy electron states, the incap states, when they are produced, they are very, very incoherent. So usually when we talk about band, it should be coherent, but actually those electron states are very incoherent. So whether you can use the usual band picture, I think that needs to be discussed. Yeah, I agree.
We have another questions, please.
Yes, I would like to ask the mode you are talking about. Could it be a local polaronic mode, like a small polaron?
Let's see. Because usually in RPES, if we can see some mode coupling like this, usually this mode should be very sharp. Should be sharp mode. Just that means it should be sharp mode. And polaron usually I think is quite, if I understand correctly, it should be quite broad. Whether we can do some simulation. If it's very broad, I think maybe they may not produce such a sharp feature here. Because usually if you see something like this, usually it's the electron coupling with some sharp mode, very sharp mode. If in my understanding, polaron may be a little broader than the regular phonon modes. Also, I think it has some quite good correspondence to the phonon modes neutron scattering observed in RTC couplets.
Okay, thank you. We have another question from Ali. Yes, please.
Thank you, Professor Zhao. Very high-level talk, and I missed some of it because I was also busy playing with my iPhone and making communication with the YouTube links to all the people interested. I'm just wondering, because we have also young talents here and as PhD students, and they would like to advance in quantum materials characterization. Can you say in simple words, I mean, what would be the benefits of RPAS for materials, for quantum materials characterization, let's say? Can you just come
Yeah,
with
yeah.
a couple of, or a few sentences, please?
And say, sorry, I didn't hear your last sentence. What's your question? What's your question?
Okay, what is the importance of RPAS characterization for quantum materials, let's say?
I think quantum materials, basically, most of the properties are determined by the electron states. I think RPAS is the most direct and powerful tool to measure the electron states so far. So I think if you really want to understand some physics or unusual phenomena in quantum materials, RPAS is a very important tool to do that. Just the it may say it is indispensable. Yeah, it provides some fundamental, very basic just information to understand the phenomena and the physics in quantum materials.
Yes, I think the clear message to our young PhD students: study RPAS. Okay.
Yeah, yeah.
I think that the RPAS that Zhu presented is very important for quantum mechanics because it's very low energy, very high energy resolution. And the new quantum mechanics always in the range of 10 to 50, 100 milleV. And this is a new physics, it's not solid state physics. So that's why you have beautiful importance of this high resolution result, RPAS.
Yeah. You're right. Because physical properties are determined by only a few millivolt or just tens of millivolt in Fermi level. Because that's why it's very low energy. So that's why we are pursuing to some high energy resolution, higher and higher. But that's very important to because we are really probing some very low energy electron states near the Fermi level.
Okay, thank you. We have time for a very last quick question. Herman, please.
Yes, Professor, so you left a question open regarding further studies of the electron-phonon coupling. And I was wondering if there has been any specific study, for example, with a femtosecond laser below 300 femtoseconds, to have just purely electronic excitation without electron-phonon time regime interaction, or above 10 picoseconds, for example, since that would be well above the effective electron-phonon interaction.
Okay. So I think if we do some time, if you can that's a good idea. If you can separate the electron-phonon coupling from the electron interaction, I think people are trying to get a way just to really separate these interactions, electron mode coupling and electron-impurity interaction. I think if time resolves, just the experiment can do this. That's of course, it's very good. Yes.
Okay, thanks so much to the speaker for the nice presentation and for these questions.
Okay, thank you. Yeah.
And we are ready for the second talk of this session, which will be given by Professor Jacopo Santamaria, and in presence, the title is Interplay Between Ferromagnetism and Superconductivity, Long-Range Ozone Effect Across a Ferromagnetic Quick Link.
So good morning, everyone. Thank you for being around. I want to thank the organizers, especially Professor Ali Genser for putting this meeting together, reminding organizers also for inviting me. I'm so happy to be here after 2 years of practical lockdown and no travel. And So also the chairman, the distinguished chairman for introducing me, Francesco Tafuri and Germán de la Fuente. So my talk is about the interplay between ferromagnetism and superconductivity. And I aim at showing a long-range Josephson effect across a ferromagnet, right? So this has been in part done in my group at the University Complutense in Madrid. I like very much, this is a time-integrated picture. My group is smaller, but I mean, there was a bunch of people getting together for a PhD defense. And I like this picture because there are the 4 PhD generation who took part in this project over the years. So it's Cristina Visani, Mirko Rocci, Fabian Cuellar, and finally this guy who succeeded in getting these junctions working. So, so this has been a big collaboration. So a part of the people in my group or in my environment in Madrid, in Spain, there has been the group of Javier Villegas in Unité Mixte de Physique en Erestales in Paris, which, I mean, we have been collaborated for many years already. The group of Jérôme Blessua in ESPCI, also in Paris. Alexander Buslin, who helped us with the theoretical understanding of this interplay with ferromagnetism, and Sergio Valencia at the synchrotron. Okay, so I'm talking about transition metal oxides, and you probably have seen already many times these color palettes outlining their technological opportunities. So these materials can host almost every possible electronic ground state in the solid matter. So they exhibit very rich cross-correlated responses and produce very interesting functionalities. That's the reason for these many color palettes, right? Which, in a sense, remind the Kabbalistic symbols of the old alchemists when they tried to convert iron into gold. And this is, in a sense, what we aim today. I would like to get a ferromagnet to superconduct. So the idea is that combining these materials at interfaces produces very rich physics. And the reason is many of these materials share a common perovskite structure. It's possible to ground them one on top of the other with high degree of perfection. So it is possible to bring very different ground states in an intimate contact at these interfaces. So an example is these ferromagnets and superconductors that I aim at combining today. And, excuse me, and this is an example of the structural perfection of these interfaces, right? So, as I said, in this talk, I aim at showing a long-range proximity effect between a ferromagnet and a superconductor. And when I say long range, I mean really long range. I mean, it is one micron long proximity effects, right? So let me take you to a walk across old physics, and hopefully I'll bring also new insights into new problems, new concepts. So the interplay between ferromagnetism and superconductivity is an old problem. It was already examined by Ginzburg, where when he found that there was a detrimental effect of the, as he called the orbital effect, the kinetic energy term under an exchange field for the superconducting state. And shortly afterwards, Harry Suhl and Björn Mathias and Korenwitz showed that there was an exchange field of an exchange effect of the magnetic field on the Cooper pairs, which introduced an energy penalty, right? But for triplets, the situation would be completely different. Triplets could, in principle, peacefully coexist with an exchange field without further problems, right? And triplets exist very, very rarely in nature, but they are quite natural in the framework of the proximity effect. As you know, in the proximity effect, if you place a normal metal in contact with a superconductor, the pairing amplitude penetrates into the normal metal over distances, which may be quite long. If the normal metal is a ferromagnet, the length scale of the proximity effect is much shorter. And the reason is that the underlying mechanism, which is the Andreev reflection, right? When an electron is directed to the interface, it is retroreflected as a whole with the opposite spins. These are the Andreev pairs. And these Andreev pairs, if the normal metal is a ferromagnet, pertain to different bands. And this introduces a phase difference. And this phase difference gives rise to a center of mass momentum of the pair, and as a result, the wave function can be expressed as a combination of a singlet and a triplet pair, a triplet contribution. But this is a triplet with zero spin component in the z direction. This is not the triplets that we aim at for the proximity effect. There was the seminal result by Sebastian Bergeret, Anatoly Volkov, and Konstantin Nefitov that showed that in presence of an helical inhomogeneity at the interface, this these zero spin triplets turned into final spin triplets, and they can propagate long distances in the ferromagnet. This was shown initially in the weak coupling regime, but it was extended to the strong coupling shortly afterwards by Matthias Eschrich and Gerd Schön, Juan Carlos Cuevas, right? And so there is, I'm sorry. And experimentally, there has been consistent evidence for the existence of these triplets in the form of long-range supercurrents that were found, for example, in chromium oxide, which is a half-metallic ferromagnet by Kaitzer and collaborators, or by Jason Robinson, at that time PhD student of Mark Blameyer, when he succeeded in engineering an helical ferromagnet at the interface of a multilayer. So there has been variety of strategies to engineer these magnetic inhomogeneities at interfaces of multilayers, and this has produced consistently many results of these long-range supercurrents. The idea is that magnetic inhomogeneity produces a rotation of the quantization axis of the triplets and projects these zero-spin triplets naturally appearing in the proximity effect into finite spin triplets. Right? So, but what is missing is evidences for the long-range Josephson effect. Right? There is long-range supercurrent, which suggests there is a Josephson effect, but evidences for the long-range Josephson effect have remained elusive. And the Josephson effect, as you know, is a phase-coherent quantum state which produces a number of characteristic interference processes. So there's spatial interference due to the spatial evolution of the phase under a magnetic field, which gives rise to the Fraunhofer pattern, or time interference processes, which produces the time evolution of the phase under an applied voltage. I'm talking about the Shapiro steps. If you want to demonstrate Josephson effect, you should be able to show both Fraunhofer pattern and Shapiro steps. Right? So the experiments I am showing is in principle very simple. It's just make this wire of a ferromagnet with two superconductors across, right, and measure transport. That's all. and materials will be ferromagnet, manganite ferromagnets, and cuprate superconductors, right? So these materials we can grow in our laboratory already for many years. We do epitaxially using high pressure, pure oxygen sputtering. And over the years, we have, probably the reason we were so much encouraged to progress in this project was that over the years we have found a number of evidences consistently pointing to the existence of these triplets in these interfaces, right? And so these are, I'm sorry. These are results of 2004. This is superlattices, right? At that time, everyone was doing superlattices, and we found that the TC of superlattices was changing over a large thickness scale of the ferromagnet. And at that time, we entitled this work "Coupling of two superconductors through a half-metallic ferromagnet," right? Evidence for a long-range proximity. Afterwards, we get this oscillations with energies above the gap in tunnel measurements in collaboration with Javier Villegas, which were explained as in terms of Macmillan-Rowell oscillations pointing to coherent transport across the ferromagnet. And there were measurements by the group of Oded Milo in Israel showing a superconducting, I'm sorry, oh, that's really annoying. That's my fault, entirely my fault, huh? Okay, I'm sorry. So, and, sorry. and so basically, we had evidences for the existence of these triplets, right? Probably due to an equal spin Andreev reflection mechanism, right? So getting back to the experiment, technically, there is one more difficulty. In principle, this is very simple. There's a cross of materials, but the problem is that materials are grown at very high temperatures, 900 degrees pure oxygen. So there is no process, lithography resist, which would withstand this aggressive growth environments. So what we did is we opt for an ex situ process where we grow first the ferromagnet, we engineer the wires using e-beam lithography, and then we use a strategy of mechanical masks made of amorphous aluminum oxide, right? And in this way, we have produced these simple devices in which we have the ferromagnetic wire and two superconducting electrodes, and this we repeat many times into the same substrate, right? And so one important concern is that since this is an ex situ process, whether the interface quality is going to be good enough or not. And unfortunately for us, we found out that the interface is atomically sharp, both structurally and chemically. And the reason probably is the very aggressive oxidizing environment. 900 degrees and pure oxygen plasma probably anneals out any possible adsorbed dirt or even surface reconstruction, right? So, and we have very simple measured voltage in the LSMO and inject current across the YBCO, and we get, this is the normal curvature of the manganite, but we get a clear superconducting-like transition below the transition temperature of the YBCO. And we checked that the LSMO remains magnetic. We went to the synchrotron and we did photoemission electron microscopy. And as far as we applying the magnetic field along the easy axis of the manganite, which is in plane at 110 direction, we get that the wires are uniformly magnetized, as shown here, right? There are domains in some conditions, but this will come later. So we have measured a critical current, right? And we actually found that the critical current, I mean, there's substantial rounding, right? At this, I mean, because the temperatures are relatively high. And if we have a closer look at these critical current plots, we find that actually the critical currents are small, are really small, and we need small voltages and small currents to reach the nonlinear regime of the critical current, right? But still there is a critical current, and the small values are not unrealistic. If we stick these values into the equations of the SNS theory for the proximity Josephson junctions with normal metal and single superconductivity of Likarev or Dubos, right? We get that there is good agreement to the prediction of these theories, and changing the length of the weak link, we get quite good scaling of the size-dependent characteristic energy, which is the Thouless energy. So the conclusion of this is that the triplet pairs, which propagate in the ferromagnet long distances, behave as singlet pairs in a normal metal, right? So now if we want to show phase coherent Fraunhofer pattern, I mean, there's a technical problem because the critical current is so small. Measuring the modulation of the critical current with magnetic field is difficult, right? As you know, this Fraunhofer pattern is this modulation of the critical current which occurs every time the magnetic field amounts of flux quantum, right? It's a flux matching effect. And to probe a flux matching effect, what we did is measuring the resistance while we rotate a magnetic field in the plane. So for each angle, right, we measure a resistance versus magnetic field curve, right? And we get a modulation of the resistance due to the modulation of the critical current with magnetic field. And this is what it is expected theoretically from the Fraunhofer pattern, and this is what we get, which is quite close. So, and the idea is that when the magnetic field is directed parallel to the wire, there is no oscillation, which is what we get here. And when the magnetic field is perpendicular to the wire, we get a rapid oscillation, right? And from the period, I mean, this modulation of the period with the magnetic field actually, again, I did it. Okay. Sorry. Okay, so we were able to measure this modulation of the oscillation period with the orientation of the magnetic field expected from the Fraunhofer pattern, right? And only the length scale that we measure from the analysis of this oscillation period. I'm sorry. Okay, so there was a bit too long. The device was 1 micron size. We get 3 micron. Right? Remember this number, please. So now if we go to Shapiro steps. Shapiro steps, as I said, is the time evolution of the phase under an applied voltage. So basically the voltage over phi naught behaves as a frequency, and with this frequency is a multiple of the microwave frequency, which we illuminate the device, we get a resonant absorption. We get phase locking of the current phase relation to the microwave frequency, right? And so we measure the differential resistance under microwave illumination, and we get, again, I don't know, there must be, okay. So there is a clear Shapiro steps, right? There is this very characteristic steps in these contour plots of the differential resistance as a function of microwave power and the ratio of the voltage over the Josephson voltage, right? And only a very interesting observation is that these Shapiro steps do not occur for integer ratios of the voltage over the Josephson voltage, but half integer ratios. So this means that there is a dominating second harmonic in the current phase relation, which is not completely unexpected. This has been theoretically predicted for ferromagnetic Josephson junctions at the verge of the zero-pi transition and in other situations too. So this is something one can expect in a ferromagnetic Josephson junction, right? Now, if we I think there is. Now we did. Okay. I'm sorry. So if we revisit now the interpretation of the Fraunhofer pattern with this dominating second harmonic, we get that the effective length scale of the device is in fact what half the 3 micron I was showing you is 1.5 microns, which matches quite well with the geometry, the actual geometry of the device. So, how much time do I have? Very good. So it's more than enough. I'll finish before that. Okay. So so far I have shown that there is in 1 micron separation of 2 superconducting electrodes on top of a ferromagnet, there is a long-range Fraunhofer effect. And this I have shown this with evidence from Fraunhofer pattern and Shapiro steps, obtained with magnetic field rotating in the plane of the devices. Let me show you what happens now if I get the plane perpendicular to the cross-section of the device, as shown here, right? As shown here. So, actually, in principle, you don't expect to see anything because the effective area of the device is so long, so large that the magnetic field necessary to produce a flux quantum over this cross-section area is very small, right? In fact, the effective area of the devices is 10 micrometers squared, which produces matching fields of below one Gauss. So we didn't expect to see any Fraunhofer oscillation in this geometry, but contrary to expectations, we get very pronounced effect, and actually we get a very, well-shaped Fraunhofer oscillation, right? Which is anomalous. I mean, it's aesthetic, right? And it shows a very rapid modulation that go even more rapid at low temperatures, right? Definitely, it is not noise. I mean, because when we, in this low temperature rapid oscillations, we mirror one of the branches, it's superimposed to the other quite closely. So there is definitely no noise, right? And the effective areas that we get from these modulations are in the range of 10 to the minus 2 micron squared, right? And this corresponds for a 1 micron device, this corresponds to effective width of the device, of the current path of tens of nanometers. So what is of the size of tens of nanometers in this device? You may imagine that this has something to do with magnetic domains, which there are no magnetic domains with the magnetic field in plane when they point to the biaxial easy axis of the manganite, but when the magnetic field goes out of plane, there is nucleation of magnetic domains, right? And previously demagnetized samples, there is large disordered domains with many boundaries in the current path, right? But if previously there is a magnetic field applied in a hard axis in plane, there is substantial ordering of the domains, and we get to this situation where we consistently reproduce with inclined domain walls at 45 degrees, right? Where the magnetization, the arrows show the direction of the magnetization, which points at, the moments are at 90 degrees due to this biaxial anisotropy of the manganite. And the domain walls are these white fringes here, which appear wide in the photoemission experiment because the magnetization is out of plane, right? So there are Bloch domain walls, right? So basically, one can estimate from the XMCD experiment, but also one can estimate theoretically from typical values of the exchange energy and of the anisotropy constant of the manganite, that domain wall width is in the range 30 to 50 nanometers, which matches with the oscillation period of the Fraunhofer pattern that we obtained. But the second anomaly is that the main peak of the Fraunhofer patterns is displaced. It's not displaced in the direction one expects from magnetic hysteresis. It's displaced to the negative side. Say if we are sweeping the magnetic field, the magnetic field, say from negative to positive, the main peak appears in the negative side. So it's not magnetic hysteresis, which, by the way, we don't expect for magnetic fields in the range we use, which are 4,000 Ørsted, which is about 1/2 of the anisotropy field of the manganite in a perpendicular field. Right? So this seems to be an anomaly, which we may analyze in the framework of symmetry breaking. In the more general terms, the current phase relations contains an infinite numbers of harmonics of the cosine and sine type, right, both, right? And in the conventional Josephson effect, under time reversal symmetry, there is current inversion. I'm sorry, the current is anti-symmetric under the inversion of the phase, right? As shown. This must be okay. So as shown here, right? So if this antisymmetry means that there is only sine terms in the current phase relation, so there is an equilibrium phase difference which is 0. Right? This is the conventional Josephson effect. But under time reversal symmetry breaking, this antisymmetric relation also breaks, right? And there's for this, I mean, if this is true, you need cosine terms in the current phase relation. And it may happen that the phase equilibrium is different, the equilibrium phase difference is different from 0, right? And this, I mean, this current inversion asymmetry, field inversion asymmetry, both current and field inversion asymmetry, and diode effects in the current phase relation have been recently observed in topological materials and are the focus of a lot of interest in recent years. So, so what we have done to investigate this anomaly is to look at the Fraunhofer pattern with separate currents in positive and negative directions. You usually mix them both by averaging, but we have separated the positive and negative contribution to the critical current, and we get this very large asymmetry, right? Very large asymmetry. This is for positive current, this is for negative current, and if you sine invert this, you may see that it is completely different. When we invert the magnetic field, as we do with the blue curve over here, there is no good overlap, which is clear evidence that there is time reversal symmetry breaking in this system, right? And actually, we may get a good overlap is if instead of inverting the field, we invert the sweeping branch of the magnetic field to correct for hysteresis, right? So there's no question that there is time reversal symmetry breaking in this system, which is also not completely unexpected because there is a ferromagnet in the barrier, right? So, and this we have consistently shown for different temperatures and magnetic field sweeps, right? And so, from the point of view of the current phase relation, as I said, this time reversal symmetry breaking gives rise to the so-called chiral Josephson effect, right? And as I said, this has been shown in topological materials, but there is nothing topological here, we believe, right? And this asymmetry that we find in the critical currents means that we are, in fact, in front of a phi-0 Josephson junction with equilibrium phase difference, which is different from 0, right? What question is what can be chiral here? What can be chiral here? And probably what is chiral is the magnetic structure of the weak link, right? So if you look this pattern of the magnetization, this, as I told you, I mean, the arrows are the direction of the moments, and the magnetization comes out of plane in the barrier. So this structure has a finite spin chirality. A finite spin chirality in the barrier has been theoretically addressed by Jacob Linder and others, right? And proposed to give rise to anomalies in the Josephson effect similar to the ones we have measured. Basically, this chirality, this shifting of the magnetization produces phase shifts for the triplets to be able to follow the direction of the magnetization, which are most likely the responsibles for the anomalies in the Josephson effect. So this brings me to the conclusions. So hopefully I have convinced you that we have found a triplet Josephson effect, which is long range, right? In a half metallic ferromagnet, 1 micron long. There is a dominating second harmonic in the current phase relation. There's no theory for this. I mean, this is a D-wave superconductor and triplet proximity. There's no theory for this scenario. This calls for theoretical investigation. We have found evidences consistent with a phi-0 junction, right? Which we need to further investigate. And this introduces very, very exciting outlook because, I mean, this phi-0, this phi shift are determined by the magnetic structure of the weak link. So it is possible to store magnetic information in the face of a quantum device. So this is, in principle, a very, very exacting possibility to the design of a spintronic, completely new spintronic quantum logic, right? And also for the fabrication of non-dissipative phase batteries with magnetic memory of interest for future quantum devices. And I thank you very much for your attention.
Thanks so much for this beautiful presentation. Now, time for questions. Yes, please.
Did you try a Little Parks experiment?
No, but we have pursued this, and this. I mean, there is many features I didn't have time to discuss. When we believe that there may be Little Parks features in this system when we increase the temperature and we get above the Josephson temperature of the weak link, right? So that we think that the ferromagnetic domains get decoupled one from the other. We get a consistent oscillation in the resistance, which matches again with the size of the domain walls. And this is probably a scenario for little Parks effects. But certainly we should design an experiment to probe it directly. Yeah.
Other questions? Yes, please. It's coming.
So about this anomalous Josephson effect. So as I understand, this phi naught shift, it doesn't affect the critical current.
Say that again, please. I didn't.
The phi naught shift in the current phase relation does not affect the critical current. So the critical current doesn't depend on the phi naught shift. So why does it, the question, why does it show in the Fraunhofer pattern then? I mean, this phi naught. So according to my understanding, the Fraunhofer pattern should be the same for like a usual Josephson and for the anomalous Josephson.
The Fraunhofer pattern should be the same. I'm not sure I understand.
Because this phi naught shift, it doesn't affect the critical current. So you can just eliminate it.
Yeah. The phi naught term we infer from the breakdown of the current and field inversion symmetry.
Yes, but you infer it from the Fraunhofer pattern, but from the shift of the dependence of the critical current on the magnetic field. But this phi naught shift should not affect this dependence of the critical current on the magnetic field.
No, we don't know how it. And of course, no, we didn't claim that we get the value of this shift. Yeah, you are right. Yeah. I'm not sure I completely understood your question, but maybe we'll talk later.
Thank you. It's a really nice talk. I'm wondering the transition temperature, and it's really broad, and it's not sharp. It's the zero resistive is you got to the 40 Kelvin. And did you also analyze the critical temperature as a function of the barrier thickness? I mean that the length of this magnetic wire.
Yeah, you are completely right. I mean, this is a high temperature device, and it's very long. And I mean, there is a strong effect of thermal fluctuations. So I will come to this in a moment. But apart of this, the device is very complex, if you think of. I mean, there is LSMO just below the superconductor, which proximatizes first. Then if it becomes proximatizing along the weak link, and probably in the last term, it proximatizes across the domain walls. So this gives rise, if you look carefully at the resistive transitions, they are, I mean, it's not only very wide, there are steps which probably correspond to the proximization of the different regions. But as I said, we looked at also at the effect of thermal fluctuations, and we analyzed the critical current at different temperatures in the framework of these theories of Ivachenko and Silverman and Gokar and Halperin, right? To evaluate the effect of the thermal fluctuations in the rounding. And certainly there is, and there is the lower portion of the IV curves we could fit consistently with these theories, but in the high voltage regime, there is these steps contributing from the different regions, which make it impossible to get a consistent fit to these theories. So there is both. There is thermal fluctuations, and there is inhomogeneities in the proximity effect in the device.
not related to ferromagnetic barrier?
Not as far as we can tell, because we get the same, in different configurations of the magnetic field, we get the same sort of steps. But I cannot be completely sure, because in the end, if there is Josephson coupling across the domains, this happens. I mean, this is something that you feel in the lowest temperature jump of the resistance.
Okay, thanks.
Other questions? I have actually two technical questions. First of all, did you measure also as a function of the length of the weak link?
Yes, we did, and maybe I can go very fast. Oh, okay.
You know, that's
yeah, we did, and we found that we get the correct scaling of the Taule's energy, which is size dependent as a function of 1 over the length of the wiggling squared. And we get that the critical current scales correctly in function of this.
Okay, which is the minimal length you can get, you know, as close as they can?
You know, this is a problem, yeah, for us. So the shortest we did in the planar geometry was half a micron, 500 nanometers. Okay. So we also have results but in vertical geometry that we get to lower, and we also see a Josephson effect.
Okay, which is the lowest temperature you measure your junctions?
Which is the lowest?
Lowest temperature you measure your junctions. From TC down to?
Oh, the lowest temperature?
Yes.
No, it's not very small, because this experiment done in a closed cycle refrigerator. So
okay.
It's
that would be
4 Kelvin or so.
4 Kelvin?
Yeah.
Okay.
Yeah.
Okay.
Yeah, this is a Montana refrigerator.
Okay.
Yeah.
Do you use filters, special filters
for the low voltage measurements?
Yeah.
Yeah.
Okay.
Yeah.
Okay.
Yeah.
That's
yeah, nanovoltmeters. Yeah, it compares.
Okay.
Yeah, this for a purist in the Josephson effect. I know this. I mean, we discussed this with Jerome extensively. But of course, I mean, if you say something, I mean, I'm very scared.
No, you should not. To the point that I give you on behalf of.
Thank you very much. Thank you. Thank you.
So thanks so much again, and the session is closed, and we see in about 20 minutes for the other session.
name is Jens Wiebe. I'm from the University of Hamburg and I'm chairing the session. And I'm happy to introduce the first speaker, which is Steffen Wirth from the Max Planck Institute for Chemical Physics of Solids in Dresden, Germany. And he will be talking about non-trivial surface states detected by STM.
Can you? Okay, thank you very much. Thank you very much, Jens, for the kind introduction, and I also want to thank the organizers for inviting me here to this very nice place. As already mentioned, I want to talk about the detection of non-trivial surface states by our STM, and I'll concentrate on two materials. The first one is a condo insulator, meaning a strong correlated material, samarium hexaboride. And the second, I should say, class of material is a half-Häusler, or the half-Häusler compounds, yttrium palladium bismuth and yttrium platinum bismuth. But before I actually get into physics, I would like to acknowledge my collaborators. This is a talk about STM, so these are the most important people here. Lin Zhao, now in Tallahassee, Vicky still with me, and Jean Souza, now at the Weizmann Institute. The samples came either from Los Alamos, Zach Fisk earlier, and nowadays Priscilla Rosa. And the yttrium-based half-Häusler compounds came from Campinas. And I also appreciate lots of discussions I have and, of course, the funding. Now, to get started, okay, a quick reminder. Scanning tunneling microscopy is not only very good in looking at surfaces and seeing how the topography looks like here. Now, this is niobium diselenide, and you see the charge density wave. But actually, we can now go for a predefined position and do spectroscopy, so very local spectroscopy. And the point I want to make here is that the IDV curves I'm going to show are proportional to the local density of states, and we can get information, direct information about the one-particle Green's functions. And that was very nicely alluded to already yesterday, for instance, in Professor Wiesendanger's talk. Now, let me, this is the instrument. We are mostly using a UHV scanning tunneling microscope, base temperatures 0.3 Kelvin, and we have a 12 Tesla magnet inside. This is coming with a little bit of a delay here. I have to get used to it. Now let's get started by looking at samarium hexaboride. STM is a very surface-sensitive probe. That means we need to have clean surfaces. So what we typically do is first going into UHV, and secondly, we cleave the samples. But then we have to ask ourselves, so what about the surface? Here, in case of samarium hexaboride, it's a cubic structure, so we don't have a preferred cleaving plane. And on top of that, the samarium, the valence of the Raher, it doesn't have to be samarium, is between 2 and 3. So we end up with polar surfaces if we cleave along one of the main crystallographic axes. And polar surfaces are known to be prone to surface reconstructions. So, and in consequence of that, this is what we mostly see. These topographies are not atomically flat. And I should emphasize here, this is the vast majority of the surface areas we look at. So this is certainly not what we are aiming for. You could imagine that the individual atoms here have different environments, and it's certainly not, or it's not necessarily related to the samarium hexaboride that we are interested in. And that should be kept in mind, because if you look at, into ARPAS or something like that, you know, you always average over certain areas. Yeah? Here with our STM, we can concentrate on smaller areas, and then with some luck, you get actually nice areas like this one. These two here are samarium-terminated surfaces. The ones here on the right-hand side are boron-terminated surface, and that's what we basically need and what we are going to focus on in the next minutes. But I should mention again, these patches are only something like 60, 70 nanometers in size, if at all. What could be a little bit larger is actually these reconstructed surfaces here. Think of that here in this case, each second row of samariums taken away. So you end up with a 2x1 reconstructed surface. They can be a little bit larger, up to a micron or so. But they don't need to be straight lines here. They can also meander around, but it takes care of the polar surface issue. Okay, now if we go for the nice areas like shown here, then you can do spectroscopy in a clean region, and you immediately see there's a lot of things going on, yeah, specifically at these low temperatures. You need to go below something like 2 to 3 Kelvin in order to see that. And then you can relate that to the band structure, and it's clear that here in this case we have multiple bands involved. And the first thing that we think is going on is that we see the onset of the hybridization gap in the order of 20 millielectron volts in line with other measurements. Then we have the small peak here. It's a very small one, so we think it's related to the gamma A2 band here. That's very flat, but hybridizes only very little, so we have very little access to it. The matrix elements are probably pretty small. But most importantly, we have this peak here at minus 6.5 millielectron volts, and that's what I'm going to focus on in the next couple of minutes, and I'll show it. It has some bulk contributions, as shown by other measurements, but mostly it has surface contributions, and that's what I'm going to focus on in the following. Now, the issue here is actually that, there's a lot of discussion, and most people nowadays believe that samarium hexaboride is a topological insulator. But it's actually pretty difficult to show because of the small energy scales involved here. It's only a few millielectron volt you need to resolve. So ARPES is pretty much at the limit, and also there are controversial results, for instance from ARPES, but also from other measurements. So what we thought of doing is, what about the surface? We are very surface sensitive. So maybe if we talk about topology, we can make use of the time reversal symmetry breaking in case of magnetic impurities. That shouldn't be there if we, for comparison, also put non-magnetic impurities in. So that's what we set out doing, and actually the hexaboride structure is here very flexible and helpful in a sense that we can put almost any raw earth and also other elements here on this side. So what we set out doing is, on top of also looking at the pure samarium hexaboride, to look at the gadolinium doped ones and the yttrium doped ones, so we have a magnetic and a non-magnetic impurity, so to speak. These are the surfaces we are going to investigate in the following. So on the left-hand side, I have pure samarium with a defect here. This is a 3% yttrium doped sample and a 0.5% gadolinium doped sample. And I would argue that this here are gadoliniums, these here are yttriums, and we can speculate about this defect if you wish to. But if we now do spectroscopy, then if you are far away from the defect here on the clean area, then you see the spectroscopy I have just shown before, and that's actually common to all of these samples here, independent of what we dope with. So here, if you are away, the same structure, but then if you approach the defect, you see that here actually the apex of this peak is a little bit chopped off. In contrast, if you look at the gadolinium here, you see this peak here, if you are right at this defect, it's almost completely gone. Yeah? In order to be a little bit more quantitative here, what we did is we looked at the height, simply the height of this peak, and we compared this, or we showed that here in dependence on the distance from the defect. So the defect is here located at 0. And as you can see here, at about 1.5 nanometers away from the distance, we have the clean surface, so everything has recovered. But then if we go towards the impurity here, we reduce the peak height by about 25%. That's different on the gadolinium. Here, if we are away from the defect, again, we have the clean surface, but we go down here if we approach the impurity by about 75%. So that's much stronger a reduction, and also it's over a larger extent of about 2.2 nanometers. I'll come back to that in a second. So clearly, this peak here at minus 6.5, and also the one I haven't alluded to so far, the minus 2.5, is mostly due to surface contribution. So we looked around in the literature whether there's any theory that can account for that. And indeed there is. And the main ingredients here are basically an exchange interaction between the local magnetic moment and the surface state electrons here. Also, the Fermi velocity comes into play here, and of course the suppression length, which we get here, or the healing length, as Zach Fisk dubbed it. So we actually got in touch with Xiaoxing Liu from Penn State University, and he helped us very nicely with doing here a model calculation, and you see it fits our data pretty nicely. So what we get is an exchange energy of about 1.4 millielectron volts and a Fermi velocity of about 3,000 meters per second. Most importantly, you see we now get a nice fit, and that's where we get the suppression lengths from. So in case of a magnetic impurity, we get 2.2 nanometers. In case of a non-magnetic impurity, yttrium, or a defect in the pure samarium hexaboride, we get about 1.5 nanometers. So clearly the surface state is suppressed over a larger extent in case of the magnetic impurity, and we can compare that actually to other results. So there are nice measurements by Jenny Hoffman's group here on the 2x1 reconstructed surface, and what they get from quasi-particle interference image on the surface is the location of the Dirac cone, which is at about -5 millielectron volts. So that's very nice, because with -5, if we have the additional exchange energy to overcome, we end up with the peak at -6.5 millivolts. Also, our 3,000 meters per second for the Fermi velocity is basically in between the two velocities she gave in her paper for the two different directions, so that fits very nicely. One question remains open. Why do we actually see a suppression in the case of the non-magnetic impurities at all? Now, here you have to think about that what we are starting with is a condo insulator. So we have samarium hexaboride, and only if we have samarium on each lattice side, we can make up or build up this condo insulating properties. If we now take away samarium, we basically create what's known as a condo hole. And that can also be magnetic, and that we think is the origin why we also see something in case of non-magnetic impurities, but as you can see, it's less pronounced. Now, in order to come up with a picture on what's actually going on, I have here this little cartoon. We now basically look at the surface of the sample, and we have suppressed the surface states here around the magnetic impurities. Now, in this case, if we have only a very small number of impurities, you can still have a percolating path here, and you still have this plateau here, which is a plateau in the resistivity at low temperature, which is a hallmark of the surface states in this material. But now, of course, if you increase the number of defects, at some point you prevent percolation. Yeah? And in case of gadolinium, that already happens at 3% gadolinium doping. You see here, the plateau here at low temperature is suppressed, or is no longer visible. Yeah? It just goes up. There may be something left over here, but the surface conductivity, we think, is no longer percolating. For the non-magnetic case, we now, because it's smaller in extent, we need more of substitution. So we would actually need something like 12 to 13%. That's our estimate. The sample we had to our avail was 18%, and you see clearly there is no plateau here. But now you see already a problem. I mean, 3% or 80%, this is not a small impurity number. Yeah? So if we do such large substitutions, you run into the question, well, what do we actually do to the sample from point of view of inhomogeneity or the Kondo effect? And are we actually really certain? We are looking at the gadolinium, for instance. So we thought about this and thought, okay, the only ingredients we need here is the exchange interaction. So why do we actually need to put the magnetic impurity into the sample? We could also have it on the tip. Yeah? So we set out and did STM with a chromium tip, chromium-coated tip, and here's the result. You now see for the tungsten tip, the red, that's what you have seen before. Now for the chromium tip here, it's completely suppressed. There might be a little bit of a leftover. We think that's the bike contribution, but for the most part, this peak is suppressed. And it's not a matter of some stray field or something. I mean, you wouldn't expect anything from a chromium antiferromagnet, but nonetheless, just for cross-check, I show here a tungsten tip result in applied 12 Tesla, and you see a 12 Tesla field doesn't do much to the spectrum. It's here offset for clarity. It really takes the exchange energy to suppress the surface states. Now, if you listen carefully, I mentioned in the beginning it's actually pretty difficult to find clean spots. So now here you could ask the question, in order to do that comparison, I have to take the tungsten tip out and replace it by chromium. So who tells me that I'm actually at the very same position? Do I actually compare different positions here? That's a question we cannot really truly answer. But what came to our help is the following observation. Now, we go back to the gadolinium doped sample here, 0.5% gadolinium doped, and to the regular tungsten tip. So what we see with a newly introduced sample, newly cleaved sample, is the normal spectrum I have now shown several times. But then if we scan, it happens every once in a while that we pick up something from the surface, and we see that by a step in the topography. And then the spectra here is changed heavily. And it's now similar to what we have seen on the gadolinium substituted before, and also to the chromium tip. Now, this only happens on the gadolinium doped samples, but we have one more parameter to play with to make my argument complete here. We can actually get rid of the add atom by applying a pulse to the tip, a 10-volt pulse, and if you remove the added atom here, you basically recover the original spectrum. So that's, I think, very nice proof that it really was due to the add atom and very likely a magnetic atom gadolinium. We have never seen that on a samarium or on a pure samarium or on an yttrium-doped sample. Now, we also tried to play a little bit with the samples itself. So, for instance, we tried to grow, or actually Priscilla tried to grow samarium deficit samples, but this is a flux growth method. And in contrast to the floating zone growth, the samples always like to grow at the 1:6 composition. So as you can see here, for the nominally 0.75 boron 6, there's no defect at all to be seen. So basically what we learned from this phase is very, very stable. So any approach here didn't help us. We also tried to manipulate the surface a little bit with our focused ion beam. And here you see we increase the number of cuts. We simply cut the surface to interrupt the surface states. And as you can see here in the sample surface with the most cuts, here we have a distance between the cuts of about 10 to 15 micrometers. You still see that the resistivity, that's the sample called F9, plateau is developing. So the surface states are still there. They are now meandering through the cuts, and also we have increased scattering, of course, but it's, the plateau still develops, meaning that if we cut trenches, the surface states just follow the newly developed surface area. Okay. So much for the samarium hexaboride. I now want to switch over to the other compound I want to report on, which is a half-Heusler compound. And if you start here from the normal regular Heusler compound and you take away half of these red atoms here, then you end up with the half-Heuslers. Yeah? You could replace that by another species, here for instance the blue ones, and then you end up with the what's called inverse Heusler alloys. So this is a very versatile family of compounds. There are more than 1,000 compounds of the Heuslers known. It's a cubic structure, so we can put quite a variety of elements on all of the three sides. And that means we can play with the properties. Depending on what we put in, we can either have magnetism or play with the spin-orbit coupling, or, that's why I showed this example, even play with the symmetry. What I want to focus on here is actually the interplay of spin-orbit coupling with topology. Now, what I will focus on is ytterbium-palladium bismuth, ytterbium-platinum bismuth, because they have almost identical lattice constants. Yeah? There's not much happening if you replace palladium versus platinum. Yeah? And you see that here in this plot where we have the lattice constants independent, and here on the vertical axis, the gamma 6, the location of the gamma 6 band with respect to the gamma 8 band. I'll come back to that in a second. Here they are almost at the very same lattice constant. So why do we plot this particular type of energy here? It tells you about the band inversion. If the gamma 6 is above the gamma 8 states, then you have a trivial insulator. So the S-type is just above the P-type. But if it's the other way around, you have a band inversion. Yeah? And that was theoretically predicted already more than 10 years ago. So again, as I mentioned, this is a cubic structure. So again, we had a difficulty of cleaving. And it took us quite some time until we actually got some nice surfaces. Oh, wrong direction. But then after some time, we actually found a very nice surface. Here you see a triangular lattice of the corrugations, and that immediately tells you we are looking at a 1-1-1 surface. Yeah? Otherwise, it wouldn't make sense. The distance between the corrugations matches nicely with what we expect from XRD or basically from the lattice itself. So we expect 4.69 angstrom, and we get 4.6 from our STM, so that's very nice. And also, if we look at steps that we see here, we get typically something which is in the order a little bit less than 400 picometers, and that's basically here the lattice, half of the lattice constant. But every once in a while, we also see steps of about 100 nanometers, and then we clearly know that the palladium, or in this case, the platinum, is involved here. Because this line is missing here because it's a half-Heusler along this direction. It's missing. What we see is, independent of what surface we are looking at, the spectra look very much alike. They look V-shaped, but we have a very finite density of states. So it's not an insulator, yeah, in this case, at least not at the surface. Now, the bad or negative surprise came when we looked at the palladium. Despite heavy searching, and we spent more than 2 months on that, and several samples were cleaved, we did not see any decent cleave on a 1-1-1 surface. But I should stress here, in order to compare the two compounds, of course, we need to cleave along the same direction. They need to be crystallographically identical. Otherwise, we would compare apple with pears or whatever. Yeah, that wouldn't be a fair comparison. So, okay, we went back to the palladium, to the platinum, and the second best topography we found is shown here. You see, it's not quite as nice as the 1-1-1 directions, but we do see a regular arrangement of the corrugations with this distances shown here. They come from Fourier transform, but you can also get it directly from zoom into these into nicer areas. And we also get step edges in the height, with a height of a bit more than 100 picometers. And actually, if we go for an area like this, where we have quite an assembly of step edges, we get something in the order of average of 125 picometers approximately. So now we also know, because whenever we put our samples into the STM, we do Laue beforehand in order to know the orientation. So in this case, we know we have a 001 surface attached to the sample holder. And while scanning, we noticed that the surface is actually inclined by about 30 degrees. So this gives us a good hint of what surface we are actually looking at. And we think it's the 012 terminating plane in this case, because in this case you expect something like 29 degrees for the surface inclination. And also, if you look at the distances between, thank you very much, between the corrugations, then it becomes clear we very likely don't have platinum here. It seems to be that we have a bismuth yttrium terminated surface plane, and that's also be seen by others, for instance, by ARPAS measurements and so on. But we seem to have a 2-by-1 reconstructed surface. Now, just for comparison now, for the palladium, in this case, we were lucky. We also found atomically flat surfaces, as shown here, similar distances between the corrugations, and again, this tilt of about 30 degrees. So far, we haven't seen any step edges, so this part of the comparison is missing, but still, I think we do have sufficient evidence that this is a 012 surface. And well, again, with the 2-by-1 reconstruction. The reconstruction is actually, in this case, not a bad thing because we expect dangling bonds here, and with the reconstruction, we minimize the number of dangling bonds, so we avoid trivial surface states. Now, if we look at the spectroscopy and we compare different areas and also the average over the whole area shown here, we do see a large difference between the two samples. In case of the platinum, as for the 111 surface, we see a finite density of states, again here the V-shaped spectrum, but in case of the palladium, you see a clear gap here. So there's clear-cut difference here. Now, of course, that calls for band structure calculations, and indeed, if you look back into literature, there are a number of band structure calculations already done, but they mostly focus on comparison to ARPAS. So far, we haven't found any STM report on these Halfhäusler compounds. So, and what we need here is actually very much the surface states. So that's why we got in touch with Andrzej here. From Krakow, and he did, first of all, DFT calculations and compared with the literature and found a nice agreement. But on top of that, he also calculated surface green functions by using Wannier tools, and that's actually what we need and what we can compare to now to our STM results. So let's first have a look here at the platinum-based compound. You see here right above the Fermi level, we have a Dirac point here, and we have these surface state bands, or surface bands here, very close to the surface. And we think this is the reason why we see here a finite density of states in case of the platinum. As you can see, for comparison here in the palladium-based compound, there is no such thing here, no Dirac point visible, nothing. And in agreement with that, we do see the gap. We would like to have density of states, and he's working on that, he promised. So that's as much as we have right now for the comparison. But what we can compare to also is the bulk properties. Yeah? And it's known, that's the last slide actually. If we look at the Sommerfeld coefficients, they are very small, but comparably small for both the compounds. And that tells us in the bulk, we have a very small local and very low local density of states near the Fermi level. Yeah? And the same result comes from the density of states. So that increased density of states here cannot be explained by bulk states. Yeah? So very likely that comes from the band inversion in case of the platinum, and very likely this is due to the non-trivial topology and not from the surface reconstruction, which has not been taken into account into the calculations so far. And that brings me to my summary. I hope I've shown you that we have indications for surface states in the Zermanium hexaborides, which are suppressed by magnetic impurities more heavily than non-magnetic impurities. And the same also happens for magnetic tips. If we use magnetic tips, so very likely we have an exchange-driven mechanism. For the Halfhäusler compounds, we could identify the 1,2,0 surface in both compounds and compare the density of states. And they are in agreement with surface band structure calculations. I actually intended to show a third materials where we, this is hafnium silicon sulfide, where we see very nice quantum Landau quantizations, but in the interest of time, I skipped that. Thank you very much for your attention.
Yeah, thank you very much, Steffen, for this very interesting talk. Other questions?
Thank you for an interesting talk. Concerning the suppression of the surface states around the impurities that you looked at, the magnetic impurities, is this visible for both negative and positive voltages?
Wait a second, we do it? No. We concentrate on the peak for which and that's at minus 6.5 millielectron volts, which we think carries the most of the surface contribution of the states. That's where we think the states are basically located. So we sit at this very energy. Yeah? If we go away, we don't see much of differences. Yeah, that's why I made in my introduction the assignment of the peaks. Yeah, we think this is very much where the surface states are located. So we have to be at this very energy. There is a side peak which I haven't really alluded to at minus 2.5, but it's not as well developed, and it's actually on the rising side of the bigger peak. So it's difficult to analyze with much larger error bars. Maybe you noticed that there were always two markers. They coincide, but I would put the emphasis on the minus 6.5. Yeah? That's where the states are located, we think.
Okay. A second question, is it purely isotropic, these suppressions that you see, or they contain some spatial structure?
Well, I cannot rule out spatial structure. We haven't seen anything. But, you know, we are always happy when we see some nice areas, yeah? And then if you go away in a certain direction, it takes some time. And after a couple of days, let's say 3 days, I have to refill liquid helium. And we need to retract the tip. If we go down again, we cannot be certain that we are at the very same position. So it's very difficult for us, or we haven't done so far, let's say, from one impurity go into different directions. We went, let's say, cross-like, that I can rule out, but you know, we haven't done any, let's say, 45 degrees or so. This I cannot rule out, I cannot answer. We simply weren't able to do so.
Okay, won't you see that in voltage-dependent imaging?
We haven't seen anything, but that doesn't have to, I mean, I don't trust that too much. I would love to go, you know, like this, but, well.
Maybe we, sorry.
Go ahead.
Sorry, I think we have to move on. Maybe you should continue the discussion during the break, because we are a little bit in lack of time. Oh. Thanks, Steffen Wirth, again for this beautiful talk. Okay, so the next talk will be given by Andrzej Tok from the Institute of Nuclear Physics from the Polish Academy of Sciences in Poland, and he will be talking about first principle studies of non-trivial topological phases in 3D transition metal atom chains.
Everyone, and I'm Andrzej Tok from Institute of Nuclear Physics, Polish Academy of Sciences, and I'll present you today our results of first principle study of 3D transition metals monoatomic chains in context of realization Majorana bound states. So subtitle is Majorana bound state, to be or not to be, and our results are also available in this PRB paper. Okay, so typically topological properties of systems are associated with spin orbit coupling physics. This very beautiful figure where we see several properties or behaviors of systems where we expect this spin orbit physics, but for us today is most important this Rashba physics. And yesterday Professor Wiesendangen presented excellent lecture about Majoranas, so I present only very short introduction to this. So here we have a very artistic figure how we can expect and how we can understand Majorana's bound state. Here we see well-localized wave function at the end of monoatomic chain. Majorana bound state in this case should have zero energy states, and indeed should be realized at the end of low-dimensional systems. From theoretical point of view, we know more or less what conditions should be fulfilled by the system where we expect realization of Majorana bound states. So when magnetic field in one-dimensional system is bigger than this square root, where chemical potential is calculated from bottom of the band, then you can expect realization topological phase and Majorana bound state at the end of one-dimensional chains. Then topological phase diagram will be given by these parabolas. However, magnetic order, for example, can change the situation and more complicated topological diagrams can be found, like here in the present of antiferromagnetic order, where even without magnetic field, Majorana bound state can be expected. Okay. Also, situation can be more complicated when effective potential in our system is non-homogeneous, like in these optical lattices, in one-dimensional optical lattices. When effective local on-site chemical potential is tuned correctly, then we can realize topological phase in whole system and one pair of Majoranas at the end of this one-dimensional system. However, we can, in this optical lattices, in a relatively simple way, tune of chemical potential, and also more complicated situation can be expected like here, when we realize topological systems only on some parts of one-dimensional chain. Here we have situation, for example, when we have two topological systems separated by part of trivial system. However, we should come back to experimental realization, and recently we know several setups of these systems where we can expect Majorana's bound state. One of them are magnetic chains deposited on superconducting surface, this left figure, or hybrid system where we have semiconducting chain partially covered by superconducting material. So in this second case, we expect in differential conductance zero bias peak. Above some magnetic field, we expect realization this topological phase. Of course, also in this situation, we can expect some interplay of Majorana bound state or every bound state with some parts not covered by superconductor, which can be treated as a quantum dot, like this famous Deng paper. However, for me today is more important this setup where we want to realize Majorana bound state in magnetic monoatomic chains. Here is results from Professor Yazdani group from Princeton, where they realize iron chains using epitaxy on lead surface. So here we see more or less how this chain is realized. Unfortunately, in this situation, this chain is not very ideal because we have a mismatch between lattice constants of chain and our base. This second result, when we have spin polarized STM result, and at the end of the chain we see non-equal contribution for spin up and down. And this can be treated as evidence, more or less evidence to realization of Majorana bound state in this system. And second system discussed yesterday by Professor Wiesendangen. This is much better situation when we realize exactly one-dimensional ideal chain, one atom one by one on surface, superconducting surface here. And moreover, we can change in a relatively simple way this length of this chain. And one additional results, dependently by length, we can observe better localized at the end some state. And indeed, when chain is relatively large, for example 100 atoms, this localized state is very nice. However, my main question is still open, Majorana to be or not to be, and now I want to focus on two experimental papers. more precisely about theoretical part of these two experimental papers of Professor Yazdani, where they have iron monatomic chains, let's say monatomic, and second paper, Professor Franke from Berlin, with cobaltium chain deposited on lead surface 110. So in both papers, we can find this part where, from theoretical point of view, this system is described by Slater-Koster approximation, and moreover, for D-wave orbitals of bulk compounds. So not exactly chain, but authors take Slater-Koster parametrization for bulk and try reproduce band structure for chain. So this open, of course, few problems. So maybe first how we can find this type of parametrization. So very simple, because we have very nice book about this type of approximations. It looks like this. So inside we have a lot of numbers which describe hopping integrals between different type of orbitals. So we can find some specific atom, compound with specific symmetry, space group, and in this way we can find, let's say, in simple way, band structure of our system. However, this parameterization don't tell nothing about spin-orbit coupling, and this spin-orbit coupling should be introduced to our calculation by hand, like here, by authors. In both cases, they take 0.2 eV. So next problem is how we can compare bulk system with chain. So this is similar like in this very known game, find tiny differences. And believe me, this situation is much complicated than our, because in our system we have bulk from left and chain from right. So without any problem, we can find minimum one difference. And as probably everyone see, system from left side has much more neighboring side than system from right side. So band structure probably, and as we know, shouldn't be the same. Second difference may be not visible very well here. When we relax our system, then distance between atoms in left and side situation is not the same. In other words, we change distance between atoms, and in this way we change overlap between d orbitals, for example, in these 3D atomic chains. As consequence, we change also hopping integrals, which is exactly given by this overlap of orbitals. And this, of course, change our results. And next problem is that Slater-Koster parametrizations do not fit to exact band structure obtained from the FT calculations. Here is very nice situation, compare of these results, where we compare exact black line, exact results from the FT with approximation Slater-Koster, and obtained from Vannierization. So we can express our momentum space calculation in the FT in real space Vannier orbitals using maximally localized Vannier orbitals basis. So okay, this is our main manner using in these calculations. First, we want to calculate exact band structure from the FT. Using this exact result, we want to find Vannier representation of our system in real space. And next, using this Vannier representation, we want to calculate something more and tell something about topological properties of our one-dimensional transition metal chains. So when we check band structure of bulk systems, we see here we have around Fermi level a lot of bands. Of course, this is 10 bands from 5D type orbitals. And somewhere far above Fermi level, we see strong hybridization with some other orbitals, other bands. And what is interesting, this hybridization can play important role to modification, some renormalization of band structure in our one-dimensional chains. And indeed, when we calculate, for example, direct band structure for chains, we see that these band structure are not given by simple cosine, like in one-dimensional chains typically, because we have some modification of bands, for example, at top of these bands, given by some hybridization with upper bands. Similarly, also shape, these bands can be changed, and also some inside this d orbitals hybridization also can change some crossing or lead to avoided crossing, like in this pink area. So this compare of our tight binding model with exact DFT calculation with spin orbit coupling. Tight binding model here is given by this blue dashed or dotted lines, while DFT calculation with spin orbit coupling is given by pink lines. So this model very good reproduce this band structure from DFT calculations. So when we compare this with this previous presented bands from experimental paper based on Slater-Koster parametrization, we see that first this band is exactly not the same, and second, spin orbit coupling is much smaller. Here was given by 2 EV by hand. However, from exact diagonalization, we see this splitting of bands is much smaller, and this splitting of bands corresponds exactly to the spin orbit coupling. So okay, so now we can take our tight binding model obtained from DFT calculation and try calculate topological invariant, and here is in practice our equations. So first is tight binding model in Wannier representation. Unfortunately, we can take superconductivity from DFT, so this is one point when we put something by hand. So we take BCS-like term, superconducting gap around 3-4 millieV, and later we can calculate from off-diagonal form of Hamiltonian quantum invariant. When Q number is negative, then topological phase can be realized in this chain. And this is our main results. So what is surprising? For iron, the topological phase is not realized. However, for cobaltium can be. And here we have, of course, additional comments to this, because nearly Fermi level, we observe several crossing, some bands. So these results can be strongly depended by position of Fermi level. And for example, this Fermi level can be also shifted by the position of our chain on some substrate. So indeed, we calculate something similar for monatomic chain deposited on lead 110. So this is our band structure, much more complicated. Black background is given by projection of bands on only 3D transition metals. And again, around Fermi level, we have a lot of bands. And here results can be indeed strongly depends by position of Fermi level or any disorder and so on. So we calculate also density of state, and our systems in sense of chains are ferromagnetics mostly. And this is my summary. I have 3 types of summary. So I start from negative, unfortunately. So theoretical description by Slater-Koster tight binding is incorrect, unfortunately, and we should looking something better. And moreover, one band or one orbital description should be treated as a toy model. I show you that band structure obtained from DFT is not the same like Slater-Koster parametrization. And moreover, as we know, when we want to describe magnetic chains where we have more than one orbital, then one orbital picture is not adequate. So neutral summary. Experiment is always correct, so we don't discuss with experimental results, but with theoretical description. And second neutral point is description should be more realistic. So indeed, more orbitals is necessary, and sometimes also some substrate. And positive important role of substrate, what was presented yesterday by Professor Yazdani. And last point, to next studies, still attractive issue to study. Thank you for your attention. I wish you long live and prosper.
Yeah, thank you for the nice talk, Andrzej, and now it's open for questions.
Yeah, thank you very much for a clear talk. I liked your cartoon about the 10 differences. Actually, the most important difference is probably not between bulk and the chain systems you have calculated, but actually the fact that in all previous studies of iron chains on lead, you did not even have a crystalline structure. These were all disordered chains because of the intermixing between iron and lead. And the reason is that you cannot avoid this by the self-assembly process, which uses a high temperature treatment. And so you get intermixing simply because lead is very well known to be a surfactant. This is a very well-known fact in surface science. So you get always the tendency that the lead would like to be on top of the iron. And that leads to severe intermixing. And experimentally, this is proven in the data published in the Nature Physics paper by the Princeton group. The line profiles of the differential tunneling conductance along the chains were always very irregular. It's not a crystalline system. So, of course, you say experiments are always correct, but they have to be interpreted in a correct way. And there's no way to get a matching between theory, which assumes, of course, a crystalline structure, and experiment where you don't have a crystalline structure. That's just a comment.
Thank you very much. Yes, indeed. I showed this cross-section, for example, this realization. So I discuss only with theoretical description. Yes, indeed. They use one monoatomic chain to description of this realization. Yes.
Yeah. Any other questions? We have plenty of time. Okay, so then maybe I can ask a question. So I find it pretty interesting that you get an increased spin-orbit coupling if you are not working with these bulk parameters. And I mean, indeed you see that the spin-orbit coupling, no, it's reduced, right? And my question is, do you know some hand-waving reason? Or, I mean, just for an experimentalist, of course, always it's important to know what do I have to do to increase spin-orbit coupling. So you can use a heavier substrate, but then maybe this is not the whole story. So you also have to look at the surface and stuff like that.
So this result was for chain, exactly chain without substrate. So maybe substrate can lead to increasing of the spin-orbit coupling. Of course, in typical situation in bulk system, enough is when we substitute some more massive atoms. This is a situation when we increase this, somehow tune this spin-orbit coupling. But in this situation, probably problem is also with this chain, where we can do this probably.
Okay, thank you. Any other questions? I don't know how this works with questions from the online audience. No questions. Maybe just also another comment on this LED system. I mean, so even for the system itself, there are experimental results also from Katharina Franke's group. You probably know for the iron chains on the LED, which show that for many of the chains, they do not find a zero bias feature, right? So
this is also surprising for us because in our calculation, Q was negative, yes? So not exactly like in this experimental paper, but in inverse. And as I say, it can be a problem with, for example, Fermi level. So where substrate can shift these Fermi levels to lower or higher values. And then, of course, calculation of Q is not the same. Don't give you the same results, of course.
okay, so then I would say we thank the speaker again.
Thank you.
Okay, I don't know whether we should still wait for 2 minutes or not. Okay, maybe we can slowly go on. So the next talk will be given by Maria Gastiasoro from ISC CNR La Sapienza, University La Sapienza in Rome in Italy. And it's about superconductivity mediated by soft ferroelectric modes. Please.
Hello, everyone. Can you hear me? Should I get started? Yes. So first of all, I'd like to thank the organizers for giving me the opportunity to discuss our work, which was it's essentially in these two papers here. It was work done in Sapienza, and this talk has nothing about topology. It's going to have some spin orbit, but I'm sort of a little bit shifted in this session. So let's hope that everyone learns something new anyway. So the title of my talk is Superconductivity Mediated by Soft Ferroelectric Modes. So the idea is a little bit like what you would expect from spin fluctuations, but now with ferroelectric fluctuations. So with that, let me get a little bit of motivation. Because there has been lately a lot of experimental evidence that there is some interplay between superconductivity and ferroelectricity, and this is something that is not, usually don't think about it in this way. So this would be the phase diagram of prototype incipient ferroelectric, which is strontium titanate. This is going to be very much motivated by strontium titanate. So you have this superconducting phase close to a ferroelectric phase. And this ferroelectric phase often can be described by this softening of what I'm going to call the soft ferroelectric mode, which is a transverse optical mode, and it's shown here for this perovskite structure. So in the paraelectric phase, it's completely, the paraelectric structure is kept, and then as you get closer and closer to the ferroelectric phase, these atoms, if you want through the transition, freeze, and the system develops a polar axis. So you get this, local dipole, if you want, with the titanium moving against the oxygen cage. That's the easiest way to think about it. Now, experimental fact, as you get the system closer to this ferroelectric phase, once you dope it, because in the ferroelectric phase, if there is no carriers, the system is a ferroelectric. If you dope it, it becomes a polar metal, and now it can also develop superconductivity. So the experimental fact is that this superconducting phase gets enhanced, TC gets enhanced as you get closer. And now the question is why, and can we learn anything from the pairing mechanism? And something that I would also like to point out in these systems is that these carrier densities are extremely low, so that leads to having very, very low Fermi energies. And that puts us outside of the conventional BCS paradigm that usually we like to think of when we think of something like electron phonon mechanism. So that doesn't work. And then what I like to discuss today is the most natural way of thinking about this problem, which is coupling these electrons linearly to this soft ferroelectric mode. And this soft ferroelectric mode is, as I said, is a transverse. So the conventional electron-phonon coupling does not work, because you can think that as the phonon propagates, it's transverse, and then Q is perpendicular to U. So the product is zero. But instead, I'll show you how you can get still to linear order a RASBA-like coupling. And whenever I use this word, I'm thinking about it in a dynamical way, because I'm always going to be outside the polar phase. So this is going to be fluctuations of this mode coupling in a RASBA-like way. And I'll also like to point out that this is not only relevant for bulk materials, but there is lately also a lot of activity going on these KTO heterostructures, this is also an incipient ferroelectric. They grow it in different directions, and it has a much higher TC, and this TC depends strongly on how you grow the substrate. So let me go into the problem. I have to say a little bit about the electronic bands. So these are this is the FT also, bulk TFT, and actually this is also an ab initio, a tight binding model. And I'm going to be using a lot this tight binding model because this minimal model gets a lot of the physics right. And then, so these are T2G orbitals, 3D of titanium with spin orbit coupling. So I have to think about it as a J. And if there was no spin orbit, all these states would be degenerate with 3 times 2 of spin. But spin orbit opens a gap. And then this is cubic, in the cubic structure. And now when you further go down into the tetragonal phase, there is a further split from the tetragonal crystal field. And now I just want you to think about these bands not as T2G, but as T2G plus spin orbit, because as I dope the material, let's say as I fill these bands, I get with a Fermi energy that is definitely comparable to this spin orbit energy scale. So I would say that that's reason to think about this basis, the spin orbit basis, as the more appropriate one. So for example, if I look at this lowest band, this would be the 3½ plus 3½ where I mix I'm going to be calling this X is just the X component of the 3D, so Y, Z, and so on. So the pseudo spin up would be X plus I, Y, and the pseudo spin down would be Y minus I down. So Y down. So this is the band structure, or the non-interacting electronic part, which is T2G plus spin orbit. Now, as I said, this ferroelectric mode is transverse optical phonon. It breaks inversion, so it has odd parity if you want. In the tetragonal phase, it belongs to these 2 reps, and I've mostly been focusing on this one here, which is in plane. And now, because U and Q are perpendicular, I can't have the classical constant coupling. I need to go to next order in linear order to U, and that is, you sit down, you do the symmetry analysis, and you can convince yourself that essentially to linear order, these electrons can couple via this coupling, which is linear in K, and cross sigma, where sigma is the pseudospin of the electron. So how is it that I'm coupling a non-magnetic polar displacement, which is U, to the pseudospin of the electrons? And the answer is I need spin orbit coupling. So let me quickly, in a microscopic sort of intuitive way, show how this, if you want, symmetry allowed or phenomenological coupling comes into play. So this would be Again, I'm showing the T2G orbitals, and now I'm gonna induce the finite polar displacement, which is characterized here by these p orbitals of the oxygens displacing. And now, without this u, so if this u was 0, this hopping would not be allowed. It would be forbidden by symmetry. In place of this, in the presence of this polar displacement, there is this new hopping channel which is allowed. And because of the symmetry of the orbitals involved, these T2G orbitals, this thing is odd. So the hopping to the right and to the left has the opposite sign. So it breaks inversion. So the first step is this interorbital hopping breaks inversion, spatial inversion. Now if I go to the spin orbit coupling band, because this is the T2G band, now I say, okay, let me go to this pseudo-spin up and down band. This hopping is still there, but now the pseudo-spin up experiences it exactly opposite to the pseudo-spin down. So that means that the breaking of inversion is experienced in opposite way. So like left movers and right movers are going to have a different energy, and therefore dynamically you get this kind of shift of your band, which is what people usually think of in terms of RASBA. So it's a RASBA like band splitting, but it's dynamic. In our case, we have a tetragonal point group. That means that this K cross sigma is a little bit more complicated. And when you go to the band basis, you are allowed to have different couplings for the different point groups. But this is allowed by symmetry. What I'm going to do next is like, okay, this is allowed. It's very good. I can also see that it could happen through these processes. Now, how large is this coupling? And that's what I'm going to do now. I'm going to use ab initio frozen phonon to sort of estimate the coupling so I'll show it for STO, but we basically build a formalism where you can estimate it for any material in a quite straightforward, cheap way. So as I said, you put this polar displacement, you're expecting to have this shift of pseudo-spin up and pseudo-spin down in this way. That means that, for example, if I go to this band split, I look at the linear component, I should expect first of all to be linear in K, so this is the RASPA-like, and then the slope is essentially going to be proportional, or I'm going to extract from the slope this coupling strength. So that's what I do. I put, well, not me, I worked with some ab initio people who did frozen phonon calculations in the bulk at Q equals 0, and then you see how these electronic band structures are modified, and I just take the split, I plot it in the same way. I extract the linear component, and sure enough, I do see that this split for all the 3 bands of strontium titanate are linearly split. So I extract, for example, in this case, from these 2 slopes, I get tau of A and tau of B. And then once I have those, this split maybe it's not very useful sometimes. So what we had to do was to go from the classical displacement to the second quantization, go into boson language or to phonon creation and annihilation operators, and then you can derive the electron phonon coupling, which has a characteristic bare coupling in the vertex, which is now depending on momentum, which is in that linear momentum, which is unconventional, but then it has also a strength which is proportional to this tau. And just to give you some numbers, what we find from this ab initio is that the coupling, this RASPA-like coupling, which naively in the community was believed to be very small, it's actually quite strong and significant. And we also find that these different labels here are just the eigenvector that is extracted from different experiments. So it's not exactly clear how exactly these atomic displacements happen inside the mode. But in all the cases, we tried like 3 or 4 cases. It's sure it depends a lot on this, but it's certainly a significant coupling. So now that I have a significant coupling, the fun part comes, which is like, okay, what about pairing? I'm going to couple the electrons in this way. It's certainly an unconventional way. And what kind of superconducting state should I expect? So as a side from SEO, just from a purely theoretical playground model, I can solve the pairing problem by projecting this effective electron-electron interaction into the Cooper channel, and I can look at the different channels, pairing channels. Usually from electron phonon, you would stop at S wave or A1G, the conventional trivial state. Something cute or unconventional about this mechanism is that even if you look at S wave, so you go to S wave, sure, it's attractive, is the leading instability, but P wave and D wave, so odd parity channels and higher order non-trivial Ls of the even parity channels are also attractive. And this is because of the momentum structure of these fluctuations. It has odd parity, and that's why it gives me this. And then it's also highly momentum dependent, and that's why I get an attraction here. Okay, so it's different from spin fluctuations, where you would have to go to different Qs and so on. This one gets it straight away. Now, going back to, I have a substantial coupling in STO. That one is an S wave as far as we know, so I'm going to focus on what I would get in STO. So I got my G, and then naively, the strength of the coupling is density of states G squared, where G is the coupling that I just estimated on this, and then you have the frequency of the mode you're looking at. And then, just before putting any numbers, density of states parabolic band goes with Kf. G squared, I just told you that G is linear in K, so this is K to the cube. This looks like I would get room temperature like this, and the answer is no, there is something else, and it's that if I look at G a little bit more carefully as a function of momentum, because now I'm going to imagine that I'm filling up my bands, then sure, at low energies, low momentum, this coupling G, so whenever this is a frozen phonon DFT, so this is giving me the split, but this split is proportional to G, so this is linear in K, but it does not grow up, to the infinity linearly, so it's not conventional RASBA-like. What Ab initio finds is that eventually this thing peaks, and then it decays in a form very close to 1 over K. So then we're like, wait a moment, because if this is like this automatically gives me a dome in G, which will give me a dome in lambda, and then a dome in TC. So we wanted to understand a little bit better this. So in order to do that, we use this minimal model that I just described with the T to G electrons. And a lot of expectation. Yes, there you go. And it works. It works extremely well. So this is a minimal T2G model. I just put the non-interacting electronic model I discussed before, and this one parameter with this induced hopping channel. And many of the details are not covered, but the one that I'm interested, which is RASBA peak and 1 over K, or linear and K peak 1 over K, is definitely there. And then I have a minimal model, and then I can understand the physics, because now I can do perturbation, and I can play around with this model. And what we find is that what sets this behavior is a competition between two energies, the spin orbit energy, which is strongest here, and some hopping term, which switches on at finite momentum. So you do perturbation, and sure enough, you do recover that when the spin orbit dominates, you have this usual K linear pseudo like RASBA, conventional RASBA behavior, but when the kinetic energy takes over the spin orbit, then you get this 1 over K, and this spin orbit assisted coupling is no longer, can no longer keep up, essentially, with kinetic energy. In a slightly different way of saying the same thing would be that you have momentum-dependent quenching of angular momentum, because when the spin orbit is the one who sets the states, then your states would be, x plus iy, which have this angular momentum, and then as k gets larger and the kinetic energy says, no, wait a minute, I want a different eigenstate, then, this interaction slowly dies out as 1/k. And that automatically gives me a scale for this problem to sort of have an idea of where this peak would happen. And in this case, is given by these two parameters, which for STO, I could fit from ab initio, and then it's around this number. That means that when I take this G, which goes as RASBA, and then 1/k into this expression, assuming a simple parabolic band, automatically, unsurprisingly, I do get a peak in lambda, okay, which is shown here. Just look at the full lines. Then that means that when I take the BCS expression for TC, now I can convert Fermi momentum to density, the usual textbook, and then I get a peak in TC as well. So this would be the blue curve from this very simple, estimation of what kind of superconducting state you would get that I got from a tandem between this minimal model and ab initio frozen phonon. And the red dots are here, shown here are experimental bulk probe TC. So I would say that the mass in density is pretty good. The magnitude that I would need for lambda is pretty good, and one even gets this kind of asymmetry in T with in carrier density. So I would say this kind of RASBA-like coupling is a leading pair mechanism in STO. And then the last slide, I'd like to just quickly, I have 2 minutes, so I'd like just to quickly say that sort of discuss some more recent work that I've been doing also now with Giulia Venditti, who is shown here. This was on Sunday while she was preparing her talk. So if you have more questions about this, you can also go find her. She's around. So as I said, there is another system where this mechanism may be very relevant, and this is these KTO heterostructures. So now we did essentially, we went through the same formalism that we had developed for STO, and we, now I guess the important thing for KTO is because tantalum is a heavier atom, then the spin orbit is about 14 times bigger. So sure enough, the spin orbit is 400 instead of 28. And then you plot this frozen phonon, you see what the coupling is. And the coupling is also much bigger. It's shown here, like the scales are much bigger. Again, it has RASBA-like coupling. There is also some deviation. And now, what is very interesting about this material is it's cubic. And that means that the J3 halves is degenerate. So this band here is rather isotropic, so what you would expect from a conventional RASBA is just a circle. But these two, you can see that the slopes are very different in different momentum directions. If I plot it in a different way in a polar plot, you see that this RASBA coupling is extremely anisotropic for this manifold here. And using the same kind of minimal model, we have also understood now why and where this K-linear, very angular, strong anisotropic comes from. And then I just wanted to mention that when you compare the numbers with STO and KTO, not surprisingly, since this spin orbit assisted interaction, this is a spin orbit assisted interaction, and the spin orbit is much larger in this material, it is very strong. So I would say this is a very promising route to look for pairing both in heterostructures and even bulk, which as far as I know, it has not been found. And with this, I just leave the conclusions. So we developed a formalism to study this generalized RASBA, which is a way to couple conduction electron to soft ferroelectric modes. You need spin orbit for this. And then I gave some estimates for STO, playing or working using both this minimal model and DFT, and we found a strong RASBA coupling, and we also found that it naturally has a dome without putting any other parameters or mechanisms into it. And then from a weak coupling analysis, that means that there is a dome in TC and there is a lambda, which is pretty robust which make this mechanism, I would say, one of the leading candidates for bulk superconductivity in steel. And then as an outlook, I just pointed out, KTO-based heterostructures, bulk, etc. And I didn't mention it, but I think there is, all I discussed was to linear order in U, because that's what we usually look at. This is unconventional enough that the linear order is different. And if anyone is interested, the quadratic coupling is also extremely large. We are now starting to understand this term right here, which would be basically this kind of vertex, which usually people never look at. And then it would be very interesting to see what the resulting pairing diagram would give you. And with that, I'll thank you for your attention, and I'll take your questions.
Thank you very much for this nice and clear talk. So I think we have time for one question.
Sorry, I cannot see how to indicate the question. I just can. May I ask?
Where are you? Oh, I see.
Yeah, Sergei Klimin from Antwerp. Sorry?
Go ahead.
Sergei Klimin from Antwerp. Could we look a bit for the slide with the comparison with experiment for strontium titanate for your model?
Yes, the one with TC, right, versus N?
Yes. Maybe I missed something. Do you have any fitting parameter for this good agreement?
No, so that's my point. Like I just had one parameter. So I first feed the non-interacting electrons to the FT. That's spin orbit and hopping integrals, which are 4. And then I just have one parameter, which is this induced hopping channel that is there one because of the coupling to this phonon. And the only way that enters is through this T prime, if you want, the TDU, and that the TDU I literally extract from DFT. So I place such a phonon, frozen phonon, I see the slope, and then that gives me some MeVs per angstrom, whatever that number is. I put the number in, and then, that's it.
Okay. Okay.
And then that
Thank
gives
you.
me a lambda. Of course, that gives me a lambda, right? Lambda BCS. And then I'm plotting the corresponding, how the TC versus TC max would look like as a function of n. And it's extremely simple because I'm assuming a parabolic band, so it would be, basically I'm saying that the lowest band has the highest contribution, and I'm neglecting any multi-band physics and so on. So I was also quite, surprised.
Okay, thank you. Because it looks a bit confusing because, as you know, there are several mechanisms, and for example, Fröhlich interaction cannot be neglected, as it always exists in strontium titanate, and this soft mode is a kind of transverse optical mode.
Yes.
In fact,
and
it is necessarily accompanied by the corresponding NO mode. It always must be present, and together with other mode, and contribute to the dielectric function.
Yes.
And if we combine both those mechanisms, I think other mechanisms must contribute too.
So what I would say is I'm going to answer with actually experimental evidence, which I think is
okay. Okay, thank you.
So with experiments, what experiments show is that taking this superconducting phase closer or larger, and you can do that in different ways, TC is very much affected. And now you look at how the longitudinal mode or the Fröhlich interaction you're referring to is changed by these very small pressures and different ways, and that doesn't move. It doesn't do anything. It doesn't care. It's very, very low energy scales. So if the leading mechanism was that interaction why is TC, having such a big effect?
Mm-hmm.
That was why I think it's, I started from, let me directly couple to this mode, because it's this mode that when I'm doing these small changes is changing a lot, and that's where I'm seeing how TC is changing a lot. And by a lot, I mean like 50% up TC and stuff like that.
Okay,
So that's a
thank
bit
you.
the reasoning. But
Thank you. I think, sorry to interrupt, but I think we have to go on. Sorry, maybe you can ask your questions during the coffee break, and
Yes.
let's thank her and also all the other speakers of this session again. Thank you.
thank you.
about noise spectroscopy on Yushi-Barusinov states on iodium diselenite. Please.
Yeah, so thanks very much. Hopefully you can see my slides and me, and also hear me. If the sound is a bit off, that's because COVID is trying to destroy my body, so apologies for that. But I would like to take the opportunity to talk about a recent work which was using shot noise measurements at the atomic scale to uncover the tunneling process into in-gap states in superconductors. More generally, I would like to address two limitations, let's say, of the STM technique that we used, so scanning tunneling microscopy, which is that usually STM is considered as a technique that only works at low frequencies, so typically below 100 kilohertz. And secondly, if you have a normal metallic tip, that the energy resolution is limited by the temperature because you have 3.5 kBT. And so if you want to resolve very fine features, then this is normally possible. And hopefully at the end of the talk, I'll have convinced you that by implementing relatively simple cryogenic circuitry, it's possible to circumvent the first limitation. And secondly, by using this circuitry, we can, sorry, I can hear myself back again. Can someone maybe turn off a microphone somewhere? Secondly, so when we use the circuitry, it allows us to measure shot noise, and in doing so, we can beat the energy resolution by a factor of 200, as I'll show you in these in-gap states in superconductors. Now, the problem of being stuck at low frequency is that if you want to look at dynamics of electrons, so correlations between electrons, or for instance, the tunneling process by the individual electrons and how they interact with one another, you need to go to higher frequencies. And so you won't be able to do this with a standard STM. And the reason for this, so essentially what you would like to do is to register the arrival of each individual electron, and then look for correlations between these electrons. But if you were to do this for a current of 10 picoamp, you would need to register single electrons arriving with a frequency of tens of gigahertz, and this is a bit too much. However, what you can do is look for shot noise. So basically the fluctuations in the current around the average current that you set. And the reason that there are fluctuations in the first place is that of all the electrons arriving at the tip sample barrier, so the vacuum between the tip and the sample, most of them are reflected back, and only very few cross the barrier. And so because of this, you have to consider the statistics of low probability. And if your electrons that cross the barrier are independent from one another, they don't correlate, then these statistics will tell you that you have random tunneling, which gives you a Poissonian distribution around the average current. And the noise power contained in this Poissonian distribution is then given by this formula. So the S is the noise power, which is 2 times the charge of whatever is tunneling, times the average current, then a cotangent term, which depends on the voltage and the temperature, which is only relevant for very low voltages or for very high temperatures. And then the F, which is the Fano factor, and this essentially encodes, this depends directly on the tunneling probability, let's say. And so here you can see F is typically given by the transmission probability divided by the sum of the transmission probabilities. Now, in a tunneling experiment, this transmission probability is very small, and so F is typically 1 if you have uncorrelated electrons. And so this allows you to, if you are able to measure this current noise, it allows you to directly access the charge of the carriers. It allows you directly to look at the temperature of these tunneling electrons or carriers. Plus, it can also give you an insight into the interactions between electrons. And as I said, this F is given by this formula if you have electrons that are not interacting. However, if they do start interacting, for instance, if you have positive correlations, then the noise will be enhanced, which means this F will become bigger than 1. Or if you have negative interactions, so the tunneling process is anti-correlated, then the noise will become smaller than 1. And so this technique has, for this reason, been used in detail in mesoscopic systems. However, at the atomic scale, it has been very tricky to do this. And the reason is that if you would like to do these kind of measurements, the noise itself is very small. And the problem is, if you want to measure it, you need to get away from all the other sources of noise. And the main problem in an STM at low frequency is 1 over F noise. So this brings us back to the initial question, why are we stuck at low frequency? And the STM junction itself is not the issue. So the junction can be modeled by a resistance, and then in parallel, the capacitance between the tip and the sample. Now, this capacitance is typically much less than 1 femtofarad. So if you take a junction resistance of 10 mega ohm, your bandwidth is at least 10 megahertz. So much bigger than this 100 kilohertz, which is typically the limiting frequency. Now, the problem comes with the implementation of this junction in the circuit, in the measurement circuitry, which gives you additional capacitances from cables and stray capacitances. So here's a typical implementation. So you have a voltage bias in the junction, and then all the cables going to room temperature. And at room temperature, you have the room temperature amplifier that converts your current into voltage. Now, if you would like to do the IDV measurements, then this stray capacitance of the cable, this cable capacitance, which is typically 100 picofarads for a meter of cable, will already cut your signal in half if you take a typical low frequency amplifier. More problematic is if you would like to measure noise, then your noise is essentially given by an extra noise source of the junction. And so for a typical current of 30 picoamps, then the current noise, so the shot noise, is 10 to the minus 31 amp squared per hertz. Now, unfortunately, the input of the room temperature amplifier has some voltage noise. This voltage noise is then converted by the cable capacitance into current noise. And if you work out the numbers, then this current noise from the room temperature amplifier is orders of magnitude larger than the shot noise you're trying to measure. And so in this standard geometry, this is impossible. Now, an elegant solution was come up with by Marco Aprile, who was inspired from mesoscopic physics, which was more his field. And he essentially came up with this idea where in parallel to the cable capacitance, you place an inductance at low temperature, and then add a low temperature amplifier. And so what this does is the LC combination essentially gives you a very high impedance at a specific frequency, which you can pick by choosing the inductance. And so we picked a frequency around 1 megahertz. And then this very high impedance, in our case, something like 200 kilo ohm, converts all the current noise from your junction into voltage noise at the input of the low temperature amplifier. And then if we use the same numbers again, so for 30 picoamp, then this means that we have a voltage noise from the current noise of something like 1 nanovolt per square root of hertz, whereas the amplifier itself has a noise that's smaller than this. So this is already very good. And then the circuit itself has some thermal noise, which is on the same order of magnitude. So in principle, with this circuitry, it's possible now to do measurements of the noise, even down to small currents like 30 picoamp. The measurements themselves, once you've implemented this, so I built my own system and implemented this idea for Marco when I came to the Laboratoire de Physique de Solide. The measurements themselves are relatively straightforward. So you just take a standard IV measurement. So here's the current and here's the voltage. And then while you're changing the voltage and you're changing the current, you're also changing the noise, of course. So if you measure the noise simultaneously, so for each current, you measure this full curve or you just measure the maximum, you can then plot the noise versus the current or versus the voltage and get a figure something like this. And so what you see is that for each voltage, the noise will change because the current changes. And then you can make a nice fit. So this noise that you measure is essentially the sum of the thermal noise, of some background noise, and of the shot noise that you're interested in, which are all converted by the impedance of your LC resonance. And then by making a very simple fit, you can directly extract the charge, which in this case is E, because you're measuring a platinum, which is a simple metal. And the Fano factor is 1. Plus, you get a bonus, you get the temperature, which is this rounding here, which in our case is 4.2 Kelvin. Now, before continuing, I would like to address one point, which is that because we convert the noise by this impedance, if you go to very low junction resistances, then some of the noise will go back through the junction. And so you reduce the noise if you go closer and closer to the surface. Now, this you can easily take into account by just adding a voltage dividing term into the full fitting equation. And then additionally, if you have a non-linear IV, then your noise will no longer be linear in the voltage. It will still be linear in the current. So here you see an example. So this is clean niobium diselenide, which is a very non-linear IV characteristic. you can see that if I plot now the noise versus the voltage, this is no longer a nice linear dependence. But again, if we take all of these factors into account, the black line is now again fitting with Fano factor of 1 at a charge of E. And you can see this works very nicely. And if I zoom in well into the bottom, you can see that essentially it tracks the measurements extremely well. Now, a different way to plot this is to extract for each point what the corresponding effective Fano factor would be. So by effective Fano factor, I mean the charge QF divided by E. And so if you have a charge of E and a Fano factor of 1, the effective Fano factor would be 1. And this is exactly what you see in clean niobium diselenide for energies where we have enough signal to noise to do this extraction. Because in the gap, there's no current, so we can't do this extraction. Now, why am I telling you all of this? I'm telling you this because what we were interested in was the intrinsic lifetime of in-gap states in niobium diselenide, or in general in in-gap states. And so as you've probably heard during earlier talks in this conference, if you place a magnetic impurity inside a superconductor, its pair-breaking interaction will generate states inside the gap, as you can see here. And these can be used to quantum engineer novel states of matter. You can try to combine them to make Majorana fermions, etc. One crucial ingredient for this is to have a long lifetime of this state, because if you have a very short lifetime, essentially you cannot store any information in this state because it's immediately destroyed. The lifetime is essentially the width of the state, and unfortunately, this intrinsic width is typically much smaller than the temperature. So you cannot do a simple DIDV measurement and plot the width, because that will just give you the temperature and not the width of this state. To tunnel into this state in the first place with single electrons, what you essentially have to do, because this is a state inside a fully gapped system. So you place your electron in this in-gap state, and then somehow this has to relax to the continuum. And there will be some time scale associated to this relaxation, which is exactly the intrinsic lifetime we're after. Now, because of this relaxation, the noise for this particular process, if you have we have a charge of E, but because you have this relaxation, and so essentially an ordering of the tunneling process, because as long as there's an electron in this state, no additional electrons can go in, the Fano factor will be reduced because you start ordering the tunneling process. And in fact, the more you order this process, so the longer the lifetime of this state, the more this Fano factor will be reduced. And so by measuring the noise, you can directly see or read off what the intrinsic lifetime of such a state is. Now, there's of course a second possibility, which is that you have not the charge transfer of one electron, but you can have Andreev processes which transfer two charges. So an electron goes in and all goes out. In this case, you have a Fano factor of 1, but your charge will be doubled. And so the noise, the total noise will be doubled. And so by measuring the noise, you can, first of all, if you have inelastic relaxation, you can figure out what the lifetime of this state is. And second of all, you can see if you have Andreev reflection or inelastic relaxation, and to what extent these two contribute. Now, to do these kind of studies, we decided to look at niobium diselenide, of which you can see a nice topography here. Now, in the middle of this surface, just below the surface, there's a magnetic impurity, which you can see if you measure the current. So here is the current corresponding to this topograph, where in the middle you see a very nice peak corresponding to this in-gap state. But then because niobium diselenide is a two-dimensional system, these in-gap states have a very large extended tails, which go up to tens of nanometers for some cases. And also interestingly, these tails have an oscillating particle Hall asymmetry. So if you sit, for instance, at the peak at positive energy, this will be a dip at negative energy, and vice versa. You can see a line profile which shows that exactly. And so this is nice for us because it allows us to find different places on the same Yushi-Barusinov wave function, which have opposite particle Hall asymmetry, so we can directly see if our measurements are consistent based on both types of polarities. So here I'm showing two of such examples. So these are measurements done on the same Yushi-Barusinov state, but on different positions. And so you see that the red one has the biggest peak of negative energy, the blue one has the biggest peak of positive energy, and otherwise everything else is the same. So the tip is the same, The measurement parameters, everything is the same. Now, because these states are very nicely isolated from both each other and from the coherence peaks, there's a well-defined range where the current is purely dominated by the in-gap state. And you can see that these currents are something on the order of 30, 40 picoamps, which, as I've shown you, is in principle enough to do these noise measurements. So to stay at the blue curve, what we essentially have to do is to measure the noise, but do this as long as possible in the sense that we need to average for a lot to get the right signal to noise. Because I said in principle it's possible, but we have a large thermal noise background. And so to get the right signal to noise to see changes on the order of 10% in the Fano factor, we need to average for something like 6.5 hours for this particular case. More than that, since it's very position dependent how the spectrum behaves, we need to be at the exact same location. So in this particular measurement, and in all the measurements that we've done, the tip basically stayed at exactly the same XY position during the entire measurement, and the Z drift was very limited as well. And then when you take this measurement, so essentially you take this measurement back and forth, this case for 500 times, then you essentially get 500 or 1,000 current points. If you make a histogram of all these currents, you get a nice Gaussian profile, which you expect if you probe a single parameter. Then we can do the same for the noise, which basically shows the same thing. And then next we plot for each of these, for each voltage, we can plot the noise as function of voltage. And this is what you see here. So the blue points are the measurements, and then again, the black line is a fit using a Fano factor of 1 and a charge of E. And unlike for the clean system, you can see now that there's a deviation from the measurement data. It's not a huge deviation, but it's significant because if I extract for the Fano factor or the effective Fano factor, you'll see that outside the gap, the Fano factor is 1, but then as soon as you go into these range where the current is dominated by the in-gap state, the Fano factor is 10% enhanced for the small peak and 10% reduced for the big peak. Now we can double check that this is actually noise by looking at the current dependence, which has to be linear for shot noise. And we've done this for these 3 different energies, so outside the gap and 2 in-gap locations, and you can see that indeed it's nicely linear and has the slope that it should have. Well, it's basically the same slope that we measured here. Then we can look at the same measurement but with opposite particle Hall symmetry, and we see that the noise also flips symmetry. And so it's robust in the sense that each time we have a small in-gap peak, the noise is enhanced and vice versa. Now, a simple way to understand is that if you have electrons tunneling in or out of this small peak, then for the Andreev process, there are plenty of Hall states available to transfer a charge of 2e. And so the Andreev reflection can have a considerable contribution, and your noise will be enhanced because you have charge transfer of 2. On the other hand, if we have electrons tunneling from this state, there will be much less Hall states available, which means that you have a smaller contribution from Andreev refraction and an enhanced contribution of inelastic relaxation. And that means that the noise will be reduced because you get this ordering process for the inelastic relaxation process. Now, to put this on a more theoretical footing, Pascal Simon and Vivienne Perrin from the LPS calculated the noise based on a relatively simple model from Katharina Franke and Felix van Oppen. And so here I show again the 2 measurements. And then what we can first look at is if we have just pure inelastic relaxation or just pure Andreev refraction. And then you get these curves. So for pure Andreev reflection, you see that the noise is symmetric with respect to 0, and it's always above the Fano factor of 1. Whereas for the pure inelastic relaxation, it's not necessarily symmetric, but it's always smaller than 1. Now, clearly, neither of these works because we have asymmetric noise, which is both bigger and smaller than 1, depending on the polarity. And so we need a mixture of these 2 processes. So this, first of all, directly shows us that we have both inelastic relaxation and Andreev reflection. But more than that, the only parameter that goes into this calculation that is not taken from experiment is the intrinsic lifetime. And so by plotting, or by calculating the noise using different intrinsic lifetimes, we can now directly figure out what this intrinsic lifetime is. And so here you see 3 different intrinsic lifetimes, so 0.1 microelectron V, 1 microelectron V, and 10 microelectron V. And you see that the one of 1 microelectron V, so that's the green curve, fits very well for both of these different measurements. And this corresponds to a lifetime of on the order of 1 nanosecond. Now, I'd like to remind you that the temperature of this measurement is, the effective temperature is something like 600 millikelvin, which corresponds to a thermal resolution of 200 microelectron V. So that's a factor of 200 bigger than the intrinsic lifetime. And so by doing these noise measurements, we can first of all uncover the tunneling process into these states, and second of all, beat the temperature broadening by a factor of 200. And so with this, hopefully I've convinced you that by implementing some relatively simple circuitry that you can implement in any STM, you can not only measure at low frequency, but also go to higher frequencies, and you can set this frequency at any value you want by just changing the inductance. And then by using this, you can do shot noise measurements or any other source, any other noise measurements. And for example, beat the temperature by a factor of 200. And so I would like to thank my collaborators from the Laboratoire de Physique de Solide and samples from Laurent Carriot. I would like to mention that we do have a postdoc position available, so if you're interested, please send me an email. And with that, I'd like to thank you for your attention.
Yeah, thank you very much, Freek, for this very nice, interesting talk. So we have time for questions. Okay, maybe I can start. So you have shown that you have an energy resolution of 200 microelectron volts. I mean, I'm wondering whether in your noise spectroscopy you couldn't have some kind of overlapping between different ranges in your bias voltage, which then somehow mess up your conclusions about this Fano factor. For example, if you measure on a YSR state, could you leak some signal from the coherence peaks into the YSR state by your energy resolution, or is that not possible?
Well, I mean, the energy separation between the coherence peak and the in-gap state is much bigger than the thermal broadening. So in that sense, we have especially, for instance, here at the dip, there's no mixing of anything. So here, the current is purely dominated by the in-gap state. Moreover than that, because here we have a low DI/dV, it also means that our circuit is actually not affecting any of the measurements. So I would say that within this range, which is indicated by dashed lines, but specifically at this minimum, the noise data is very reliable. And in fact, that's where all the action happens. So I don't think this plays any role.
Okay, but what is then so if you imagine you would have, I don't know, some other peaks which are more close by. So what is then your energy resolution, how you can separate these different tunneling processes by a noise spectroscopy? So if you would
if you wouldn't have a nice clear separation like this, but you have overlapping things, then of course you start mixing signals. So if you also include contributions from the coherence peak, then of course you will have an enhanced contribution of single electron processes, which will basically give you a noise that becomes closer and closer to 1, a Fano factor of 1. And so yes, you have to be lucky in a sense to get a range where you do not have this. If you do have it, then you will less likely see a clear-cut signature, for instance, of Andreev reflection.
Okay, thank you very much. Are there other questions from the audience? Or maybe from online visitors? Okay, that seems not to be the case. So then let's thank Freek again for his talk. And Okay, so maybe I can already start introducing the, or is everything okay with the technique? Everything's okay. So I can already introduce the next speaker, which is Shavoljeno Ketselibike from University of Jyväskylä in Finland. And so he's talking about topological superconductivity in van der Waals heterostructures measured with scanning tunneling spectroscopy, I think. So you have to unmute.
Oh, sorry. Sorry. Okay, now I think everything is fine now?
Yes, everything's fine.
Yeah, okay, good. First of all, thank you very much for this invitation and giving me the opportunity to talk about our recent work. So today I'm going to talk about how one can construct topological superconductors using van der Waals heterostructures. And our main characterization tool is the scanning tunneling microscope. So I think topological superconductor is not something new for this audience. I think, basically it's a new type of superconductor, but it has a gap in the bulk, but at the boundary, it has a protected metallic states. And what's important here is that this metallic states is believed to be host Majorana zero modes. And as you know, the Majorana zero modes, one of the main building blocks for topological quantum computing. However, these materials kind of rarely exist in natural occurring materials, but we can construct these materials in artificial way by combining superconductors, magnetism, and spin-orbit coupling to achieve this kind of engineered band structures. So you need 3 different ingredients to achieve these topological superconductors. First is, let's start with simple parabolic band. If you add Rashba spin-orbit coupling or any spin-orbit coupling into your system, what it does is basically lifts the spin degeneracy, except the one point where the Rashba goes to 0. Now, if you add Zeeman terms, magnetic field, the direction is perpendicular to the spin-orbit coupling, you lift the rest of the spin degeneracy and you open a gap. Now, if you add superconductor into the system, it basically duplicates your band and creates this kind of particle symmetry of symmetry band.
Can you hear me?
Now,
I think you are not changing slides somehow. We do not see your slides changing.
I'm changing.
But we do not see. We just see your first slide.
No, I'm sorry. I'm changing my slides. Let me share. No, I'm sharing my slide. Can you see now?
Now we don't see your slides. Now we see your PowerPoint in the normal mode.
Can you? Yeah, no, I am not. Sorry, I can share it again, but I think it was working fine. Sorry. Can you see now?
Yes.
Okay. Sorry. Yeah. So yeah. Okay. So as I said, if you so this 3 ingredient. Yeah, but I see my slide is not changing in the. I don't know why.
Artificial topological superconductor.
Yeah. No. I am not in there. My slide is not changing. I can see it from the list. But why it's not changing? I don't know. My slide is changing here.
Could you maybe disconnect and join again the meeting, maybe?
Sorry, I can share a different way, but I'm not sure that makes things work. Let me try.
Okay, now we see your PowerPoint.
Yep. No, but yeah, but I am not in that. Is this my slide is changing? No. I don't know. Somebody is kicking me out. That.
Can you use the PowerPoint screen? So now we see the slide topological superconductivity.
Can you try to
Yeah,
change
but no.
the slides?
No, I can see my slide is not changing, but I don't know why.
Then maybe you can just use the PowerPoint without presentation mode. Just
Okay,
maximize
let me try. Sorry.
Yeah, now we see your full slide topological superconductivity in 2D, but maybe, yeah.
But can
Now somehow your image is frozen and we do not hear you. Can you hear us? Maybe you have low connectivity. Okay, now you're back. We can see you again. You could, so you can show it like that, or you can try leave the meeting and reconnect. But maybe you can also just go on like that. We see your full slide.
I'm reconnecting and coming back.
Okay, now we see your first slide in the PowerPoint.
Okay, if I move to second slide, what do you see?
We just
That's
we don't see the presentation mode, but maybe it's fine.
See any? But I don't know.
What happens if you if you just switch to
I
the
don't
second
see
slide in the normal PowerPoint mode without presentation? Maybe it works.
Oh. But now I'm in the second slide, but I don't see any change in here.
We also don't see any change.
Okay. This is. No, this is weird.
Hello.
Okay, it's
Can
not
you hear me?
responding, but I think the next speaker can go, but this one I don't know what is the problem here.
Can you hear me? Hello.
Yes.
Please stop sharing now.
Sorry?
Please stop sharing your screen now.
Okay.
And then start your presentation on your computer.
Yeah, but without seeing screen, how do you know what I'm talking?
Is your presentation started? On full screen.
I don't understand what you...
You are sharing
Yeah.
your PowerPoint screen. You had to share the screen which your slides in on full screen.
But yeah, okay.
Yes, now it's the right screen.
But okay, now it's changing. Yeah, now
yes.
I can see. Sorry, I don't know. No, it just started and then stopped. No. No, it's not. I mean, it's not moving the PowerPoint slide. I can see it on the big screen. But it's definitely moving in my screen, but I don't know.
You should click on the
Yes,
slide.
I'm doing. I mean, it's changing in my screen, but not in the big screen.
You are changing the wrong screen.
So the slide is changing now or not?
No, it's not changing now.
Yeah.
You have to click on the big screen.
Yes, I'm doing that. Yes.
Now, could you use your arrow keys?
Okay. Yes, I am doing that. Yes, I am clicking the big screen.
Okay, maybe we can try. Could you unplug your second screen?
Okay, I will share my second screen then. Yeah, but
and this is the presentation view. Please switch it. There's a button on the top. Switch screens. Yes, that one.
Okay, so maybe we can try later on with your talk.
Okay. Okay.
And we move on first with Pascal Simon's talk, and try later with Shavolino.
Okay, thanks. Yeah,
talk.
thanks.
Okay, so is Pascal Simon set up?
Pascal Simon is around.
Okay. All right, so we can see you.
Good. Let's see whether I'm more lucky. So let me share my screen, at least try.
Okay, we see PowerPoint.
Let me move full screen.
Yes.
Is it okay?
Yeah. Can you maybe switch slide once? Okay.
Is that good?
It works. So then let me introduce you. So the next speaker is Pascal Simon from Université Paris-Saclay in France, and he will be talking about shot noise in superconducting subgap bound states.
Thank you for the kind introductions. I hope things will work okay. So I will go on and try to provide some theory to the recent experiments that you just heard about by Frick Massé, a colleague of mine. So, I mean, in order to motivate that talk, I mean, you may worry about why studying magnetic impurity in superconductors. It's a priori a whole problem, solved one. I mean, typically what I have in mind, let's consider iron, cobalt, manganese atom inside a S-wave superconductor. So what do we know about it? I mean, this problem has been solved a long time ago in the 60s, and we expect bound states. And it turns out that, well, this problem is well known and solved, but it regained some interest. Essentially, it was motivated by the perspective of Majorana bound states using chains of magnetic adatoms on top of the superconductors. So there was a series of experiments by the Princeton group, Berlin, Basel, and more recent one by the Hamburg groups, where they consider iron chains or wires on top of a superconductor, and at the extremities of the chain, some Majorana bound states or evidence or signature of Majorana bound states as zero bias peaks were shown. So obviously this raised a lot of interest in the community, and this pushed us to maybe have a better understanding of already the basic cornerstone of this proposal, the single impurity. So this is the outline of my talk. I will try to convince you that, follow up the talk by Frick Massé, that we can get some insights about transport properties inside these Shiba bound states. And in the last few slides, I will show you that actually this short noise tomography can be an interesting signature to look for Majorana bound states. So let's start with the short noise tomography. So as I said, the system of interest is a single magnetic impurity inside a superconductor. So without the impurity, well, this is the typical spectral feature with a nice gap. When we add a magnetic impurity, which is exchange coupled to the substrate, so here basically I will model the impurity as a classical magnetic field and eventually some non-magnetic scattering. This gives rise to these bond states, which are generically asymmetric inside the gap, this green arrow here. The position of these Shiba bond states as a function of J, the magnetic coupling, and the non-magnetic one. Well, if you consider, for example, a 2D van der Waals magnetic superconductor, like now BMD selenites, which contains a small number of magnetic impurities, iron, chrome, and manganese, this is typically what you will show. So it turns out that these magnetic bond states have a very large extent, about 20 nanometers, and indeed, in the spectra, you see these small peaks here around zero energy. There are more in the past 5-6 years. There have been much more evidences, and of the long-range extents of these magnetic bond states. You just show, Frick just presented these bond states with very high resolutions. There were some others in the Hamburg group in lanthanum 001 and also in the Katharina's Frankel group. So as you see, I mean, in these 2D superconductors, bond states have very large extents and with very good energy resolution of them. So we can get a very good understanding of the real space form of these U-Shiba Rusinov states, their anisotropy, eventually the decay and all the oscillating part, which can be understood by the anisotropy of the Fermi surface. So recently we have developed a magnetical approach, which enabled to get a hand on the shape and all that features. But today I would like to focus better on the transport properties. Typically, when you want to probe such bond states, most experiments consider superconducting tip, which has a high resolution in energy, and try to inject electrons. So there are two processes which are typically involved, either inelastic process where you send electrons, it go into the bond states and move away. So, or you also have elastic process in which you inject an electron, for example, in the electronic part of the bond states, and your Andreev reflected, get it all back, and you transfer a charge 2e into the substrate. This is typically, these two processes have been evidenced in recently in this paper in the group of Katharina Frankel, where when the tip is far away from the atoms, well, we are mainly dominated by the inelastic processes. Why? If you bring your tip much, much closer, you see that actually Andreev processes start to pop in, and you have a different scaling behavior of the conductance as a function of the normal conductance. Okay, with our experimental colleague, Frick Massey and Marco Aprilli, well, we try to better understand if we can get more insight from the current noise. So current noise, well, you still have your STM tip, but what you want to measure is actually the current correlation functions at very low frequency. And therefore, you will have access to some kind of atomically resolved final factor, which is the ratio between the noise divided by the current. So Frick already told you about that. Again, the idea is to have to discriminate between all these processes, elastic processes and inelastic processes. For elastic processes like Andreev 1, like where you inject an electron and get it all back, you expect a final factor equal 1, but a charge transfer 2e, as I mentioned. So therefore, an effective final factor, which is the ratio between the short noise divided by 2e, to be equal to 2. On the other hand, when you have inelastic processes, which is Poissonian or below Poissonian, you are blocked somewhere, so you expect a final factor to be less than 1. So when both processes are taken into account, you do expect a final factor between, well, I don't know, less than 1 and 2. So let's see what we get. So this is the experimental data that Frick mentioned. Top of it, you have the DIDV. You see two the Shiba peaks, and right below, this is the effective final factor. When the peak is small, you typically have a final factor which is much larger than 1, between around 1.2. However, for the largest peak, you get a final factor which is less than 1. Is it an artifact? In fact, not. For example, for this, if you move away your tip still in the Shiba bond state wave functions, here you have a large peak in the Hall sector and small peak in the electronic sector. And this gives rise to an effective final factor less than 1, where you have the large peak, and a final factor more than 1, where you have a small peak. And it turns out that this behavior is quite generic. And here you can use the fact that the Shiba bond states have a long extent. And because the electronic and all part oscillate when you move along when you explore the whole extent of these bond states, you can require many data at atomic resolutions. And this is typically what is shown here. The rule of the thumb, a large peak in the DIDV will give you a final factor less than 1. So this is what is shown here in red. So, however, a small peak in the DIDV will give you a large final factor above than 1. And you have a systematic such behavior that you can collect here. Okay, so I'm a theorist. Okay, how can I understand that? So we made a few theoretical basic assumptions. First, we will assume that the data are taken away from the core of the magnetic impurity. So we will only retain the bond state contributions to the transport observable, so rail inside the gap. I will neglect any invasive effect between tip and bonds and the impurity. And I expect, well, this feature to be enough, relevant enough to describe the experiments. So what about the model? We consider a very simple model, a classical magnetic field, and eventually some scalar potential. These give you two parameters, two-dimensional parameters. So we are left with a total of 4 parameters, basically. The energy of the Shiba bond states is 0 here. And this parameter U and V, which can be related to the electronic and all part of the wave functions, which are also related to the magnetic and non-magnetic part of the interactions. And temperature is obviously relevant. And the 4th parameter is, I call it lambda, or tau, which is the inverse of lambda, which is the intrinsic lifetime of the Shiba bond states. It turns out that, well, within this simple resonant model, we can calculate both the current and the noise. And more than that, okay, the expression look ugly and lengthy. However, we can really look at term by term. The first line that I'm showing here with this green arrow corresponds to the Andreev-like contributions, which is particularly symmetric. The next 2 lines corresponds to quasi-particle contribution, which is inelastic. These are my 2 main channels, and finally the last 2 lines correspond to thermal contributions, which goes to 0 when temperature moves to 0. And we can have some specific diagram to each of these terms. If I will make a few assumptions, let's this expression simplify when the position of the bond states is larger than KBT, which is larger than gamma, which is the tip hybridization scale. And basically from this expression, we can extract all parameters but 1. The position of the peak is given by the experiments. The temperature, which is around 700 milliK, is given by the experiments. And this gamma, so the hybridizations, and it can be extracted from the normal conductance. And using the anisotropy between the electron and all peaks, we can extract the U squared and the V squared. So basically, we are left for a given impurity with only a single parameter, lambda, which we can extract. And as Foto showed you, we use this intrinsic Shiba bond state lifetime as a fit. And it works just quite pretty well, the data, assuming intrinsic lifetime of the order 1 nanosecond, which corresponds to an energy scale of 1 micro EV. Well, in short, we have a pretty good understanding of the experimental data using this simple model. And this predicts, therefore, lifetime, which is pretty short, around 1 of the order of 1 nanosecond at 700 milli-K. So in the next few minutes, I would like to push this idea a bit forward and to see whether we can use this short noise tomography as a signature of Majorana bound states. I don't need to introduce further the Majorana bound states. I mean, it was already mentioned in a few talks, especially yesterday. On the theory part, I mean, sorry. I would like to, mention that in the earlier theory paper, people look at the current and the noise in a 2-lead device with Majorana bound states. What is the prediction concerning current? If you try to form this Majorana bound state, you do expect a perfect zero bias peak, so at conductance 2 square H, but also you do expect a Fano factor equal to 1. Why is it so? A Majorana bound state is characterized by a perfect electron-hole symmetry. Therefore, you're perfectly all Andreev reflected. You send an electron, you get a hole back, polarity 1. So, therefore, if we are probing these Majorana wave functions, we do expect a perfect Fano factors, whatever the position of the tip, providing it probes the bound states. So we have considered several situations in order to discriminate Majorana bound state from fake Majoranas, which could be, for example, a Shiba bound state at 0 energy, an Andreev bound state at 0 energy, or a quasi-Majorana. So in all the situations that we will be considering so far, they will be characterized in the conductance by 0 bias peak. So I want to see whether noise is able to discriminate, to sort the 0 bias peaks. So I will make a few assumptions. I will assume that I'm considering a voltage less than the effective gap and larger than temperature. And typically, I will assume that hybridizations is larger than the intrinsic lifetime. So what we found in the limit where the EV of voltage is larger than hybridizations is that the Fano factor, which is spatially dependent now, its atomic resolutions, can be expressed in a very simple manner. It's 1 plus a term which is just the local BCS charge, and or in other words, the particle-Hall asymmetry. And it exactly cancels for Majorana bound state. So we do expect the Fano factor to be 1, whatever the position for the Majorana bound states. So we probe that. I mean, we can there will be correction at larger, but which are small. So we probe that, and this is about in different situations. So this slide is a bit complicated, but it summarizes the key results. As I say, in all the situations I'm considering, they are all which the Majorana in red and the other bound states are in blue. They are all characterized by 0 bias peak. What is depicted here is the noise. So for the Majorana in red, when you move your tip away from the core of the Majorana bound states, you find a Fano factor which is 1, whatever the position. However, if you compare to U-Shiba Rusinov bound states, still at 0 energy, you found oscillations of your Fano factor between 1 and 2. We did the same for Andreev bound states. The Majorana is 1, and Andreev bound states show oscillation again far away. And these oscillations are due to the fact that when you move away, when you probe far away from the Andreev bound state, you do see particle-Hall oscillations, which are intrinsic to the Fermi sea. The situation of what we call a quasi-Majorana bound states, which may occur when you have a normal metal smoothly contacted to a S-wave superconductor, then your bound states have some large extent. You find that your Fano factor for the Majorana is 1 as it should be. However, for this quasi-Majorana from bound states, it's 1 in the normal part and it starts only to oscillate in the superconducting part. Still, it does oscillate.
You have 2 minutes left.
Then
you have 2 minutes.
Yeah, I'm done almost. Perfect. That's my last slide. First, this situation of quasi-Majorana bound state demands fine-tuning, so it's not generic. And although it starts to mimic the situation of Majorana bound states, we do see, if you move away, some oscillations. And my last statement would be, okay, a quasi-Majorana bound state, after all, is a Majorana which is not protected, and something that can be useful. I try to convince you actually that this short noise tomography, which explores the non-locality of the Majorana function, turns out to be a very good tool in order to discriminate Majorana bound state from other fake bound states. And this brings me to my conclusions. So I've shown you the use of short noise for Shiba bound states, and we have a pretty good understanding of the experimental data shown by Frick-Massey. And a theory proposal use Fano factor as a signature of Majorana bound states, and this could be a necessary ingredient, maybe not a foolproof, and could be an interesting tool to develop. And to finish, let me thank my main collaborators, especially Vivien Perrin, PhD student, and Matteo Civelli, and my experimental colleague, Frick-Massey, Marco Aprilli, Doug Pacula, and Alessandra Palacio Morales. Thank you for your attention. Can take a few questions.
Yeah, thank you for this very interesting talk. So, other questions? Not from the audience here. What about from online? There's one question from the audience. No? No. Okay. Well, there seems to be no question. But so then I think we thank the speaker again and go on to the next talk. Okay, so we try to see whether it works with the talk from Shavulieno Kirtsilebike once again, and as I was told, we now try to, well, I was told that we try to proceed like that you show your presentation, but the people here change the slides.
Okay, let me try again. Share my screen. Just for... Can you see the screen?
Now we see your first slide in a presentation mode.
Okay. Okay, now if I move.
We still see the first slide.
Then I don't know.
Okay, so maybe then you would just have to tell us.
Let me one more. I just tried to share only the PPT. Let's see if it works. Then if not, then I already send my slides to there, so we can. Okay, how about now?
Yeah, we can see your presentation mode.
Okay, now if I move. No.
It's still the first slide.
Okay, so I
now
think we
see
just use the slide I sent it to the organizer.
The organizers will change for you.
Okay, good. Thank you.
Okay, then go ahead.
Okay. Okay, so sorry, all this technical trouble. I don't understand what's going on here, but anyway. So yeah, today I'm going to talk about this topological superconductors in van der Waals structures, and we are going to characterize it using scanning tunneling microscope. So I think the topological superconductor is not something second slide. So it's not something new for, sorry, should I continue? Sorry, should I continue?
Just go on. Yeah.
Okay, so yeah, second slide, please. So yeah, not something new for this audience. So basically, it's a new type of superconductor. It has a gap in the bulk, but it has this boundary modes, metallic boundary mode, which is protected by that gap. And interesting, I mean, importantly, this boundary mode hosts so-called Majorana zero modes. It's believed to, at least, and the Majorana zero mode is the main building block for quantum computing. However, in these materials very rarely exist in nature, but we can achieve this material in an artificial way by combining superconductors, magnetism, and spin-orbit coupling to achieve this kind of engineered band structures. Next slide. So there are three main ingredients in topological superconductors to get superconductors. Let's start with simple parabolic band. If you add Rashba spin-orbit coupling, you basically left this spin degeneracy, except the one point where the Rashba goes to 0. Now, if you add Zeeman term into this system, you left that rest of the spin degeneracy and open a gap. Now, if you add superconductors, basically you just get symmetric band due to the particle hole symmetry. And the main important condition in order to enter the topological superconductor is where your chemical potential is. In order to enter the topological superconductor, your chemical potential has to be in the gap, which is defined by this the magnetization gap. So here schematically shown a simple topological, so-called topological phase diagram. In order to enter, we need to be in this red region in here. Next slide. So this has been experimentalized in different systems. In the one-dimensional case, the famous example is this atomic chains, which is self-assembled or atomically perfectly constructed by STM scanning tunneling microscope. And in these systems, the Majorana zero modes should leave at the end of the chain. However, next slide. However, this is not something only limited. Next slide, please. Not something limited by one-dimensional case. It's also been reported in two-dimensional case, where you deposit an island of ferromagnetic islands on superconducting substrate. Then if you look for with STM, you should still see the age states at the age of magnetic islands. The difference here is that in the one-dimensional case, you are tunneling into the single states. In two-dimensional case, you have band of states. So you have many states around circulating around your topological interface. The next slide. So we would like to do it using van der Waals materials. As you know, the van der Waals material, you have many different tuning parameters. For example, the alignment between the layers, or you can also use you can also make simple devices out of it. So here we use niobium diselenite as our superconductor, which is layered superconductor, as we heard from previous talk. And our magnetic materials is here we use the chromium tribromide, and which is newly discovered two-dimensional ferromagnets. And if all the conditions are satisfied, we should expect the boundary modes, and that can be studied using scanning tunneling microscope. Basically, I'm going to focus these two papers we recently published. Next slide, please. So this is how monolayer chromium bromide looks like on niobium diselenite. We use molecular beam epitaxy to grow our sample, and as you can see, this is the STM scanning STM topographic images, and we have here is a zoom in atomic resolution of the monolayer chromium bromide. As you can see, besides the atomic resolution, you can also see some patterns, which is called Moray pattern, and basically it comes from the lattice mismatch between these two different materials. And we also checked it is magnetic properties using a MOC measurement, magnetic optical Kerr microscope. And as you can see very nice hysteresis loop here with different temperatures. And from this, we can get the Curie temperature, which is in the range of 60 Kelvin. And all the experiment we did is done at 300 millikelvin. So this temperature range is it's okay for us. So if you want interested more details about the sample growth and other characteristics, please go to this publication. Next slide, please. So as I said, the most difficult condition to satisfy the to enter the topological phase is where the position of the chemical potential. In the niobium diselenide case, niobium diselenide has a triangular lattice, and the topological phase should appear those high symmetry points, mainly gamma and mk, and where the Reshba goes to 0. So. And you can also see where this high symmetry point is located by calculating the band structures. In this particular experiment, we don't have external gate to control the Fermi level chemical potential of our system. Therefore, what we are looking for is the high symmetry point, which is very close to the Fermi level. So according to the DFT here, for the monolayer case, the high symmetry point is here is M point, which is close to the Fermi level. And however, as you can see, this point is also lower than like 250 millielectrons below the Fermi level. However, what we are using is the bulk materials, and in the bulk case, this M point is a little bit closer, but it is still 50 to 100 millielectron below the Fermi level. So therefore we still need some kind of doping to enter the topological phase. So we can also check experimental whether we have this kind of shift or not by looking at the STS spectroscopy. This STS spectra taken on bare niobium diselenide, and this peak is correspond to the D band of the niobium in the niobium diselenide. As you can see, when we measure the same spectra through the chromium bromide layer, this spectra is shifted. And this shift we can also study systematically across the boundary between chromium bromide and niobium diselenide. And from this, we can get the overall shift is something around 80 millielectron volt. And this is really puts us very close to where we should be. Next slide, please. And here, some low bias spectroscopy. As you can see, this is the bare niobium diselenide superconducting gap you already saw before. Now we can also measure the same spectra on top of the chromium bromide, and here this red spectra is through the chromium bromide. As you can see, these two spectra are similar. However, in the chromium bromide spectra through the chromium bromide, we have extra peaks inside the gap. And in order to see this more clearly, now I can subtract the background spectra from this, and then I get the third data spectra here. Now, as you can see, we have some sort of gap, and this gap for now I call it topological gap, but I have to prove to you this is indeed a topological gap by looking at the age of the sample. If this is the gap is related to topological gap, then when I go from a trivial superconductor to the topological superconductor, and this gap has to be closed, and I should expect some kind of age stays at the boundary of this system. Next slide, please. Now, this is another spectra, another island, and this is in the middle. It's the STS spectra. As you can see, at the age of the sample, we have very strong enhancement of the density of states. And interestingly, this enhanced states lives in this region, the red curve over there, the gap which is defined by the topological. We can also look at how this states varies in space, and this is the map taken at zero bias conductance map. As you can see, this stays really localized only at the age of the sample, and this is a very nice indication. This states probably the topological. This system probably topological system. Next slide, please. In STM, of course, we can measure a different island with different shape and different at different tip conditions, and all the cases we only observe these states for all the islands, and it doesn't matter what kind of shape and orientation of the island we have. Next slide, please. So in order to say something about this is related to topological superconductor, first thing we need to check is this state kind of related to at least superconductivity of the sample. For that, we just remove the superconductivity from the equation or destroy the superconductor by applying external magnetic field. Here we are applying 4 Tesla external magnetic field, and which that kills completely the superconductivity in the niobium diselenide. As soon as we destroy the superconductivity, the states which is at the age it completely disappears. And here the map, and here some line spectra which taken across this island. And this is eliminates some trivial states, trivial electronic state, which is not related to superconductors, and also it's also eliminates so-called Kondo effect, which is the conduction magnetic impurity screened by conduction electrons, and that states should exist even if the superconductivity is gone, or splits under the external magnetic field, depending on what kind of widths the peak has. Next slide, please. So we also did some comparison between theory and experimental results, and this is the results are shown here. I don't want to go to all the details of what the quantitative and the qualitative agreement between the theory and the experiment, but what I want to say is what the experiment doesn't reproduce. Our experimental results, the theory doesn't reproduce. As you can see here, even if you have this kind of straight age of the age, but we still have some sort of modulation on top of the age state that we see. And this modulation exists for all different islands. Next slide, please. And which is shown here. So the one can think of, and in these materials, we have also this Moret pattern. So the main question now is there any relation between this Moret pattern and the modulation of the age states on the system? Next slide, please. So here the very simple schematics of what is a Moret patterns. The Moret pattern basically the interference pattern which rises between two different layers if they have a different lattice mismatch or misaligned respect to each other. And this lattice mismatch or misalignment gives you a new Moret lattice, which is much larger than the original lattice constant you have in the system. And as a result of this, the original electronic band starts to fold, which folds the electric band into a so-called Moret Boolean zone, its own Boolean zone. And this opens this folding the band, and it opens also some small gaps, which is called Moret mini bands, mini gaps. And as a result of that, you create some sort of a periodic potential on top of your material, and this will modify the pristine electronic property of your original material. Next slide, please. Now the question is how this affects how one can apply this into the topological system. So let's look at in the very simple one-dimensional case. So in the one-dimensional case, your topological states appears at this green regions where on top or bottom of your parabolic band. over there you have this helical spin states. That's why you have topological states. But in the middle of there, there's no topologic region. This region is the forbidden, or there's no topological region in between this top and bottom of the band. Now, if you apply some sort of Moore modulation, this modulation can be electrostatic modulation between the two different materials, or exchange coupling modulation. This exchange coupling comes from the superconductor and the magnetic layer on top. So then, if you turn on this, as I said, it folds your band, opens the mini Moore band. And the result is much more clear if you look at the topological phase diagram. Now, when you turn on the Moore, you create new regions, which is not exist without the Moore. That region now hosts the topological state. So this, by creating a Moore into your system, you create new topological regions. That is the kind of regions that's trivial without the Moore. Next slide, please. So now we can simply extend this into the two-dimensional case. Again, this is the triangular lattice, and this is 3 different high symmetry points, which gives you topological superconductors. And in particularly without the Moore pattern now, in particular without the Moore pattern, especially close to the charge neutrality point, you don't have any states, regions that host topological states. But if you turn on the Moore, and I'm simply here zooming into that region, now if you include the Moore, now you create new topological regions that host topological phases. So again, the Moore pattern creates new region that can host topological states, and this is only exists because of the Moore. So next slide, please. How we can detect do you have any modulation or not? So the first thing we can look at is the conduction band of chromium bromide, and here the STM topographic image. This is the tunneling spectra in the large bias. What we are looking at here is the conduction band on chromium bromide. As you can see, this conduction band exactly modulates as a periodicity of the Moore. You can also look at in 2D case here in the different maps, and as you can see, for example, in one bias, the region, one bias map, the dark region turns into bright region. And from this modulation, we can estimate the magnitude of the modulation is around 50 millielectrons.
You have 1 minute left.
Yeah. Okay. So now the question is, next slide, please. Next. One more next. Yeah. So now the question is how this thing related to the is there any correlation between the topological band and this Moore modulation? As you can see here, some maps and interestingly, we have very strong modulation when we cross when you hit the topological band, and this modulation only exists exactly at that band and not outside or inside of the spectrum. And we simulated this simply by modulating the exchange coupling between superconductor, and we see when we hit the band, we have strong localization, where outside or inside we don't have localization. Next slide, please. This is my final slide. As it turns out, this modulation also affects the modulation at the edge. As you can see, when we have inside at the topological band, we have some small modulation inside of the sample, and this modulation exactly matches with the modulation of the Moore when we go when we look at zero bias conductors. And our theoretical calculation also nicely reproduced this result. With that, sorry for all the difficulties, and I hope I convince you that the van der Waals materials are one of the way to engineer topological superconductors, and we have a more parameters to tune and very interesting physics. So thank you. Finally, thank you very much, and I have some positions open if anybody interested in to join the group. Thanks. Sorry for the again. Yes. Any questions I can?
Yeah, thank you very much, Shavolino, and I'm sorry that we had these problems. Thank you for the beautiful talk. So I think it's time for questions. Anybody? Yeah, there's one question there.
Thank you very much. My question about the chemical preparation of this interesting material. Why you prepare this film?
Sorry, your question is why I prepare the film or how I prepare the film?
The question is how the film is prepared, how the structure is prepared.
Okay, so how I prepared the, okay, yeah. As I said, we use MB, molecular beam detection, to grow our chromium bromide, and particularly, so we didn't grow the niobium diselenite, but we can also grow niobium diselenite using MB. So I don't know you are familiar with the MB technique, but it's basically you just spray paint with atoms. Basically, you just provide the metal atoms or the chalcogen or the bromine or whatever the next element is. You evaporate them on top of preheated substrate. The substrate temperature usually matters what kind of final product you get. And the nice thing with van der Waals is you don't limit it in this kind of lattice mismatch. So the van der Waals, if it actually doesn't, I mean, the lattice mismatch is not that important. So they can just grow if it actually. But of course, if it's a real, like the 3D material, not van der Waals material, then the lattice mismatch matters. I hope that answers the question.
Thank you.
Yeah, I also have a question. So you showed that for these edge states, you get a peak usually and not, because in principle, for these one-dimensional edge states, you do not only have particular energy of your Majorana modes, but they are distributed all over the topological gap, right? So what is your explanation why you see a peak and not some?
Yeah, you are right. So it's not necessarily you should observe the peak, and there's some theoretical work. I mean, if you based on theoretical calculation, if this dispersion slope of the dispersion is linear, then you should get constant dose, not the peak. But as you can see, this peak is a little bit broad. It's broad because of you are tunneling into band, not single states. But as you know, we are not measuring dose. We are measuring aldose, basically. So the aldose is not exactly the dose, but it's really depend on what kind of material, I mean, the material properties. And you usually not get exactly linear dispersion. I mean, the aldose can change dramatically if you have not linear, a little bit kink in the dispersion, then you start to get peak. So in that sense, you are right. It's not necessarily you get a peak. You can also get a just constant step. But in this particular system, we mostly get a peak, very broad peak, the sharp peak.
Yeah, thank you. Could it also be that you have some kind of confinement of your Majorana modes in the edge, which lead to confined states and discrete peaks?
Yeah, okay. This is something we didn't check properly. So that means the island size matters. I think the confinement in that sense, what you are saying. So as you can see, we measured our island size is on some of the slides, but this one we didn't check it properly. So just looking at the Majorana with the different sizes, really follow from small to big and try to look at the evolution of the peak. But this we didn't try. But yeah.
Okay, thank you. Is there any other question from the audience or from online visitors? No? Okay, then let's thank Shaul Yeno again. Thank you for your talk.
Okay. Thank you, and sorry for all the technical problems.
No problem. And by this, we end the session. Thank you.
Thanks.
session 3. There is just a technical announcement. Probably you could just switch on the microphone.
Actually, you may see a voting box on your right side, and you need to vote for the first day speakers. After this session, and this is important for the presenters for the first day. Please don't forget it. Okay.
So this session is going to be chaired by Mustafa Akdogan from the Bolo University and me, Alexander Dobrovolsky from the University of Vienna. And it's my great pleasure to invite here the speaker of this half-plenary session, Professor Fomin, who is research professor at the Solid State and Material Science Institute, Leibniz Institute in Dresden, Germany, and is a honorary member of the Academy of Science of Republic of Moldova. Professor Fomin is theorist known for his contributions to various branches of physics, including functional nanostructures for magnetism, optics, semiconductors physics, and superconductivity in 3D nano-architectures belongs to the topics Professor Fomin has been contributing for a good decade. So, for him, stage is yours, and it's my pleasure to introduce your talk now. So.
Thank you, Chair. Good afternoon, ladies and gentlemen. First of all, I would like to thank the organizers of this nice conference, and personally Professor Ali Gencer for inviting me. This work refers to the realm of 3D superconductor nanoarchitectures, and these are two places where I have been working. It's Dresden and Chisinau, it's capital of the Republic of Moldova. Here is the outline, very brief. I will give, in fact, a definition of superconductor nanoarchitectures, and then more specifically will introduce a few of them. In particular, open superconductor nanotubes, recently unveiled topological transitions in curved superconductor nanomembranes with some interesting peculiarities depending on how the transport current is switched on and off. Then superconductor helical coils, and most recent, still ongoing research on topological transitions in modulated transport currents in such nano architectures. At the end, when I have time, I will speak about perspectives. Advanced superconductor nanoarchitectures feature very attractive physical properties like very high magnetic field inhomogeneity, non-trivial topology of superconducting screening currents in them, and complex dynamics of different topological defects. This was a part of my recent book on self-rolled micro and nano architectures, published last year. A kind of overview of this advanced superconductor nanoarchitectures was provided this year in our perspective paper together with Professor Dobrovolsky here. And there are very prominent technological advancements which have made possible in the last 2 decades, in fact, to produce such novel structures. And one of them is self-rolling, which has been mastered by our institute in Dresden and also in many other laboratories in the world. And another one is focused electron or ion beam deposition. And there can be also natural self-organization of such nanoarchitectures. We can recall carbon nanotubes. They are nanoarchitectures which are naturally organized, but now there are very, very many representatives of this class. What is self-rolling? This is here a very short reminder to those of you who are not aware of this approach. Let us take a bilayer of 2 materials with different crystal lattices and put it on a 3rd layer, which is white. This is a sacrificial layer. It's all on a substrate. If you etch off this sacrificial layer from a side of this structure, then these 2 films, which can be a few monolayer thick, are under significant strain because of mismatch of their crystal lattices. And this strain should be somehow realized, and it is realized in deformations. There can be different deformations, but under certain conditions, this deformation is rolling. And it can be 180 degrees rolled part. It can be 260 degrees, a full tube, or it can be many, many rolls which give already a new nanoarchitecture which can be called radial superlattice. What is important here for our presentation? That this is certainly a nanotube, but it is not a complete closed nanotube. It's an open nanotube because this edge, which I show now, is free. And there could be special efforts in order to glue it in a nanotube, but we will speak about such self-rolled nanotubes. Another very nice approach, which was already mentioned today in our session, it's self-organization due to chemical reaction of precursor molecules under focused electron or ion beam and moving this focus in space. We can produce very different geometries. Here it is an example of a helix. If the focus ascribes a helical path in space, then these molecules which are under the effect of this focused ion beam,
recording stopped.
They are forming a nanohelix, for example, but this path can be extremely different, thus producing a great variety of structures. And I already mentioned this rare metal dichalcogenide nanotubes. In the same natural way, one can even form a Möbius ring of niobium triselenide, but this is a little bit outside of my topic. I want simply tell you that there are different well-established experimental approaches who give us nano architectures. Please. Nanoarchitectures in 3D are in fact two-dimensional manifolds like films or stripes, which nevertheless are shaped in a form in 3D. So they are not 3D in fact, but they are developed in 3D. Oh, can you go further? No? Let's wait a little bit. Okay, I still have here a first slide. If we consider such a superconductor nanotube, look, here is a slit, and put it in a magnetic field orthogonal to the axis. The main difference between a planar film and a rolled up nanotube is in the following. In a planar stripe, the screening current, Meissner current, in fact they are small, they cannot expel magnetic field, but Meissner-like currents, they flow along the perimeter. It's a loop which is singly connected, that is, it belongs to the whole structure. But if you rolled up, you have rolled up a nano tube and put it, as I said, in a magnetic field which is orthogonal to the axis. There are two loops of superconducting screening currents developing in the upper, conventionally, and in the lower part of this tube. And they are independent from each other. And they are topologically disconnected. And already at this very early stage, I have shown you even how they are fabricated. We can deduce that they will reveal some topologically non-trivial features of superconductivity, like development of two different loops of superconducting screening currents. And it's clear that this will lead to some at least interesting, unexpected properties of superconductivity. If this is a superconductor under conditions when there are vortices, then in a planar film, the vortices arrange themselves, okay, in a line, if it is narrow, in two chains, if it is wider, or in a kind of abrikosov lattice, if it's wide enough. But this is a unique array. And if you have two, oh, very good. If you have two halves of a tube, you will have two sets of vortices, one in the upper part and another one in the lower part. And their dynamics was in fact the object of our, oh, please, next one. Initial stage of investigation. So we had this, yes, and wow. Okay, thank you. Thank you. I went already a little bit ahead of this slide, but so these are examples of representative three-dimensional nanoarchitectures which were fabricated really. So what I am telling you about, it's a theoretical work, but it has been motivated by these wonderful advancements in fabrication and characterization technologies. This is an example of self-rolled nanotube. At that time it was 2 micrometers radius, but now it's below 1 micrometer in diameter. These are self-rolled helices, which are produced in the same way, but if you use a gamma-like stripe to roll up. And this is one and second examples of direct written nanoarchitectures. Next, please. Yeah. I was telling you that there should develop 2 different loops, 2 sets of screening currents. And one more interesting thing, that it is an open nanotube, and it's possible and technologically feasible to attach contacts to 2 banks of this slit. And it's easier to do than to make this tube full. If you send then current, here it is a DC current, from one bank over this azimuthal path to another bank, then there will develop Magnus force in this system, which will influence the eventual vortices, but here the current is from right to left, and here it is from left to right, because of the fact that this is self-rolled nanoarchitecture. Therefore, the Magnus force will act on vortices in this direction, in the upper part, and in the opposite direction, in the lower part. One more important remark before we go further. These tubes are really very narrow. The thickness of typical niobium rolled up tube in the previous slide is 50 nanometers. And the radius can be 1 micrometer or 2 micrometers. Therefore, they are really very, very thin. Therefore, the vortices we will speak about, they are not like Abrikosov vortices from a textbook, because Abrikosov vortices are long. There are lines with a core. And in this case, I would call them slices of Abrikosov vortices, which have very, very small height. But nevertheless, they have all the topological properties of rotating currents around the core. Next, please. This is a very brief presentation of our theoretical approach. We are using time-dependent Ginzburg-Landau equation supplied with Poisson equation for the scalar potential, with Maxwell equation for the vector potential, if we like to consider renormalization of the magnetic field. And then within link variables approach, in order to take into account gauge invariance, we project this set of equations onto a lattice. It's shown here, in fact, 2 lattices, one lattice for order parameter, another lattice for velocities or vector potential. And in this sense, we would like to emphasize this paper by Valery Vinokur, who established this approach for planar structures. But we are applying it for curved structures. Please, next. This is how the Ginzburg-Landau equation looks like in terms of the link variables, maybe from this slide, without going into details which are available for theorists if you are interested. We have here typical sizes of mesh, 250 by 250 in earlier calculations. Now these numbers are increased up to 1,000, and typical number of iterations to solve this set of equations with appropriate boundary conditions is 100,000 to 1 million. It depends on the system and mainly on its size. So, next slide, please. Yeah. And this is an example of what we obtained. In the right-hand side, we have two vortices in a planar film, and in the left-hand side, we have two vortices in the tube. This is the surface of the tube. Can you push on now? Yes, yes. This is very important. In a planar structure, the vortices move as governed by Magnus force. But I told you that there are two different, please put it once again if possible. Yeah. Vortices move in one direction, in the upper part, in another direction in the lower part. So dynamics of vortices is already highly non-trivial. And this is a correlated motion. When one vortex is nucleated on one edge in the upper half of the tube, another vortex is nucleated in the lower half of the tube in the opposite edge. And then they move like shown here. We investigate certainly their dynamics, and they feel each other because they belong to the same state of a superconductor. They are not independent. But when they are in the central part of this path, I will show it in the next slide, they are slowed down a little bit, and then they are again enhanced in their velocity. And in order to anticipate possible questions which are very, very typical, the dynamics which will be discussed here, it's typical of thin tubes or helices. If the tube becomes thicker, then certainly the vortices become more developed, and they start feeling each other inductively. And when this, would say, opening of a tube is very small, we have already a trend of formation of a Abrikosov vortex through the tube, and certainly then there is no such dynamics. There is only deformation of Abrikosov vortices. But again, this is a case of narrow tubes. Please, next one. Next. Okay. Depending on the magnetic field, we can have regimes with one or less than one vortex, with a chain of vortices, with two chains of vortices. And here are two critical parameters. In terms of time, it's the time of flight from nucleation to denucleation, and delta tau 2 is period of nucleation of a vortex at a certain edge. And depending on the ratio between these two times. We can have sparse vortex regime like here, or dense vortex regime like here. Please, next one. The relation between these two times is a strong function of radius. And here we plot these times as a function of the applied magnetic field. And you can see that when changing the radius, we change this both times very strongly. They are all shifted to the lower magnetic fields when radius is increased. So that the difference between typical magnetic fields of transition between two regimes or simply starting of the motion of vortices, it can be changed in the range of a numerical factor of 7 or even better. So it's not a small effect, it's very, very, very pronounced effect. This, what I was presenting you, refers to the case when the transport current is relatively weak. Already in this regime, we can state that the control of the properties of superconductor in the form of vortices is very significant. But if we increase the transport current towards critical values, we arrive at very interesting and unexpected topological transition that in spite of some arrays of vortices, we will see phase slips like shown here in the bottom part. But this is an announcement. Let us go to the next slide. Yeah. So these are typical pairs of distributions of autoparameter in a planar film above and in an open tube below. No time for this. Next one. Yes. Here, very interesting observation that if we take a planar film, niobium, this is all about niobium. These are typical values of magnetic field, critical when the process starts or transition from one regime to another regime. And let's roll it up. We do nothing. It's physically the same plate of the same material, but one's not rolled up and another rolled up. We see here a shift of this typical characteristic magnetic field by a factor of 3. Isn't it remarkable? It shows that the geometry of a nanotube influences physical properties. It's another tool for control over the physical properties of superconductors. Next one, please. Yeah. Here, how to explain a transition from single chain to two chains. Please put on both, yes. Single chain we discussed, but double chain you will see now. It's magnetic field which is not yet sufficient to embed two chains. And what do the vortices do? They show a bifurcation. They start as a single chain, and then they move into different paths. And these two paths have different typical time as shown here below. So bifurcation allows to accommodate such a number of vortices which cannot be divided by number of vortices in one chain. So this transition is easily realized by bifurcation. Please, next slide. Yeah. This is our system with a little bit more detail. I told you already a single loop when there was no picture, and in a tube there are two disconnected loops in a nanotube. Next one, please. And this is very, very unusual development. Let us try to follow this same transition, but at enhanced currents, when transport current is already of the order of critical, still subcritical, but strong. It occurs that the system does not show this transition via bifurcation in this case, but the transition occurs where formation of a phase slip in a part of a tube which is opposite to the slit. First we obtain all this, and we try to go with more and more to resolution, and we were not practically able to see anything. But then we plotted a phase portrait of this same stage. This is a phase of the order parameter, and it was clear what happens. Here, just on a line opposite to the slit, in this case, pairs of vortices and anti-vortices are spontaneously generated. We can check it by simply calculating the change of phase when we encircle these topological defects in one direction. And then under the influence of the Magnus force, they start moving. If a vortex from a pair meets an anti-vortex from another pair, they annihilate. If an anti-vortex from the first pair meets a vortex from the third pair, they annihilate. But they move with such strong speed that even their lifetime is 3 orders of magnitude smaller than for vortices in chains. They can produce very prominent induced voltage. And what is induced voltage? It's a measure of deviation from superconductivity. It's a measure of induced resistance due to the motion of vortex-anti-vortex pairs. And on the characteristic induced voltage as a function of the magnetic field, this regime is represented by a peak. We have a peak of magnetic field versus induced voltage versus magnetic field characteristic. And what is interesting in this stage from topological point of view, we know already that in a tube there are 2 loops of screening currents. But in this regime, we see that former 2 loops are pushed towards the banks of
Recording in progress.
Slit, and there develop 2 more loops of screening currents, shown here by green. We have already 4. It's more complicated topology. And just between these loops, we have a locus of formation of vortices and anti-vortices. Please, next one. We have already discussed this. Please, next one. This is another material. For tin, it's equally good. Next one. Yeah, we have seen it already. Next one. Yeah. Okay. In recent work, very recent work, we considered this transition in more detail, and if there are states with vortex change and slips, phase slips, then depending on the direction of changes of current or magnetic field, we can see hysteresis. Please, next one. Next one, still next one. So these are two cases depending on the ramp time. When this ramp time is large enough, only vortices appear, but if the ramp time is small, so we can in fact visualize the metastable state with phase slips very confidently. Next one. Next one. Yeah. Okay. Next one. Good. This is a hysteresis. Next one. Yeah. The last few minutes I will devote to other nano architectures, and one of them is helical coil, which was produced by different methods. Next one. There is incommensurability of the vortices in different half windings of such a tube, which certainly are influential for transport. Next one. And this is an experiment which was already discussed by Professor Cordoba in our session, when the experimentally observed steps in resistance as a function of the current in such a nanohelix was explained by the occurrence of a few or more phase slips in half windings of this helical structure. Next one. Next one. Yeah, this is how does it develop on the number of half windings. Next one. Yeah, this also influence of an electric field. Next one. And very recent work was devoted to response of nanoarchitectures on modulated transport current. Next one, which shows a very rich set of transitions between vortices, phase slips, and combined structures, which certainly are reflected in the voltage as a function of time. Next one. Very interestingly, in this case, we can see also phase slip joints which are not along the axis, which are orthogonal. So in dynamics, new phase slips develop. Next one. This is another example of the same, depending on the modulation depths. So we can control which kind of defects will appear. Next one. And click 2 times more. Okay. Depending, and once again. Yeah. Depending on the frequency of modulation, for example, we can have either a state which is superconducting with relatively low voltage response due to surface stages without superconductivity, via stages which have both part of the sample which is superconducting and a part which is normal. Therefore, we have a kind of beatings in the voltage as a function of time, which are reflected in the fast Fourier transform to the state when almost the whole sample is already normal, and certainly it gives only frequency of the modulated current. Next one. This is simple, similar dependence on the magnitude of the current. Please, next one. Next one, yes. And this is, in fact, the final slide, which will be partly discussed today in our session at 15:20. But from these traditional structures, which are we are moving now to novel nano structures which can be fabricated, like this hat. And in this hat, we have already three-dimensional phase slips, which certainly open a new avenue for controlling the superconducting properties of such nanostructures. This opens perspectives both for fundamental knowledge and for applications, like filters, switches, sensors, bolometers, detectors of terahertz radiation, fluxonic devices for information processing, and squids and other Josephson devices in nanoscale and curved. And next one, so these are my thanks to collaborators. I am afraid I will not have enough time to name all of them, but please read, and to funding agencies, and I thank you for your attention.
Thank you very much for your nice presentation. Because of the delays of time, probably we have time just for a couple of questions, please. If any, just raise your hand. Yes, please.
Thank you for a nice talk. So I have a question about quantum phase slips. So vortex is a topological defect in superconducting order parameter, and there is a structure of eigenenergies levels in the core of vortex, and there are quasi-particles occupancy. So do we have similar features in case of phase slips, and to what extent movement of phase slips is deterministic process?
Certainly, there is an analogy between the structure and energy structure of vortices and phase slips and in their dynamics. But there are significant differences between these types of topological defects. Vortices are well defined, and though dynamical due to the superconducting currents in a vortex, they are defined entities, and they can be treated even within molecular dynamics as quasi-particles, if you know the interaction potential, which is already well established. But phase slips is a more complicated situation. It's a phase defect which is temporarily developing. It develops in time. Sometimes the definition names them as phase slip events. And they are represented, for example, by occurrence of some line or some region, one-dimensional or two-dimensional, even three-dimensional, with suppressed superconductivity. But there is a very rich dynamics of vortices and anti-vortices in our case and in many other cases within this entity. So therefore, if we're speaking about phase slip, we cannot simply attach some energy spectrum to it, because it's something more complicated. It embeds maybe 10 pairs of vortices and anti-vortices with their own energy spectra, which are moving, which are occurring and annihilating. And in this sense, a description of a phase slip cannot be reduced to the same instrumentarium as the description of a vortex. It's simply more complicated. One should take into account more conceptual ingredients for a phase slip.
Yes, please.
Thank you. Phase slips in field theory are not topological defects, are instantons. So they're tunneling events. So they're topological defects in Euclidean spacetime. That's the difference. So they are events, not topological defects.
Okay. Do we have further questions from the audience? Seems not to be the case. So let's thank the speaker again. And on
Thank you.
This and related topics we will continue in hall 3 in 5 minutes after a short break. So, Dino, it's my pleasure.
There is an announcement again. Please don't forget putting your words to the voting box for the first day presenters, please.
starting off with a little movie, I think, or an advertisement for the excursion tomorrow. So please enjoy. Really? Okay. So thank you very much. So I think we all look forward to the excursion tomorrow. But today we continue with the scientific sessions, and our first speaker today is Jens Wiebe from the University of Hamburg in Germany. And Jens is going to talk about the search for large topological gaps and isolated Majorana bound state in atom-by-atom fabricated Sheba chains. Jens, the floor is yours.
I hope you can hear me. Yes, okay. Thank you, Steffen. And thank you also, Andrzej Ptot, for putting together this nice series of talks, and for that I'm able to show our results. I will talk today about the topic of spin chains, which are assembled atom by atom on the surface of a topological insulator. And as you might have heard on Monday by Roland Wiesendanger, we are able to, by using a scanning tunneling microscope, to measure these N states, and also to show that the band structures, some of the bands in the Sheba bands of such chains are topologically non-trivial. And so today I would like to focus on think about how we can increase these topological gaps here, because one problem that we still have is that these Majorana bound states here are still quite extended along the chain, and then they can hybridize the two Majoranas from both ends, and they split off from the Fermi energy and are hidden in these trivial bands. And because the extension of these Majorana states is inversely proportional to the gap here, if we try to enlarge this gap, we might have a chance to have, in the end, more isolated Majorana bound states. And this I will show you by looking at two different samples, niobium and tantalum. Tantalum has a 3 times larger spin-orbit coupling, and the hope is that we increase the gap there. And then, if I have enough time, I will also show you some results on a thin gold layer grown on niobium, which we also do in order to increase spin-orbit coupling. And then finally, I will show you, this is the second focus on my talk, how we can also do some tests on some trivial edge states, which might look as Majorana bound states, in order to prove that they are topologically trivial. And this I will do for antiferromagnetic chains on niobium and tantalum. So these are the people who are who are collaborators. We are doing the experiments here in Hamburg in our group. Most of the work, or all the work here, has been done by a postdoc, Lukas Schneider, PhD student Philipp Eck. And then we are collaborating here with the groups of Thoro Poske in Hamburg, and also with the group of Stefan Rachel in Melbourne, and also here with Levente Rocha, and also the group of Laszlo Schönyok. And we have funding here from some priority SFB and Cluster of Excellence, and also from an ERC of Roland Wiesendanger. All right, so to give you some introduction on how you get Yushima-Rusinov states, what are Yushima-Rusinov states, how you get one-dimensional topological superconductivity and Majorana bound states, I will start with the smallest building block here of, imagine you have an atom which has only one orbital with one electron, and if you put this on a superconductor, you have already seen a couple of times that then you break the pairs partly in the superconductor, and therefore you get these so-called Yushiba-Rusinov states, which are in energy symmetric around 0. They must not be symmetric in their intensity due to Coulomb scattering effects. And the point is that if you change the Kondo coupling of these electrons, the local electrons with the superconducting bath electrons, then you shift these states through the gap given by this formula here. So this is the effective Kondo interaction. And now the interesting thing is if you couple such Shiba states together, so if you imagine you build a chain and then these Shiba states, they can hybridize, as you can see here. For example, this is the spectral function here as a function of this effective Kondo coupling, and you see that you form the bands when the Shiba states are shifting in the gap. So you form these so-called Shiba bands. And when you would measure the local electron density of states in such a Shiba band, you will find that they are all over the chain. And of course, you can then have here also some gapped, some mini gaps opening out, which are open, which we call trivial mini gaps in this case. And the most important thing is if you have now a non-zero angle between the neighboring spins, like a spin spiral, or you have ferromagnetic chains with spin-orbit interaction, then you can show that once these Shiba bands overlap with the Fermi energy, then there is another gap which can reopen here, and this is then topologically non-trivial. And inside of this gap, you will then get zero energy states which are located at the ends of these chains, and this is exactly what we are looking for. So you can also show that this works also for ferromagnetic chains if you have spin-orbit coupling, but then the question is, of course, for an experimentalist, how do you get strong spin-orbit coupling into your real system? And for us also another question is, what happens if the chains are antiferromagnetic? Does it also work? And then here, this is of course a model, a single orbital model, what happens with multi-orbital effects. And then always the question is, how do we distinguish topologically trivial mini-gaps from topologically non-trivial mini-gaps, or trivial n states, which you can also have close to the Fermi energy from these Majorana bound states. Okay, so of course we are not the first ones who look at such systems experimentally. So there is this pioneering work of the group of Jan Stani, these iron chains on lead, which we have already seen a couple of times. So the problem here is that these zero bias features that they observe are not on all chains in their system, and also not on both ends of the chain. And also the tuning of the system here is not possible because you can only grow them but not manipulate the chains. So then we have looked at, so these are both ferromagnetic systems in red. So we looked at these niobium and tantalum substrates because there you can really also manipulate your chains, and we have seen clear topological mini-gaps, as you have seen in Roland's talk, in one of the Shiba bands, and also we have shown that we find precursors of Majoranas which are still strongly hybridized. And but you can also have systems here, chromium chains, where you have trivial edge modes, as was shown in Stuart Parkin's group. Then there is the group of Nacho Pascual, which works on bismuth palladium system, chromium chains here. They didn't experimentally find zero bias end states, possibly because the chains are still too short, but you can also manipulate them there. And here there's the group, work of the group of Katharina Franke for niobium diselenide, where they also manipulate chains, but here they also did neither observe a topological gap nor zero bias end states, possibly because there are problems due to quantum spin behavior. Of course, there was then also work on spin spiral systems. This is the example here of our group, where we have looked at iron chains on the rhenium 001 substrate, and you see some end-state features here, but here the problem is that it's difficult to really separate them from the trivial Shiba bands because the gap size is very small, and this is the case because of the small substrate gap. And then the question is, what about antiferromagnetic chains? So here there's so far only theoretical work, and it has been shown here in the group that in contrast to ferromagnetic chains, a critical spin-orbit coupling strength is required for realizing really a transition to a topologically non-trivial phase. And we will look at this experimentally now. So all this work has been done in a 300 millikelvin ultra-high vacuum scanning tunneling microscope system, which you can see here, which is published in this publication, and we can apply a magnetic field perpendicular to the surface. Okay, so let's look at these two sample systems. Why do we choose niobium and tantalum? So the reason is that they are next to each other here in the periodic table. They have a very, very similar crystal structure. So the lattice constant is only very tiny difference. Oh, I think something is mixed up in this talk, but anyhow. So what you can also show that is that they have almost identical Fermi surfaces. They have a dz square-like surface state with similar effective mass and binding energy. And the gap of the tantalum is about half of that of the niobium. And the most important thing is here, while the electronic properties are very similar, the spin-orbit coupling of the tantalum is 3 times as large. So it's not so easy to prepare clean surfaces. We have to do flashing at a very high temperature close to the melting point, but it's doable. So you see here the surface with the steps after flashing with some residual oxygen defects, and then we deposit transition metal atoms like manganese at low temperature, and they just stick on the surface. And we have also shown that the same is possible for tantalum 110 with a similar quality. And here you see a sample of manganese atoms on the tantalum 110 substrate. And then we go ahead and okay, the next thing what I want to show you is that these systems have very similar multi-orbital Yushiba-Rusinov states. So we look at the spectrum here at first for the niobium substrate. You see here the nice coherence peaks. So by the way, all these spectra are taken using superconducting tips and then are deconvoluted. And so the gap is about 1.5 millielectron volts. And if you now take a spectrum on this manganese atom, you see that you get these additional states inside of the gap. And this is now not only one Shiba state, but 4 of those, because you have 5. You can have up to 5 because you have 5D orbitals. And then you can map the shape of these Yushiba-Rusinov states by taking maps at the locations of these peaks. So this is shown here. You see that we have, of course, always a peak at plus and minus energy. So you see here always these shapes appear twice. And you see that they resemble these d orbitals, right? dz square is the one which has the largest intensity here. And then there's the one which is already close to the Fermi energy is the dyz state. And here you can see their energies normalized by the gap of the niobium. So you can do the same thing for manganese atoms on tantalum. This is shown here. So now, of course, the tantalum gap is smaller. It's only 0.7. But again, you find that there's one state here, which is the dz square-like state, which is closest to the gap edge. And there are some states which are more inside of towards the Fermi energy. So, and if you compare the numbers here, particularly this dz square-like state is very comparable to the niobium case, and that's why it's very good system to now form bands of these Shiba states and look at their topological properties. Okay, so I think Roland Wiesenhanger also has shown already that we can investigate the magnetism of these chains by spin-resolved scanning tunneling spectroscopy. So this is just an example. We can do this for all the chains we are looking at. This is now an example of a chain assembled along the 1, -1, 1 direction. And you can see here when you measure with a magnetic tip that you can see this dark, bright, dark, bright, dark, bright contrast in a magnetic field. And if you reverse the magnetic field, you have a phase shift here of this contrast. and as you can see in the subtracted images, this reminds you of an antiferromagnet. And you can see the same thing for if you have the same manganese chain on tantalum. Again, you can see here a dark, bright, dark, bright, dark, bright contrast, which is reversed in a magnetic field. So from that we know that for this example, both chains have an antiferromagnetic spin order, and you can really show this for more different directions, that these two systems are very similar. And here in my talk I will concentrate on this direction along 001, chains along this direction which are ferromagnetic, and later on chains along 1 minus 1, 1, which we have just seen, which are antiferromagnetic. Okay, so let's look at these ferromagnetic chains along 001. And now again we will, in order to see what the Shiba bands are looking like, so how these U-Shiba-Rusinov states are hybridizing to form Shiba bands, we will take spectra along such a chain and plot here the energy, and here is the position along the chain. And then you can see that now inside the gap of the substrate, which is marked by the coherence peaks here, you can see these standing waves occurring with different numbers of maxima. So this one has 4, 3, 2, and 1. But you already can see that there is this kind of gap at the Fermi energy, and this holds true if you now make the chains longer and longer, then just your standing waves are changing in energy, okay? And the states just hop across this gap. So there is this mini gap, and we can also look at this a little further if we not plot the density of states only along this line, but on a two-dimensional fashion across such a chain. And then again, you can see these states which I've just shown you previously here with 7 maxima, 6, and so on. So because if you remember these, the form of the Shiba states, we can prove that these bands which are forming here are coming from the dz square-like orbitals, which have this kind of shape. But you can also see at some locations where you, for example, do not have these alpha Shiba states, you can also see these kind of standing waves, which remind you of the extension of these other orbital states. And so we think that these kind of states here are scattering states which appear in the other orbital delta band. And now you can go ahead and extract the dispersion of these states either by doing just a Fourier transform or by doing some more, by fitting some sine square functions basically to the data, and then you end up in this kind of dispersion of these states. So you here see again this nice quasi-parabolic band of this alpha Shiba states with this band gap, mini gap here. But you can also see that these other states, so these states here, they basically cross the gap. So if you zoom in intensity here, you see that these orbitals here, they cross the gap. And now, if you want to show that this is you can show that this is a topological gap, for example, for this alpha band, because if you compare this to a single orbital tight binding model, you see that it looks, so you can compare this to this tight binding model and go from the topologically non-trivial case to the trivial case, and you see that you clearly have this kind of crossing of the Shiba band of the Fermi energy, which means that it has to be a topologically non-trivial band. And on the other hand, this is not, of course, a little bit more complicated because you also have this delta band. And here we have to rely on recent theory from Daniel Crawford and Stefan Rachel, which tell us that overall the system is topologically non-trivial. So these delta bands also must have a topological gap, which is just too small for us to be resolved. Okay. Okay. I cannot show you this. These other kind of. Sorry, I'm also doing this. I have a problem with this button on the side. I have to? Okay. Maybe just press 10, enter. Yeah, okay, thanks. Okay. I have no time to look into other chain directions, but the question for us now is how are we able to increase the size of this gap? Because one problem that we have here is that in the data we do not see clear end states, and then the question is, can we increase the size of the bands by using a substrate with stronger spin-orbit coupling? And therefore we do basically exactly the same experiments now with tantalum. So here I show you the spectroscopic line profiles along chains of increasing length. And again, this is the energy, this is the location along these chains, and you can see basically very similar behavior as before, just with less energy resolution. Yeah? Again, you see these standing waves which are jumping across the Fermi energy, so there is again a mini gap, and you can also look at the states in a two-dimensional way. Here again you can see these standing waves with 4 maxima or 5 maxima or 2 maxima, and then you can also prove again that these states come from this alpha orbital. Now it's slow. Okay, and if you again extract the dispersion, you find again a very similar band structure here, which now has a gap, also a gap at the Fermi energy, and you can, in order to extract absolutely the width of the gap, you can make a cut through this position here and extract here the size of this topological mini gap, and then compare this to the niobium case which we measured before. Yeah, so you see here the comparison of the two band structures. So they look very similar, just that of course on the tantalum you have less energy resolution. And by this comparison you can see that the gap of the tantalum is about 150 microelectron volts, while it's 160 microelectron volts on the niobium, but of course you have to relate this to the absolute gap of the substrate, and by that you see that the gap of the tantalum is 2 times as large as on the niobium. And because these two cases have so similar electronic structures and so similar Shiba state properties and similar dispersions of the Shiba bands, we think that this strongly substantiates that this mini gap is really due to p-wave pairing induced by spin-orbit interaction. All right. So how much time do I have? Okay, then we have to press the emergency button. So I have to skip this gold monolayer, and we go to the, thank you, antiferromagnetic manganese chains. So now let's look at this case of antiferromagnetic manganese chains on tantalum. Here is a manganese 22 chain, and again, I can measure line spectra along such a chain, and again what you see is that within the gap of the tantalum substrate you have this kind of band formation here, Shiba band formation, and then you have a mini gap, and in this case you see some end states. Yeah, these states here are on the, quite close to the Fermi energy on the end of these chains. You can also do, again, this two-dimensional mapping and show that here in the Shiba bands, these states are located all over the chain, and here at the Fermi energy you get a clear signature of some end states. You can also show this for different chain lengths. Maybe I don't have to show this in detail, but basically these end states, they already evolve for chain lengths on the order of something like 10 atoms. Okay, so the question here, what is surprising is that this is a very large mini gap, and the question is of course always, are these Majorana bound states or trivial end states? In order to find a way to answer this experimentally, we move some manganese atom close to this end. So we put another atom here and then move this atom closer and closer, and now look at these spectroscopic line profiles along this whole system, which is shown here. So this is the case for this topmost situation. So you can see here again these N states, and here are the U-Shiba-Rusinov states of the manganese atom. And now you can see what happens if I move the atom closer and closer. You basically see that here there happens something to this side of the chain, but on the left side the state basically stays completely unaffected. And this is not at all what you expect from a Majorana states, because they're either you would always have a zero energy end state which is just shifting in position, or you would expect that when you perturb the system here considerably, that also on the left side the system will be affected. We can do the same thing for the niobium substrate. Again, very large mini-gap. Now in this case we clearly have non-zero energy end states. And again, you can look at these states in a two-dimensional fashion and look at the length evolution. And again, you can conclude that we have a very large mini-gap with finite energy end states, but and that these states evolve from U-Shiba-Rusinov states from the Fermi energy. And again, you can play the same game here, that you perturb the chain from the left side in this case with some defect, and you see that these end states are perturbed into two states which have a different energy. So it's clearly not a coherent state, but these are local end states on both sides of the chain. And we can model this by some very minimal tight binding model by just taking into account that in such an antiferromagnetic chain, the hopping between nearest neighbors will be essentially very small, while the superconducting coupling will be large because of this antiferromagnetic spin structure, while the second nearest neighbor hopping will be small, when the second nearest neighbor hopping will be large, and the second nearest neighbor gap superconducting pairing will be small. And if you do this, you end up in such band structures which you can compare to from the scattering vectors to the data. Yeah, and by this comparison, you can extract exactly the parameters of your tight binding model. This is here the calculation, and this is the data. And then you can look at the local. First, you find that T1 is non-zero because of finite spin-orbit coupling. But the most important thing is that your band structure and model exactly reproduces the experiment. You get these finite energy end states, and so what you can conclude from that, even if in the case of zero spin-orbit interaction, you get trivial edge states, which can be quite close to the Fermi energy. And you always have to be very careful not to confuse this with Majorana modes. And if you want to drive this system into the topologically non-trivial phase, you need a very, very strong spin-orbit coupling, which is unrealistically large. So we think that for this case, to drive the system into topologically non-trivial mode is basically very, very difficult. And I think I just leave this for you to read, and thank you for your attention. Oops.
Thank you very much, Jens, for a very clear and talk, and I can certainly appreciate the experimental efforts that went into that. Other questions in the audience? Please.
I will speak loud. Oh, sorry. There's a microphone. Thanks, Jens, for a beautiful talk. One question I have concerning the Shiba state. Why is there such an asymmetry for the states in the negative and the lower and the upper part of the gap?
Yeah, this is because of that you do not only have this Kondo coupling, but you can also have Coulomb, Coulomb repulsion, and this makes the asymmetry you can show in this very classical model of Shiba. This does your asymmetry, and this is also what helps us in order to distinguish that these bands are in a topologically non-trivial case, because if the two Shiba states would be equal height, then you would basically see two bands which have exactly the same intensity, and then it's again very hard to tell whether your gap is topologically trivial or not. But just that we see that one band with a large intensity crosses the Fermi energy gives us a handle to prove that this is topologically non-trivial.
Can I ask a second short question? Why is the resolution on tantalum so much worse compared to niobium? You maybe said it, but I missed it probably.
Just because the superconducting gap is half as large and our temperature stays the same.
Thank you.
Okay, I think in the interest of time we continue, but not before giving you the certificate. Don't walk away.
Thank you very much.
Okay, thank you very much again. And we move on to the second talk in this session, which is given by Omar Geldi Atonov from Hong Kong University. And this talk is on one-dimensional superconducting quantum anomalous Hall insulator.
Sorry. Can you hear me? Is it okay? Okay. Maybe I put this here. Okay. Thank you. Good afternoon, everyone. Thank you very much for organizing committee for inviting us to give this talk. Unfortunately, my supervisor couldn't come, and I have to present my talk here. But thank you very much for inviting us. So what I'd like to present to you today is our recent work on quantum anomalous Hall insulators, especially in quasi one-dimensional limit and induced superconductivity. But before getting into the details, I'd like to acknowledge our collaborators in this project, namely Professor Kangel Wang and his group in UCLA provides us with the heterostructures, and Professor Campton Lowe's group at HKUST helps us with the theoretical support. And he's my supervisor, Professor Lors. So I'd like to, first of all, start by giving a brief background about our work, and then I will give some specifics of the materials and methods, and then I will share the results of the 2 experiments that we have done on this heterostructure, and I have some concluding remarks at the end. Okay, so some of the most important achievements, I think, in the last 2 or 3 decades in condensed matter physics is, I think, the completion of this Hall effect family picture, where we discovered all the quantum counterparts of the classical Hall effects. And you know, we learned a lot of physics from studying these quantum Hall systems. For instance, the quantum Hall effect, as you know, is the precise quantization of the Hall resistance at certain magnetic fields. And at the time, the question was whether one can achieve this quantized Hall resistance without the need for any external magnetic fields. And it came much later, only after the discovery of quantum spin Hall effect. So the quantum spin Hall effect has this, it was first discovered in mercury telluride quantum wells, and it has a time reversal symmetry which supports the existence of the helical edge states. And once they doped these mercury telluride quantum wells with magnetic impurities, they could break this time reversal symmetry to obtain only one channel of a chiral edge mode. And once you have this chiral edge state, you can achieve a quantized Hall resistance. But still, in that mercury telluride samples, they needed some magnetic field, some limited magnetic field to see that exact quantization. And only the ultimate quantum anomalous Hall effect with 0 magnetic field was discovered in chromium-doped bismuth telluride samples. So, and it was theoretically proposed that you can have a chiral topological superconductor by inducing superconductivity on the quantum anomalous Hall insulators, and by just normal S-wave superconductor, you can proximity induce the superconductivity and achieve a effective P-wave superconductor. And this topological superconductor, in theory, supports odd number of chiral Majorana modes, edge modes, and Majorana zero modes in vortices. As you can see here, the quantum anomalous whole state supports chiral edge mode, which is an electronic mode, and you can mathematically decompose it into two Majorana modes. And if you can achieve this chiral topological superconducting state, one of the degeneracy of this chiral edge mode is lifted, and you can have only one chiral Majorana edge mode. And so that was what we would like to utilize in our experiments and what we'd like to realize at the end. And the material that we use for our case is the 6 quintuple layers of chromium-doped bismuth antimony telluride films that are MBE grown on gallium arsenide substrates. And the Fermi level in this recipe is exactly in the middle of the surface gap opened by the chromium doping. So they tune the bismuth to antimony doping ratio to achieve that. And we have, we deposit 200 nanometer thick niobium superconductor on top of this QHI film. And you can see the standard Hall measurement of this sample, where there is this exact quantization. And the interesting point is that in this QHI states, we have this characteristic zero conductance plateaus that happens because of an intermediate trivial insulating phase. That can also be seen in this longitudinal conductance measurement with this dip at the same magnetic field that corresponds to this Hall plateau, zero Hall plateau. So we, on this heterostructure, we prepared different point contacts in order to see this spectroscopic signature of these propagating Majorana modes. So this work has been already published in 2019. And this is the schematic of the device that we have prepared. So we first deposit gold at the edge of this heterostructure, and then we pattern this gold to be in a point contact limit by patterning it into strips of 200 to 500 nanometers. And also we attach normal contacts on the surface of superconductor. And once you have this, you can drive the system through different topological phases by switching the magnetization of the QHI. And that's what we did. So we started, for instance, in this case, we started from minus 500 millitesla to plus 500 millitesla. Of course, all the data are taken at 15 millikelvin. So at 500 millitesla, the QHI is fully magnetized, and it's in a normal QHI state, quantum anomalous Hall state. Basically, it's somewhere here. And then as you increase the magnetic field and as you reach this magnetization reversal, you enter into a chiral superconducting state, and then your end-ref reflection spectra also changes from a deep structure into a plateau-like structure. And as you go further, you reach this trivial insulating state with a normal zero conductance. And as you go further, you again enter into a chiral superconducting state with only one Majorana mode and then normal QHI state. You can repeat this experiment, same experiment, by reversing the magnetic field, and you will traverse this trajectory, basically, and then the same exact features will be repeated. And so this same experimental observation is in a good match with the theoretical calculations based on the same point contact spectra. Now here you can see the band structure corresponding to this system with this magnetic field axis. As you can again drive the system through these different topological phases with changing the magnetic field. And the calculated spectra for the end-ref reflection can be seen here with the observed experimental data. So at QHI quantum anomalous whole state, you have two Majorana modes that are canceling each other's end-ref reflection. So you have a deep at zero bias and a peak at the gap. And then you have, when you enter into chiral superconducting region, you have only one Majorana mode, which gives you this plateau-like structure. And then when you reach the insulating state, you have only zero conductance. But as I said, it's been almost 3 years now that we have done that experiment, and most recently we have been interested in observing this Majorana zero mode, as we have heard a lot today. And now the motivation for that comes from these two papers that were published in 2018. Both of them are basically talking about using a quasi one-dimensional quantum anomalous whole system, which is what we have, and in proximity to a S-wave superconductor. And so the idea presented in the papers goes like this. So we have chiral edge states in our QHI, and if you can shrink this, narrow down this QHI into a width that is comparable with the chiral edge mode localization length, the two edge modes will be coupled into each other, and then they open a hybridization gap in the spectrum. So this one is the normal chiral edge mode with linear dispersion, and then this one is for the narrowed down quasi one-dimensional limit. And if you can induce superconductivity on this helical channel that is formed after the gap opening, you basically enter into a topologically non-trivial state which is characterized by the NBDI here, equal to one region, the regime. Then you have this Majorana zero mode in theory that are localized at the ends of this quasi one-dimensional system. And then you can reach that region by either tuning your chemical potential or the magnetic field, or both together. So experimental detection of this Majorana zero mode bound at the boundary can be done by attaching a macroscopic lead on the QHI and then grounding the superconductor. So when an electronic mode, which is a chiral edge mode of QHI, is reaching the boundary, it will be reflected as a whole, and then a Cooper pair will enter into the superconducting side. And the conductance through this boundary will be doubled, and as a result, the Andreev reflection, there will be a resonant Andreev reflection, and then you expect to see a 2e square over h quantized peak at zero bias. Okay, so in real life, we wanted to basically realize this system by patterning our two-dimensional QHI superconductor samples by using FIB SEM dual beam system with focused ion beam system use accelerated gallium ions in our case. So you can see the typical SEM image from one of our nanoribbons. So we can make sure that all the layers of this nanoribbon is preserved by checking with the SEM from the side and comparing the heights. And this is a AFM scan cut from another study that we have been collaborating with. And here I'd like to highlight that the cross-section of the nanoribbons are not rectangular, but the top layers usually have narrower width than the bottom layer. And this is a typical image of our device where we prepared this 82 nanometer nanoribbon at the edge of this, at the boundary of this QHI and niobium layer niobium area. And the device geometry for our experiments device setup is like this. So we send the current from a QHI side by depositing gold, and then we measure the voltage from the inner contacts. A real life image of the device looks like this, and this is the toy model for the theoretical simulations that I will come later. So in the first devices that we measured, we have observed some zero bias anomalies, but they don't look pretty as pretty as the theory suggests, of course, and it's not as sharp or any kind of, it has all these structures to it with some shoulders and with a central peak basically, and we wanted to reproduce the theoretical result, of course, but it didn't succeed yet. So what we observe here is that we have a central peak, and then we have all the shoulders, and then we have this diminishing and reflection signal as you go out of the niobium gap. And just naively considering that it's of superconducting origin, we wanted to fit this signal, the spectra that we observed, but you need at least 3 gap values for fitting this with normal standard BKT model. And all these gap values are interestingly below the niobium gap values, and so we attribute these structures to the central peaks to the Andreev bound states found at this interface. And another thing to note is that these shoulders are smoothed out at some of our devices, and they are, and in some devices we prepared several nanoribbons in parallel to each other to increase our chance of obtaining some results. So also that contributes to the smoothing out of all these shoulders. And also we observed that the conductance is very much enhanced, and in the theoretical prediction, of course, you have zero conductance and with a sharp zero bias peak, but we don't observe that, and we think and we suspected that there is a bulk conduction going on inside, in addition to the helical channel that is going inside the superconducting side. So we wanted the same theory group to help us in simulating this, our device structure, by considering that the Fermi level is lying inside the bulk gaps, bulk bands. And they did, and what they also observe is this kind of structure with the peak and all these shoulders. When they consider that, for example, for this black curve, the Fermi level cuts 3 bands inside the bulk, and for the pink and blue curve, it only cuts 1, this helical channel. And this is our experimental observation, where we increase the out-of-plane magnetic field, and we also see that the central peak and the shoulders are changing with the magnetic field. So as we increase the magnetic field, these shoulders go away, and then we reach a stage where we only have a central zero bias peak, and that also disappears at 4 Tesla. 4 Tesla is around the same, that's the critical field of the niobium in our system, usually. And so what we suspected is that the applied out-of-plane magnetic field is somehow driving the system from the bulk and into the gap region, and where there you obtain this zero bias peak that is coming from the only bound Andreev states. So this is for the device, for the second device, and this is theoretical simulation with considering the Fermi level cutting 7 bands for this blue one, and it goes down, and here it only cuts the helical channel. So that's what, for the device 2, it looks almost the same with the 7-band cutting Fermi level simulation. And then as we increase the field, we also get this a very broad kind of a zero bias peak. And then it's diminishing as you increase the magnetic field. And this is for the third device. The same story repeats, but in this one we had 9 nanoribbons in parallel to each other, so we don't see these 2 sharp shoulders here and only a broad peak. And then this is the evolution of the peak at higher magnetic fields. So it also vanishes and it goes away at about 4 Tesla. How much time I have? 5 minutes. So I think I can summarize. To summarize, so we have prepared point contact devices at the quantum anomalous Hall insulator niobium heterostructures at the edge of these heterostructures to obtain the spectroscopic signatures of the propagating Majorana modes. And the experimental observation of ours matches well with the theoretical calculations. And afterwards we did the Andreev reflection spectroscopy at the end of quasi-one-dimensional system of the same heterostructure. And we are still ongoing, these studies are still ongoing. And what we observe, we attribute it to the Andreev bound states that are located inside the niobium gap. So I would like to highlight that this is a promising platform for observing the Majorana zero modes, of course, because it's first of all, it's theoretically possible to see these Majorana zero modes, but of course we have to improve the quality of our devices in order to prepare cleaner devices. And the importance of this is that our approach is an easy one because you can scale it easily, and it's a top-down approach basically. We don't have to grow the nanoribbons. And of course, if you can one day observe them, this final step would be to, next step actually, would be to try to control and braid them for topological qubit structures. These are from the same 2 papers that I've presented before. Using the gates, they would like to braid the Majorana zero modes to obtain a qubit structure. And these qubits will be topologically protected and are building blocks for quantum computation. So I think I will end my talk here. Thank you very much.
Thank you very much for a nice talk and specifically for staying in time. The talk is open for discussions. Are there questions, comments? Maybe I can get started. You mentioned in your second part for the device fabrication that there is some problems with the devices. I think one issue that arises from the gallium FIP is typically that you implant gallium into your device, specifically when you have these very small ribbons. Can you exclude that there is a gallium doping?
So we have also tried this FIB patterning with normal two-dimensional QHI films, and we can we can measure it so that we can make sure that the helical channel is formed through the nanoribbons, and there is no gallium, there is no defect because of the gallium, that when the nanoribbon is continuous, you can expect the helical channel to be forming, and it should be, the chiral edges anyways, it's ballistic and it's dissipationless, and when the helical edge is formed, you expect it to be continuous through the nanoribbon despite the gallium implantation. Yeah.
Any other questions? Okay, if not, then I think in the interest of time, we go on. Thanks very much again.
Yeah. No.
And yes.
Thank you. Thank you very much.
So the third talk in this session is given online, and it's actually given by Madhab Newpain from the University of Central Florida. So I appreciate very much Madhab getting up early in the morning. Madhab is going to talk about photo emission investigation of superconducting and magnetic topological materials. So we see you, and we do not yet see your slides. There it is, okay? So we see you well?
Hi, can you hear me?
Yes, we do.
Okay, thank you. Thank you for your kind introduction. So let me get my pointer. Okay, so good afternoon, everybody. I'm Madhav Neupane from University of Central Florida, Orlando. Today, I'm going to talk about photoemission investigation of superconducting and magnetic topological materials. So before I start, I would like to thank organizer for giving me this opportunity. I'm sorry that I could not be there in person. I would like to especially thank Professor Petak for the invitation and giving this opportunity. Okay, so this is the outline of my talk. I will be introducing topological insulator and beyond, means some new phases beyond topological insulator. And then I'll talk about superconducting topological materials, for example, strontium doped bismuth selenide, BIPD, alpha PDBI2. And then I will talk about some magnetic topological materials, especially Kagome magnet. Okay, so let me talk a little bit about topological insulator. So what is the difference between conventional insulator and topological insulator? So in conventional insulator, we have conduction band and valence band. They are separated by band gap. But in topological insulator, we have conduction band, valence band, band gap. But within the band gap, we have this surface state, which have this spin polarized channel within the band gap. So how we can understand this topological insulator with simple band-like picture? So one way of thinking is that, let's say in the atomic limit, so when your lattice constant is infinity, then you have energy level, they're separated by some sort of gap. But if you take a real lattice with the experimental value, you have this kind of band. So conduction band, valence band. In some materials, it may possible that the bottom of the conduction band goes down, top of the valence band goes up. And if you consider the spin orbit coupling, the band gap may open. And if there is some sort of symmetry, so you have this kind of inverted band gap, and within the band gap, if you have some sort of symmetry, for example, time reversal symmetry, you may have this kind of linearly dispersive spin polarized surface state. Okay, so for experimentally, so how you can determine the topological insulator? So I call this experimental checklist. So let me explain what is this. So this is energy versus momentum. So it's kind of dispersion map. This is what we got if we do angle resolved photoemission spectroscopy. So 0 means Fermi level, and x-axis is momentum, y-axis is your binding energy. And when you get this kind of image using the spectroscopic technique, so you will be looking for Dirac point. So Dirac point is basically the points when you see this left moving branch and right moving branch, they cross some point or crossing point. And another thing we are looking for is band gap. So it's basically bottom of the conduction band and top of the valence band. So how big is the band gap? So typical topological insulator, something like bismuth selenide, it has band gap of around 300 milli-electron volt. So including Kramer's point, the state including Kramer's point, so you actually map out the whole billion zone and try to find out how many states you have in the billion zone. That includes the Kramer's point. So another important point, this kind of hallmark of topological insulator is spin momentum locking. So you measure the spin on one side and you measure the spin on another side. So they kind of have opposite spin. So at K, if you have up spin, so at minus K, you have a down spin. So another thing is like number of Dirac cone, like either it's odd or even. So based on that, you have weak TI or strong TI. Okay, so that's all about the introduction of topological insulator. So now let me go beyond the topological insulator. So after the discovery of topological insulator, people started to look for other phases protected by some other symmetry. For example, this mirror symmetry protected state called topological crystalline insulator. Or people also started to look for the bulk state. Okay, so like metallics, like Dirac, wire, and nodal line semi-metal. Okay, where the spin orbit coupling does not open a full band gap. So there's a certain point of the billion zone, you have conduction band and valence band, they touch each other. Or some sort of interaction. So like especially like SMB6 type of material, so where you have D and F electron, they hybridize and open up a gap and there's some sort of symmetry coming the surface state. Or the main focus of this talk is this topological superconductor or magnetic TI. So topological, you can do the proximity induce or you try to find the intrinsic topological material, or same thing for the magnetic topological materials. Or you can also do some sort of phase transition going from trivial to topological insulator by tuning the spin orbit coupling. Okay, so I happen to work on these various phases, but this talk I'm mostly focusing on topological superconductor and magnetic topological materials. Okay, so let's start with superconducting topological materials. So the motivations come from earlier work from Professor Kaba group at Princeton, where they reported this copper doped bismuth selenide superconduct. So for example, you can see this magnetization and resistivity measurement in this particular copper doping. You see TC is 1.8 Kelvin, in another doping like 3.8 Kelvin. So this actually really started looking for the superconductivity in topological material with doping. Okay, so it's basically search for the bulk topological superconductor. So it's basically copper is intercalated between this quantuple layer of bismuth selenide. And another way to introduce superconductivity is just use the pressures. For example, this pressure-induced superconductivity in bismuth telluride. And you can see within 3 to 6 gigapascal, you have TCs of 3 Kelvin. Okay, so one is the doping, another is the pressure-induced. So there's another way to introduce the superconductivity. So this is kind of proximity-induced superconductivity. So this is one of our earlier work, where what we did is we grow bismuth selenide on top of niobium diselenide using MB. And due to the proximity effect, actually, this kind of superconductivity actually can be observed on this bismuth selenide film. So for example, this 4QL, like 4 quantuple layer, which is around 4 nanometer, and you can actually, we have a momentum resolution, so you can actually do the temperature dependent measurement, particularly selecting either surface or bulk, and you can clearly see this kind of superconducting gap, this quasi-particle gap, and they actually vanishes if you go above the superconducting transition temperature. If you go above 7 Kelvin or 12 Kelvin, there's no gap, but if you come down, you can clearly see this kind of superconducting gap. Okay, so then, so what we did is, okay, so copper doped bismuth selenide at that time is basically the superconducting volume fraction is not good. So if you see that is in some of the cases, you see it doesn't even come to the 0. So at that time we thought, okay, let's do the strontium doping on bismuth selenide. Okay, so we did like 6% of strontium doping on bismuth sunlight, and you can clearly see very sharp superconducting transition temperature with TC is around 2.5 Kelvin, and this shielding volume fraction is at large as 90%. So other group also reported even more than that. So you can see that with the varying doping, the TC can reach close to the 3 Kelvin as reported by other group. Okay, so what we did on this strontium dope bismuth selenide, so we use a spectroscopic technique. So it's kind of a RPACE and time result RPACE. So RPACE is basically photon in electron out process. So using the conservation of energy and momentum, you can actually map out the band structure, Fermi surface, electronic structure, and so on. So time result RPACE, what you do is you use the pump probe setup. So you pump your system, and then your probe actually try to picture what is happening on the unoccupied side, okay, on the excited side. So for example, you can see is in native is highly pedo, Fermi level is well deep in the bulk valence band, but if you pump it, you can see excited state, surface state, bulk conduction band, but they decay pretty fast. So within 10 picosecond, everything is recombined. So it's a short optical lifetime. Okay, so we did the similar measurement on this 6% strontium doping bismuth selenide. And without pump, what we see is this kind of Dirac state where Dirac point is deep below around 550 MeV below the Fermi level, but there's some sort of this kind of 2D band, 2D quantum well state near the Fermi level. You can see 22 eV, 24 eV. And using this pump probe setup with the 6 eV laser, we can clearly see this kind of Dirac band as well as 2D band. So we pump it and you can see this occupied side and then, a little bit 2D state extended over here. Okay, so, and then we try to understand the relaxation dynamics. So you actually, because we have a momentum resolution, so you sit here and then do the time scan and see what will happen. And this is how we got. So you can see that this right surface state and left surface state, they have one kind of decay mechanism, but this 2D state has a slightly different type of decay mechanism. So both relax within the 5 picosecond. Okay, but seems like it has two different decay mechanism, and obviously there's a short optical lifetime, couple of picosecond. And one important thing is if you are dealing with a metallic sample, it's very hard to pump. I mean, very hard to get the state above the Fermi level. Okay, so then what we did is we tried to fit this surface state and 2D state. Okay, and we found that this 2D state is well fitted if you use two double exponential decay fitting function. But the Dirac right and Dirac left, so they fitted well with the single decay function, single exponential decay function. So we did a little bit of modeling and we come up that so this topological surface state, mostly the decay mechanism is mostly dominated by intraband scattering, but this 2D state, it has this double decay function, so it has both intra and interband. So if you consider this kind of decay constant, so it has kind of longer decay similar to the surface state, but it has one faster decay, which may be coming from this strontium vibrational mode. Okay, so that's all about the dope system. And then we thought, okay, let's try to find some intrinsic topological superconductor, like not dope. Okay, so the idea is single material with topological surface state and superconductivity. So our idea is to get this topological superconductivity. So it's a source discovery and characterization. Okay, so then we come up with this BIPD, we including other group. So this is monoclinic unit cell and non-centrosymmetric structure. You can see that crystal structure here. So this top surface is different than bottom surface. And it has very metallic, and also it has sharp superconducting transition temperature around 3.7 Kelvin. And you can see very sharp core level and this is a bulk and surface Billion zone. Okay, and we did this electronic structure measurement, and you can see this energy versus momentum dispersion map. And you can see this kind of cross state, X kind of state. And we did this kind of constant energy contour, and around 700 MeV, you see this dot over there. And if you go higher, you will start to see circle. Okay, and this kind of, we see linearly dispersive state around 700 MeV below the Fermi level. And we did photo energy dependent, so this always, this state always remains there. It doesn't disperse with photon energy. Could be signature of surface state. And we say, okay, it could be some surface originated, some dangling band or something. And what we did is we call this thermal recycling. So we raise the temperature and cool down. So it is up to 300 Kelvin and come back at 20 Kelvin. So it's always there. So it's kind of very robust state. So another thing we did is we measure the spin polarization, and you can see spin at this line. So I mean, this branch is opposite to the spin at this branch. You can see it's going down and up, but here going up and down. So it looks like it's a spin polarized state. Another interesting thing we found on this system, this is a non-centrosymmetric. So if you clip one side of the surface, the location of Dirac point is different than if you clip on the another side. So it's a direct observation of non-centrosymmetric electronic structure. So Dirac point is almost around 50 MeV offset, so which is kind of in agreement with the DFT calculation. Okay, so summary for BIPD. So we get presence of surface state in non-centrosymmetric superconductor, presence of surface state about 700 MeV below the Fermi level, spin polarized state, and non-centrosymmetric electronic structure we observe. Okay, then we started to think of some Rasper system which might have superconductivity. Okay, so the motivation is actually comes from this theory paper. So where they say this coupling of S-wave superconductor with Rasper split system in a magnetic field could provide Majorana zero bias mode. So thinking along that line, we come up with this alpha PDBI2. So this is superconduct, so less than 2 Kelvin. And we see some sort of Rasper state near the Fermi level as well as some sort of Dirac state. Okay, so this is a crystal structure and characterization of alpha PDBI2. It's a monoclinic crystal structure, so it's a centrosymmetric. You see top and bottom surface look same. And this is a resistivity measurement. So TC is less than 2 Kelvin. And this is a Billion zone, and you can see core level measurement. And this is a unit cell. Okay, and we did the electronic structure measurement, and you can see clearly it's very metallic. There's a lot of band near the Fermi level, but there's some sort of Dirac-like state around 1.2 eV below the Fermi level. So if you do Fermi surface map and go to the higher binding energy, you can see those state, how those revolve. Okay, so it's if you do the wider mapping, you can see a lot of pockets, a lot of bands. So it's highly metallic at normal state. Okay, so we did the band structure calculation, and you can see if you include the spin orbit coupling, there's always this kind of Dirac state as well as Rasper state near the Fermi level, in the vicinity of the Fermi level. Okay, so this is how our data looks like. So there's kind of Rasper state at A point, which is in agreement with the DFT calculation. Okay, so conclusion on this superconducting topological materials. So in strontium doped bismuth selenide, we found Dirac state, 2D state. Dirac state is around 450 MeV below the Fermi level. So using pump probe measurement, we found different decay mechanism. And in BIPD, we observed a Dirac state well below the Fermi level. Spin polarized state is a non-centrosymmetric electronic structure. And alpha PDBI2, the Rasper state in the vicinity of Fermi level, Dirac state below the Fermi level, but it has centrosymmetric structure. Okay, so let me go to the magnetic topological materials. So these materials are kind of very hard in condensed matter system right now. So we work a couple of system. So for example, first is UIN2S2. So this material is predicted, theoretically predicted by CDI group to have this higher order topological insulator. So there, what we did is, so it's a magnetic with AFM temperature is around 16 Kelvin. So we measured the electronic structure below and above the transition temperature. Okay, and we clearly found that below the transition temperature, there's some sort of splitting there. You can clearly see these two pocket below the transition temperature, but only one pocket above the transition temperature. And we also study this kind of breathing Kagome, where we see a lot of flat band. I'll describe more this. And also we study this 166 type Kagome system, like ERMN6SN6 or HOMN6SN6, where we see very complex magnetic structure. Dirac state looks like a little bit higher than above the chemical potential. Okay, the another system we study this CLSI, cerium-based system, where so it has a magnetic as well as it has non-centrosymmetric. So actually, this system we observe this kind of wild point as well as Fermi arc, and this tuning the temperature, you can actually tune the wild points. And on this NDSP system, we kind of see Fermi arc and very complex structure below the magnetic transition. This is also AFM with temperature 15 Kelvin. Okay, so let me go a little bit detail on Kagome system. Okay, so why Kagome system? Okay, so Kagome is like a Japanese word, it's kind of bamboo basket. So it's basically corner sharing triangle. So if you have a triangle, so let's say if you want to arrange this antiferromagnetically, and let's say if you arrange your one spin down, one spin up into another corner, but at third corner, it doesn't know which way spin has to be pointing. So it created this kind of spin liquid phase, this spin frustration or geometrical frustration. It also has a charge frustration. So let's say electron at here, here, and here, the electronic wave function may go to the destructive interference, and they are kind of localized, and that can give this kind of flat band in your electronic structure. So it has this hexagonal structure. Okay, so that hexagonal structure might give you, it's like a graphene, like Dirac state or band of singularity. So the interesting thing in the system is that, let's say, spin doubly degenerate, but if you broke the time reversal symmetry, it can be singly degenerate. And if you use the spin orbit coupling, and you can open up a gap, on that gap, you can see this kind of edge state. So recently using STM in one of the 166 system, Princeton group, Professor Jahid Hassan's group reported edge state on this band gap, Zone gap state, within the Zone gap state. Okay, so we work on breathing Kagome lattice. It's kind of very new. So why breathing Kagome lattice, or what is breathing Kagome lattice? So before that, so let me talk about the motivation. So this motivation actually comes from this 2D community, where they are looking for this layer compound van der Waals transition metal can be exfoliated into the single crystal. 2D ferromagnet is basically looking for a 2D ferromagnet, environmental friendly, biocompatible, non-toxic, stable with environment, semiconductor, and good for light absorption. So thinking along that line, there's a couple of theoretical predictions saying this niobium halide, so niobium chloride, bromide, iodide, monolayer are ferromagnetic. And there's a theory calculation predicting the Curie temperature like 31, 56, 87, but in other group, they are predicting even much higher. Okay, so this work is done in collaboration with Professor Xiaodong Su and Ting Kao of University of Washington, Seattle. Okay, so what is breathing cargo lattice? So in the cargo lattice, we have this kind of triangle, but this triangle size is same into the different layer. But in breathing cargo, the bonding length in alternating triangle of the cargo geometry are different size. So this triangle size and this triangle size is different. So breathing cargo lattice could be more interesting because it has this local electric dipole moment, so potential for ferroelectric ordering. So it has gapping of the Dirac point, so potential of higher order topological phases, intrinsic topological flat band coming from this correlation. So that's why this system is even more interesting. Okay, so then this niobium iodide, niobium-based halide system, this niobium has this kind of breathing cargo geometry. You can see clearly here. So within the layer, so the center atom is niobium and is sandwiched with iodine. So this is kind of covalent bond, but between the layer or interlayer, they have a weakly van der Waal bonding. You can see it's a rhombohedral space group. So A is around 7 angstrom, but C is around 41. So C is much larger. So it's easily exfoliated. So this how you can easily get down into the monolayer. Okay, so we did the electronic structure measurement. So we kind of surprised to see this result. You see energy versus momentum. So there's a lot of flat band there. Very weakly dispersive band. You can see it's a semiconductor, so it has a band gap around 500 milli-electron volt. But you can see clearly a flat band here around 1.2 eV. So we did some sort of analysis and you can clearly see two peaks here. So there's two band and there's another broad flat band over here. So we did second derivative measurement to confirm that. And again, we have a flat band over here. Okay, so we did the first principle calculation. So you can clearly see very weakly dispersive band A and B, and there's some sort of flat band on C and D over here, very weakly dispersive band. So to prove that, we did the photo energy dependent measurement, and we clearly see this flat band is some sort of 2D nature. They don't disperse much with the photon energy, but this band around 2 eV below. So this is kind of highly dispersive with the photon energy. So it's mostly originated by 3D. So this is a more photo energy dependent data, which clearly show less dispersive band near the Fermi level, but highly dispersive band around 1.2 eV. Okay, so we also did the polarization dependent measurement, and we found that this linear horizontal, some band is highly enhanced, and the linear vertical polarization, the other band is highly enhanced. So we come up that this band A and B is strong in linear horizontal polarization. The origin is DG square orbital of niobium, and C and D is in linear vertical polarization, which is DXY orbital. So different orbital coupled differently with the polarized light. So this is the calculation, and you can see the band close to the Fermi level, this band A and B and C. So those are basically coming from niobium D orbital. So niobium is actually forming the breathing cargo lattice. But this band is basically coming from iodine P, which are mostly the dispersive band. Okay, so we also compare the bulk and monolayer. So you can see the frontier of band looks similar. Well, bulk band has more bands as compared to the monolayer, but you can clearly see this negligible kg dispersion because C is much larger. Okay, so summary for niobium iodide. So we study electronic structure and breathing cargo. So we found the flat and weakly dispersive bands. So bands are sensitive to the polarization of light, and flat and weakly dispersive band originated for breathing cargo layer of niobium atom. Okay, so I would like to thank my collaborators. So especially samples are provided by Professor Kaczorowski Group of Polish Academy of Science and Saudeng Su Group of University of Washington, Seattle. And the calculation mostly done in collaboration with Professor Arun Bansal Group of University of Northeastern University and Professor Opener of Uppsala University of Sweden in Tinkau of University of Washington. So this is my group at UCF Physics Department, and these are my funding agency who are supporting all this interesting research on quantum materials. So with that, thank you for your attention.
Thank you very much. Thank you for this nice overview over so many different materials. Are there questions in the audience? Maybe I can ask a question concerning the the palladium bismuth 2. You very briefly sketched the resistivity, which I think looked linear up to pretty high temperatures. This is always, controversially discussed, or, there are different models and so on. Can you, palladium bismuth 2?
It's just, it's not bismuth 2, it's just bismuth actually. It's a 1-1 system.
No, the 1-2 system.
Oh, the alpha, I said.
Yeah. Yeah, here it is.
Oh, yeah, this
so
one.
That looks very much
Okay,
linear
so
to me. So that's always,
yeah, so
can you comment?
yeah, so it's basically for our measuring temperature, so it looks highly metallic. I mean, if you go up to room temperature. So we try to measure around 20 Kelvin or around the room temperature. So this always very metallic. We see a lot of band over here.
Okay, but you don't want to comment any further on this linear resistivity? I mean, any
No,
correlations
no.
going on or so on? Oh, okay. Are there any other questions? Well, if not, we run a little bit over time. Thank you very much again.
Thank you for the opportunity.
With this, we close the session and thank all the speakers in the session. Thank you very much.
Liang in Taiwan. So, what is type 3 superconductivity? In the first few slides of this talk, I will try to give you what I can define the take-home message, the key features of this, what I mean by type 3 superconductivity, and in the rest of the talk, I will try to, without going too much into detail, to show how all these arise. In this talk, I will use a relativistic notation for simplicity, although, as we heard yesterday from the talk of Carlo Trugenberger, the correct formulation of this problem should have been done on the lattice, where an ultraviolet cutoff naturally arises. So, what is type 3 superconductivity? Let me start from superconductivity, and I read there a field theory's perspective. What I mean by a field theory perspective, what I mean is that I will not use a microscopic approach, but I will use a long distance effective gauge theory approach to catch the essential features of the problem that I want to study. So let me start with 3+1 dimension. If I'm in 3+1 dimension, I want to describe superconductivity in this way. I can do this using the word of Weinberg. So a superconductor is simply a material in which electromagnetic gauge invariance is spontaneously broken. If I take this point of view, what I can derive immediately is that I have the screening of the electromagnetic field. I have the Anderson-Higgs mechanism. I can construct a phenomenological model, the Ginzburg-Landau model, to describe superconductivity, and I have the Meissner effect. In 3+1 dimension, I want to stress also that Coulomb interaction in this game, they are subdominant. Now, what happens if I change dimension? Let me move to the 2+1 dimension. And first of all, let me define what is for me a 2+1 dimensional system. So what I will talk about are superconducting films that have a thickness d that is comparable or smaller than the coherence length. Now, if I do this, the first consequence that I have is that the screening length become comparable or even bigger of the size of the system. This is an example, for titanium nitrates. And the system that I want to describe are systems that harbor the superconductor to insulator transition. And what is the consequence of this? The consequence of this is that the dielectric constant is huge. And having a huge dielectric constant has the consequences that the electric flux lines are confined on the plane. And so what I have is an effective 2D logarithmic potential, a real two-dimensional Coulomb potential between charges on scale that are between d and this screening length that is epsilon times d. So what I will show you is that in this condition, the Landau-Ginzburg model cannot describe superconductivity. So what fails? Now, Coulomb interactions are important, and so what I have is that if I couple electromagnetism to the Ginzburg-Landau model, what I get is 2+1 dimensional scalar QED. Now, this 2+1 dimensional QED is a theory that is plugged by infrared divergency. I have the coupling constant, the scale, like the size of the sample, divided by a scale. In this case, I took C. This was shown by Jakiv at Templeton. So what I have is that the system is forced to break in droplets. Droplets that have a size that is comparable with this length scale that I have here. And so what I have is, due to this infrared divergence, my system cannot be homogeneous, but must be granular. And this granularity in film, as Carlo Tugendberger showed yesterday, has been experimentally observed. Now I have droplets in which I have local superconductivity inside described by this Gisborne-Landau, but I need a mechanism that will give me global superconductivity, and this global superconductivity will be realized when I can establish a global phase coherence over all these pre-existing droplets of condensate. Now, in this system, what I have is that Cooper pair survive above the critical temperature, and what will cause the destruction of the superconductivity will not be the breaking of the Cooper pair, but will be the proliferation of vortices. This will be Josephson vortices. Carlo Tugendberger introduced yesterday the Josephson vortices. So the transition that I have here will be a Berezinski-Kosterlitz-Thouless transition. So here is what happened in my films. They break down in droplets. And what I can have channeling between these droplets. And these droplets are characterized by condensate and a phase. And when this phase formed configuration like this, I have what forms is a coreless vortex that is called Josephson vortex. And this is very similar to what happened in Josephson junction array. And in fact, what we have is that the theory that describes this type of superconducting system is the same that describes also Josephson junction array. Now, I told you my system breaks in droplets, and I have to have a mechanism that gives me global superconductivity. To have global superconductivity, I have to have a mechanism that works to screen my electromagnetic field, so I have to have a mechanism of mass generation. And in 2+1 dimension, I have two ways in which I can generate a mass by screening of the electromagnetic field. The first one is the one we heard yesterday, namely through instantons. And these, we have seen yesterday, give rise to the state of matter that is called superinsulator. And the other one that will be relevant for us is the generation of a mass through a mechanism that is alternative to the Higgs mechanism, and it's called the Chern-Simons mechanism, or BF mechanism. BF is not an acronym, it's the name of the theory. So this is a topological mass generation. Now, I thought about 2 dimension, but is this limited to 2 dimension? No, the answer is no, because this mechanism of generation of topological mass can be extended to any dimension. And moreover, it has been experimentally found that granularity is not confined to films, but it can exist also in bulk sample, and it has been found also on the ground state of ITC superconductor. And what I will show you is that, in fact, what we can have is a generalization of the Biquet-Tree transition to any dimension, and in particular, in 3 dimensions, this Biquet-Tree transition will become what is called the Fokker-Fourier-Taman transition. So what I said for film in 2 dimensions can be extended to any dimension, in particular to 3+1 dimension. Now, okay, this is the take-home message. Now let's see into a little bit more detail, how this mechanism of mass generation that is crucial to obtain the screening of the gauge field works. Now, let's start from 2+1 dimension, and let's consider the usual Maxwell action, F mu nu, F mu nu. We all know that we can give mass to this gauge field through the Higgs mechanism. I can add this term with the covariant derivative, and I have 2 possibilities. I have an unbroken vacuum, in which I have a complex scalar field that has two real massive degrees of freedom and one massless gauge excitation. Now, if I go into the broken vacuum, my gauge field become massive, and I have, so I have 2 degrees of freedom from that, and I have massive chargeless Higgs boson. This theory respects the PAT symmetry, parity at time reversal, and this is the phenomenological theory that I was discussed before for what is called, let me call it standard superconductivity. Is this the only way? No. Deser, Jakiv, and Templeton show us that you can, instead of adding this term, you can add a term. Here you have the gauge field. So you see you have a new term that is a term that is quadratic in the gauge field, but contain only one derivative. So it's a term that is dominant at large distances, and in which the index are contracted with the totally antisymmetric tensor. If I add these two and I compute the equation of motion, what I see is that a mass appears. Remember that in 2 dimensions, this object has the dimension of a mass. So a mass term appears, and I have that my theory describes a single degrees of freedom that has a mass. My gauge symmetry is not broken. And if I will compute the Gauss law, I will see that this term has the peculiarity of connecting electric and magnetic fields. So magnetic fields are as a source for the electric field and vice versa. And if you look at this theory now, what you have is that this theory breaks P and T symmetry. And so this theory combined together was used as a phenomenological theory to describe, for example, the quantum Hall effect, or was used for what was called anion superconductivity, when it was believed that anion superconductivity was a T-breaking theory. Now, let me just stress another characteristic of this term. If you take this term by itself, it doesn't describe any dynamics. Its Hamiltonian will be 0. It describes invariance of curves and oops, sorry. Okay, so it's a term that so this Chern-Simons term, pure Chern-Simons term, is a term that do not describe any dynamics. And so, as we will see, when we use it in physics, we should add other terms that introduce the dynamic for us. So my films, the system I start with, is a system that doesn't break PAT. So can I use this topological mechanism by having PAT symmetry? Yes, I can use this topological mechanism. And the way I can use this topological mechanism is if I write this Chern-Simons term, now here I write it in Euclidean spacetime, if I couple a vector and a pseudo-vector field. If I do this, and then I will check the P and T symmetry, this theory respects P and T symmetry. And this is what is called the mixed Chern-Simons theory, or BF theory. Now, again, I should add the kinetic term for the gauge field A and the gauge field B. These are these two terms here. And I will have the analog of what I had for the Chern-Simons, pure Chern-Simons theory in terms of two gauge field. Now, as I told you, we want not to be confined to 2 dimensions. So let's see if I have a way to generalize this term to higher dimension. And the way it exists in 4 dimension, 4 Euclidean dimension, epsilon has 4 index. So if I want to have one derivative only, I need to have an object that can saturate 3 index. So what I do is I take a vector field and I couple with a pseudo-tensor field. And this is what is the BF theory. And this is the generalization with the kinetic term add. This is just the equivalent of the Maxwell term for a tensor field. And this is, again, the Maxwell term for the A field. This action was originally in 2 and 3 dimensions, was proposed by us, Pasquale Sodano, Carlo Trugenberger, and myself, back in '96 to describe topological phases of matter. Now, what are the characteristics of the Chern-Simons and the BF action that I wrote is that, again, the two emergent gauge field, or the gauge field and the pseudotensor gauge field, acquire a mass that is given by this expression. The coupling of the Chern-Simons term is always taken dimensionless. And now if you would look here to the coupling constant that you have, you will see that they have the dimension of the mass. In 2 dimensions, they are naively irrelevant, and in 3 dimensions, this one is marginal, while the other one is still irrelevant. And so what you will think is that this, if I go back, so these 2 terms will not influence the phase diagram. This is not true. And this is due to a peculiarity of this Chern-Simons term, and from the fact that if you want to correctly define the pure Chern-Simons limit in which the topological mass goes to infinity, you see that these terms are necessary because the quantization of the theory will not commute with this limit. So these terms are relevant, they play a crucial role, especially what plays a crucial role is the ratio, the dimensional ratio between these 2 coupling constants, as we will see. Now, where this theory, I wrote down this topologically massive theory, and now I would like to see what is the connection of this theory with my system. I say that I want to describe a system that have the superconductor to insulator transition. So let me try to see how can I describe a theory, an effective theory for this system. I know that in this system, the relevant degrees of freedom are Cooper pair vortices. This has been told us by Fisher. And what I know is that I have these 2 quantities that both in the film interacts logarithmically. So I have competition between these 2 quantum orders. And what I have is that these Cooper pair vortices interact through they have a topological interaction, and that is the Aharonov-Bohm-Kasher interaction when you have the world line of a charge that wraps around the world line of a vortex. So what is this topological interaction is the interaction that is dominant at large distances. And if I want to write it, this is the linking number of these 2 curves. This is written in this way. Now, this is non-local, but Wilczek has shown that we can write this interaction local at the price of introducing 2 emergent gauge fields. So I have my theory for the SIT that is dominated by the Aharonov-Bohm-Kasher topological interaction, and I arrive at the local formulation in terms of the 2 emergent gauge fields, in which one is a vector because coupled to charges, and the other one is a pseudo-vector because coupled to vortices. Now, this is not the end of the story because, as we said before, this term does describe any dynamics. If I want to, so I need to introduce the dynamics. If one wants to be really precise, one should say that this term needs a regularization because it has a 0 mode. But we need to add the dynamic. So if I add the dynamic, the next term with the minimum number of derivative and that respect gauge invariance that I can add is this term here. So as you see, I obtain the action that I had before, in which F mu describe fluctuation of charges, is a charge current fluctuation, and G mu is the dual quantity in terms of vortices. Now here I have wrote the coupling constant SEV and AQ because now I'm describing films that have a seat, and I can relate this parameter to the energy scale of the droplets and to the magnetic scale of the droplets. And I can trade these two parameters for a massive parameter, my topological mass, and the ratio that I was telling you about before between these two parameters. And this ratio is the ratio between the electric and magnetic interaction. And when one dominates or the other one dominates, I will get the different phases. Now, to obtain the phase structure, I will have to couple this with the real electromagnetic field and compute the induced action. But just before doing this, let me see, this will be the analog of what I have done in the case of the 3-dimension, with the only difference that now what was the current of vortex that had just one index become an object with two indices, because in 3 + 1 dimension, vortex are one-dimensional objects and describe a world surface. Okay, if I compute the effective action, this is the phase diagram that I obtain with the parameter eta that naturally appear in our description, and this is G. So you see when G is bigger than 1, I have the phase in which the charge dominate. This is the phase in which vortex, the contrary, vortex dominate, charge dominate. So I have vortex condensate, magnetic monopole condensate, and charge condensate. And in the middle, I have a phase that can appear. You heard everything about this phase yesterday. Let me just stress that this phase in between that appear when this parameter eta is bigger than 1, it's a phase in which this topological interaction that is being ignored plays a crucial role and screen both charges and vortex interaction, and these are both gapped interaction. Okay, 5 minutes. Okay, so let's concentrate on this phase, X-less superconductor. What is an X-less superconductor? This was introduced originally by Pasquale Sodano, Carlo Turgenberger, and myself in 2006, and studied again in 2017. So what I have, if I look at the effective action, the term, the vortex-vortex interaction in the effective action that I was telling you before, normally this interaction is screened by the topological interaction. So here, sorry, the minus sign should be here. So I have the screening of the vortex interaction, and now since I'm in the charge condensation phase, if I look to what happened to this term in the charge condensation phase, I see that the screening is suppressed. The fact that the screening is suppressed and that they interact with the inverse of with the Coulomb potential means that leads to a logarithmic confinement of vortex. And if I do the same thing for the 3-dimension in which I have world surfaces of vortices, again, I see that normally they are screened by the topological interaction, but the charge condensation, again, suppress the screening. So again, if I will look at the analog of the Tufte loop for surfaces, I will see again that these vortex are logarithmic confined. So the phase, in this X-less phase, X-less superconducting phase is characterized by logarithmic confinement of vortices in 2 and 3 dimensions. And the transition is given by vortex liberation. Now, let me see what is this effective action in this case. Now, I know that vortex are confined, are dilute, so I can write down my action, and this is the action that I obtain. This is the field that is connected to the charges when I solve the constraint, and this is the real electromagnetic field. So you see that I have a Maxwell term for this term, for the charge here, a Maxwell term for the real electromagnetic field, and these are coupled by a Chern-Simons term. So again, I found that topological mass generation for my electromagnetic field, and I have a screening length that is given by this expression. And the transition is given, as I told you, by the proliferation of vortices. In 2 dimensions, I have a BKT transition, so the liberation of vortices, and the scaling that I will have for the resistance is given by this expression. If I will play the same game in 3+1 dimension, what will be the analog is the vortex as a string, the string as a tension. So what will be the analog of this transition will be the fact that this string becomes tensionless. And the scaling of the resistance in this case has been computed in collaboration with Luca Gammaitoni, Carlo Truggenberger, and Valery Vinokur. This is the scaling that you get, and this has the same form as the Folger-Fulken-Taman transition. So this is the new scaling that we have. And this scaling has been observed experimentally by the group in Taiwan. So here is the experiment done on niobium nitrate of 20 nanometers of thickness with coherence length of 4.2 nanometer. And this is a similar experiment done on a thicker sample on niobium titanium nitrate with the thickness of 10 nanometer, coherence length of 10 nanometer. As you can see, we have plotted in blue, in red, the scaling with BKT scaling, and in blue, the Folger-Fulken-Taman scaling, the same here. You can see that, so blue is the Folger-Fulken-Taman and red is the BKT. What you can see here clearly is that the more the system becomes thicker and three-dimensional, the more the Folger-Fulken-Taman scaling better describes the experimental result. And thank you for your attention.
Christina, thank you so much, and we have time for a couple of questions.
Just trying to understand how different from the XY model your theory is. So in 2+1, for example, if you would integrate out the vortices and just look at the theory for the charges,
okay.
How different would that be from the standard XY model that we all know?
The theory, our theory is completely different from an XY model. You see it clearly here. It's a theory, okay, in which the crucial point is the topological interaction, Aharonov-Bohm interaction between charges and vortices. Okay, so this theory is not an XY model. Now, you say you want to integrate the charge?
That's right. What's left?
Okay, so if you integrate the...
Not the charge, but the vortices, for example. So theory for the charges would be XY model ordinarily, but
okay,
what is yours?
You will get a theory if you integrate... You want to be in which phase? Sorry, in the phase in which you have a condensate of vortices?
Yeah, whatever.
Okay, in the phase in which you have the condensate of vortices, you will start with the theory, okay, in which you have a condensation of vortices. You will have these vortices, okay, as Carlo Truggenberger showed yesterday, liberated in this phase. You have the liberation of the instanton that are in a plasma phase. And so what you will get is a linear potential for charges.
Well, I understand that. I understand the description of phases. But my question still is, just if you integrate one of these two fields, either vortices or charges, what's left would be some interacting theory for whatever is the left degree of freedom.
This is, okay, when you are in the phase, you start with the theory like this for vortices, okay? You are in the phase in which you have the charge condensation. You have this theory for vortices, you have the charge condensation, and you get this theory for charges.
Maybe I can answer that question directly. If you integrate out one gauge field, in one case you get the pro-Lagrangian, in the other case you get Polyakov's compact QED. This is quite different from the XY model.
No, I agree it is different. My question is exactly that. What is the difference?
I just told you. In one case you get the pro-Lagrangian, in one other case you get Polyakov's compact QED.
Okay.
Maybe I didn't show it very well. I didn't brought this formula, but in this case, as I told you, here you generate a linear potential, so you have a confinement. In this other phase, you do not have a linear confinement. You have in 2 and 3 dimensions, you have a logarithmic confinement, and if you go a little bit beyond this, you can use what is called, you can promote these forms to a 2-dimensional tensor field, and you derive what is safe.
I got it. So the transition would be first order, presumably, between these two phases.
Oh,
right?
This transition here,
yes.
This is a first order transition. You have is a first order, but these two here are in 2 dimensions. They are BKT transition, even at 0 temperature, and they are Folger-Fulken-Taman transition in 3 dimensions. So the key point is that you have to have these vortices and charges. And if you take the XY model, you would take only vortices.
That's right. That's right. Yeah. Thank you.
Okay. One quick question, if any. Ali, please.
Just a curiosity, I say, okay? Just a curiosity, maybe you can answer too. We used to work on YBCO a long time ago, and the oxygen content is very important. Then it becomes antiferromagnetic or superconductor at a critical point for something, oxygen content. What if we were able to make a monolayer or 2-dimensional 1-layer YBCO? And how could you correlate this work to this possible experimental study?
So you want to have a layer of
YBCO with the controlled oxygen content.
By one
elementary
layer,
cell, you mean?
Yes.
So 2 layers. 2 planes.
Yes, 2 layers, yes.
But 2 planes.
Two unit cells on the top of layers. So let's assume like that. Yes.
So you have 2
unit cells.
2 units. Okay. This is what Carlo was explaining yesterday. This okay.
Oh.
Here.
How did you steal my idea? I know.
Oh, it's okay.
So the point here is that that system for us will be 3D, because you have 2 layers, so I consider it as 3D. And in this theory here, we used yesterday, we talked about monopole and charges, okay? Now, if you take this theory here, and this is not the only thing that you can do, you could add another term that is called the theta term, that is FF dual, and the effect of this theta term is to give charge to the monopoles, and you can play a game very similar to this game that I did, and you will see that you have a phase in which this object that is charge plus monopole condensate, and this will give rise to an oblique confinement phase that, as he was explaining yesterday, is what explained this pseudo-gap state in ITC superconductor. So, but I don't know about the contact with oxygen.
Turned it off. Oops.
Maybe I can just answer it. What she's trying to say is that if you just modify this a little bit by adding a topological term, this leads to the model of the pseudogap and high TC that I spoke yesterday briefly. So
but
it's
I
very
don't know
important.
if the oxygen, what is the...
Basically, this one layer thing is not going to be different in superconducting properties from the bulk material.
Yeah, it's 3D, that's why, yes?
Yep.
Okay.
Exactly. Thank you very much.
It's a pleasure.
And
Christina,
don't go away. And now we like to invite the second speaker of the session, Javad Shabani, induced superconducting pairing in integer quantum Hall edge states. Is it remote or?
No, he must be around, either in the C or I don't know.
He must be around. He's okay.
Okay, hello. I'm sorry, I was getting ready.
Good.
Okay, thank you for inviting me to be here. It's a great pleasure, and it's my second time in Turkey after Antalya, and that conference was also fantastic. So today I want to tell you a little bit about topological quantum computing as being a very far goal and how we are trying to build up toward that goal, and how it actually passes through the old quantum Hall physics that we all know as one of the most robust topological systems. So this is the work of my group, in particular Mehdi Hatefipour, who actually pioneered a lot of this work in my lab. Okay, I'll get used to this. Perfect. So, okay, that wasn't me. It is going down. One time. Okay, I will just keep. Okay, press harder. Okay. So very briefly, I want to kind of motivate quantum computing again and why we think the way we think. And yesterday there were beautiful talks by Irfan and Roland about kind of the topological aspects and superconducting aspects. But I think this is a very generic line of thought that if this is the merit of quantum computing, how fast we can compute, the power of computing, and this is the number of years, what we should appreciate is that when technology changes from vacuum tube to transistors, we definitely have more power in terms of computing. Then we went to integrated circuits. And now there is this next generation thing that will come, and that could be quantum computing or something else. But I did not press anything. Okay. So what would that be? And again, I think based on Moore's law and everything getting smaller, the quantum technology is probably the most relevant technology to look at, especially in solid state in my mind. A very brief overview that I would like to connect to quantum Hall later on and discuss why I think it's a very interesting system is that the qubits are basically a two-level quantum system that we describe by Schrödinger equation. This is a 101 type description. But what I like to emphasize is that this two-level system is separated by an energy, but those energy levels could be also broadened. And that is usually related to disorder or dissipation. So all the qubits that we have talked about so far, these are, I would call them, again, first generation in the sense that you will find a two-level system in your materials that you like, diamond vacancies, ion traps, and these are perfect quantum systems. The problem is that there is no intrinsic protection from relaxation or decoherence. We basically found the first two-level system we could, and we are trying to kind of operate it as a qubit, which is great, and we have made great progress in the last 10 years. But to go now to do the harder thing, the stuff that Irfan was talking about yesterday, now these things are basically opaque. Anything can harm them, the cosmic ray, everything. And because the information is basically placed in such a small and simple system. How can we look at this problem in another way? When things are very small, they are prone to error. A very poor man's version of showing this is that if I have a length scale problem, and this is atomic scale, and this is macro, and I know that the small things I can have quantum theory, I can ask an interesting question. I can say, what is the longest length scale that I'm completely dominated by quantum effect? And instead of going Moore's law that was classically pushing me this way, now I'm asking a new question. I'm saying like, can I be at millimeter and have quantum theory completely dominant? If that's true, can I have a two-level system at that length scale? And at that length scale, my resolution of like 10, 20 nanometer of avionics or nanofabrication or whatever that we use is just very, very sophisticated for that length scale. But if I want to control like a 2 angstrom NV center, then I'm kind of out of tool unless there are some accidental stuff. And in reality, there are things that actually work in millimeter scale. Like quantum Hall effect, you can make a sample that are like 5 millimeter and you're still going to get a quantized value. You can make a superconducting cavity that is also few millimeter and it still works. And going back to my very simple qubit picture, you basically need to beat these two things. The temperature has to be small enough that you can resolve the two-level system. Your dissipation should also be much smaller than the energy scale. In superconductivity, that is easy. This is 0. And you basically cool down to below TC. If your energy level is good, you're done. Quantum Hall is kind of the same thing. If the material is clean enough, like gallium arsenide, 30 million mobility, basically all of this checks out. And if you look at it in this perspective, there actually has been a handful of, I would say, Nobel Prizes that went to this direction of how we can actually get the quantum effect into larger length scales, whether by accident or was by design. So great. So we have things that do not have any intrinsic protection. We have things that now the quantum is taking them to the longer scale. So what can we do? Can we make a second generation qubit that basically are in this new regime? And that's indeed, I would say, the last 3 years or 4 years of qubit research is going toward that direction with a name called protected qubits. These are the qubits that you basically make the Hilbert dimension like redundant, so when the error comes in, it doesn't like scramble your information. The most famous one is CatCode that came out from Yale by Mazjami Rahimi and Michel Devoret and Rob Shokov. And this is one of the best, I would say, qubits that we have these days. There are like at least 10 of these different variations. But then there is also this topological version. And these topological versions come in a variety. I guess the most famous one is Majorana fermion that we discussed. But that's not the only one. And I will show you in a second that that's why that is the case. But when I say topological, I basically mean that I have a degenerate manifold at the 0 energy. And if the operation is that I get these two particles and basically bring them down, and somehow a truck is passing by or I have some noise in my system, and this line becomes wiggly, topologically I've done the same thing here as I was supposed to do it there. Or if I am supposed to braid this thing, this would be sort of the equivalent picture of that. And because of that, this is much more forgiving for quantum computing compared to actual qubits. So what should I do? So the work originally in quantum Hall effect in terms of non-abelian physics and Pfaffian started with Reed Green, and then by Adi Stern, by Kitaev. The best translation, at least for an experimentalist, is this paper by Chetan Nayak in 2008 that basically they put everything in sort of one concept of how non-abelian anyons and topological quantum computings are related. And going through this paper, you can also create these kind of mountains of milestones in very long scales, time scales, that basically starts with, we first need to find a system that hosts non-abelian physics. That is Majorana in a nanowire, that's something on quantum Hall, whatever that is, we need to figure out those systems and engineer them. Then we have to control the Majorana. We have to be able to move things and braid things. Majorana will only give you 2 gates out of the 4 gates you need for universal quantum computing. Parafermion will give you 3 protected gates, and Fibonacci will give you all protected gates. So even getting Majorana, that's although it's fantastic, it's not the end of the game. This thing will continue. But today, as Irfan showed on his last slide on the Alps, we're talking about just how we're going to design our experiment to get to this kind of physics. So what are anyons? I keep saying anyons. If you haven't heard about it, this is actually nothing very particular. If I have a many-body system and I exchange 2 particles, I and j, together, you can define it as an operator. If I pick up a sign, like a minus sign, that's a fermion. That, it's just Ashcroft-Mermin type things, right? If the sign doesn't change, that means all the particles are identical. I have a boson. So this is very standard in condensed matter. Anion is basically systems that will pick up this operator is a phase. So for example, if theta is 0, this operator becomes 1. If it's pi, you will get a -1. But it could be anything. It could be pi over 3, right? So all of these, these are all abelians. But because they can get any phase, we call them anions, basically any phase particle. So that's great, but this is proven that is not very useful for quantum computing. What you want is an anion that also has a non-abelian behavior, a statistic. So what does that mean? Good. So this was the standard anion. The non-abelian version is that you can no longer have a phase change when you exchange two particles. Basically, it means that that unitary is not just a diagonal e to the power of I theta. It's basically a matrix, and that matrix is very unique to the physics we're discussing. If it's Majorana, it's going to be something. If it's 2 pairs of Majorana, it's going to be different than 5 pairs of Majorana. So in case of 2 pairs of Majorana, if you basically define your qubit state by basically the digits that are the occupation number of fermionic mode, 0011, the standard qubit system, and you calculate the unitaries in this system. Basically, U12 means I change Majorana 1 and 2. These belong to the same chain. And then there is another one that basically is 3 and 4. So 1 and 2, you can easily see that basically is diagonal and is a phase. So that's not going to give you anything interesting. But if you do connect the chains, if you try to braid the 2 and 3, now you can see you have off-diagonal elements. That what it's going to do is that if you just apply it to your ground state, 0, 0, it's going to take you to a superposition. That's exactly what non-abelian physics will give us at our manifold. That's fantastic, but how can we actually get one? So there are many, many proposals out there. It actually, a lot of it started with 5-half physics in quantum Hall effect. Atomic chain we heard about yesterday, nanowires, this is my research, mercury telluride. But today I want to talk about this particular proposal. This proposal is trying to basically, I guess, discount the 5-half requirements. The 5-half physics only shows in gallium arsenide under really low temperature and highest mobility, and the gap is almost only 300 millikelvin. But if we somehow move that to an integer quantum Hall effect, then we can actually use a lot more bandwidths in terms of controlling it and the stability. The price we pay is now we need a superconductor to actually interact with quantum Hall effect. So there are a series of proposals that actually came maybe too early before the experiments could actually try them. But then later refinement on these proposals basically identified that this very pictorial picture has to be different in a way that you put a superconductor in the middle of this Hall bar. This is n equal to 1 with one chirality. There is this chirality, which is the same, but now you have two opposite edges that are going to basically be coupled through a superconductor. And that's exactly what will give you a Majorana physics. How do you do parafermion? In the other proposals I showed you, like the atomic chain, there is no way you can do parafermion. Here, if you change this n equal to 1 to 1/3, you get a fractionalized Majorana, and that is basically parafermion. So that's quite straightforward here. Okay, so I need a superconductor talking to my quantum Hall effect. And what I need as a precursor is to see Andreev states, right? Basically, I want Andreev reflection in magnetic field. To just remind you what is an Andreev reflection, at zero field, you get an electron hitting on a superconductor, a hole is going to come out, and a Cooper pore is created and goes inside the superconductor, right? In a very naive semi-classical picture, when magnetic field is no longer 0, this is the scenario. The electrons in an edge state mode will come to the superconductor. They become a hole, so they now have to have another, basically, circle. They go back to electron, and then they kind of hop and back and forth, right? Quantum mechanically, I have to write that as a superposition. I can't write it as a, basically, a hopping. So what do I need? I need to interface superconductor with my quantum Hall. We have done a lot of epitaxial work of how to put superconductors on indium arsenide with great quality. And we can show that we can get transparencies that are exactly 1. Okay. So this was supposed to be a video, but basically we have 2 decks at the surface. If you want your superconductor talk to your 2 deck, the 2 deck has to be at the surface. The mobilities are around 40,000. You can see a couple of quantum Hall states, and we use niobium tinitride here on top of the aluminum, and that critical field is about 28 Tesla. So we can actually cover the whole range of quantum Hall effect here. So this is the device. It's basically a Hall bar. Indium arsenide is green. This is niobium ti. There is a gate voltage that covers everything, so we can change the density here. So what do I need? What do I expect? In a very simple quantum Hall system, when all the contacts are great, you basically measure 0 for your RXX or longitudinal, and then you measure the Hall data for your Hall measurement, basically when you measure across. When I change one of these contacts with a superconductor, now I have to actually include the effect of Andreev reflection. So this is kind of a modification on Buttiker formula that basically my reflection plus T that was 1 for normal contacts, now I have a contribution from the Andreev states. So basically the bottom line becomes that for Andreev states, I didn't touch it, okay, is that you basically, the Andreev parameter enters your Hall data and your longitudinal resistance. And what you would expect, I will just cut for time, is that in an ideal case, when Andreev reflection is perfect, and instead of 0, you will measure minus h divided by 2 square. And in the case of, again, perfect Andreev reflection, you measure half of the Hall data. So Hall data goes from this value to half of it, and then the RXS goes from 0 to minus that half. And if it's non-ideal, you get kind of sit somewhere in the middle, right? You basically will be between 1 and this basically factor of 2. So we make these devices. We actually put a great care in terms of getting these interfaces right. So this is the interface, almost like the optical image I showed you. We measure RXX, 2 normal contacts. Current goes from one side all the way to the other. This is magnetic field as a function of the top gate voltage. And you see the integer quantum Hall effect is very clear. The resistance goes to 0, everything is normal. Now what I would do, I would actually measure across this interface where there is Andreev reflection. So now if you look at the same graph, now basically I'm just plotting this downstream. This downstream is between 5 and 4 prime. And now you see these strong blue color regions, exactly where the quantum Hall is supposed to be. These are now at minus almost 1 kilo ohm. So now we see a very negative resistance when we look at across the interface. So that's promising, at least within the Buttiker formula, that's exactly what we expect. If you want to see it better, I can get a line cut at 11 Tesla, and this is RXX on basically gray line, as you see, and then blue is across the interface. And as you see, blue, whenever it's supposed to show a quantum Hall effect, it actually goes to a negative number. Right? What about Hall data? I also said Hall data has to drop. So Hall data, the black is again the standard Hall data in the middle of the sample. The blue is across the interface, and as you see, whenever we get to a quantum Hall effect, the Hall data basically drops below, right? And that difference is exactly that difference. If you add them up, you recover the Hall data. So what if I actually measure farther? Like I measured from 4 to 3 and then 4 to 2. If there is no dissipation across the quantum Hall, basically the resistance shouldn't matter. And as you see, basically blue and red are such experiment. Red is as 4 times L, the blue is 2L, and as you see, the quantization value somehow doesn't change, but then the graph's obviously very different above that value, right? So once you are basically getting to the Andreev reflection, that number is fixed, determined by that interface, not the length and the contact or the normal contact variation. So if you believe on those data, basically the formula of this Hall data, I basically said is relevant to the Andreev reflection. I can basically plot these lines and then basically as a function of different field, deduce an Andreev coefficient. The Andreev coefficient we find is basically 20%, which is quite high for a system that is basically operating at 10 Tesla. If you compare to graphene data, basically they get 1% almost. And here the advantage is this epitaxial contact that we can make to our indium arsenide. We also got worried that maybe there was something wrong, maybe this was an accident, whatever. We made like 8 or 9 samples, and in every single one that the interface is good, we actually observe a negative resistance. And the variation comes from the fact that how perfect is in the interface. When the interface is clean, you see the highest negative number. when the interface is not clean, deliberately you don't clean the interface and let it oxidize in air and you put it in the chamber, now you see that there is this number drops to 8 ohm instead of minus 800 ohm. So it's a direct interface problem. You compare it to graphene data. This is our data. This is the data by, I believe, Duke. And then you see that basically minus 100 ohm versus minus 800. These are also minus 20 ohm or so. So basically, I think there is a direction that a lot of people are kind of following in quantum Hall effect by adding superconductors, niobium nitride, molybdenum rhenium, and niobium tinitride that we did. And I think the best Andreev reflection has been achieved by us. So why all the qubit business? The topological gap at the end of the day is going to be very important. So what we did actually in one of these experiments, we basically put a QPC right across that interface. So half of the QPC is covering niobium ti, half of it is covering 2DEC. So by this operation, now I can look at the induced gap at the quantum Hall effect in niobium tinitride. And this is the number, 700 microvolt when you are at 6 Tesla at the quantum Hall effect. So this 700 microvolt, you have to compare it with these Majorana gaps from Microsoft and other people that are only on the order of 20 microvolt. So if we can actually create Majoranas in the system, this would be a great host because the topological gap is already strong. So we see another experiment you can do here, which I'm going to briefly mention, is that if you have edges coming up this, some of them can go through the QPC. With QPC, you can actually allow the select number of modes that go inside or get reflected back. It's basically your tunable mirror. And if they go inside and get reflected back as a whole, you kind of see this quasi-hole that comes out that can actually now interfere with the electronic system. And the result is an oscillation around the quantum Hall states when you go to 0. So we are actually studying that. Let me just skip this and get to the summary. So I think we have managed to basically make this niobium tinitride indium arsenide with really high quality interface. We observe this negative resistance that actually matches the presence of Andreev reflection in these systems. And we also have found these Andreev reflections can get up to about 15 to 20%, which I would say is the record number for these systems. So now we are trying to actually go to the next level, which basically is now coupling different quantum Hall states together. Thank you so much.
Okay. Thank you very much. Perfect timing. And okay, please, questions.
Yes. I have a question. You mentioned the non-abelian anions, like for example the 5 halves states. Do you know if the non-abelian character has been explicitly, experimentally measured?
I don't think so. I don't think a non-abelian character has been measured in any system.
Right.
Even if on the Majoranas, if you cannot fuse them to get the algebraic relationship, or you break them, which is harder than fusion, there is no way to say that these are non-abelian or not, right? So basically, if you fuse two of them, whether you get MT or you get I, right, the psi daggers. So that experiment has not been done on anything. Even on nanowires, it hasn't been done because you need two pairs or two anions deterministically to fuse them, right?
Correct. So I just wanted to point out that even for the simpler series, it's not even clear now if the anions are abelian or non-abelian. There are two competing series. One is Venn Chern-Simons theory.
Yeah.
One is a theory which is based on W algebras, which gives non-abelian character already at 2/5.
I see.
So maybe one can use even simpler.
12/5, I see. Yeah, yeah.
But
No.
I think nobody has established if measured.
No, indeed. I think in quantum Hall, especially on 5/2 and 12/5, the gaps are so small that even measuring a gap is not right. Making a mesoscopic thing, which is an interferometer, that's even harder. And on gallium arsenide is almost impossible. So the hope is that with this superconductivity, you mimic that physics in a regime that you have more control. You test it. It could be a failure. It could be a positive signal. So we'll see.
More questions? Then maybe I have a completely different question. Since you seem to use niobium nitrate there,
Niobium tinitride.
yeah, you can expect that when you make qubit, at long last, it will be very well coherence protected. Is that correct?
Right,
Because
yes.
you have huge kinetic inductance because of this, so what's your, like, if you have some estimate for?
Right, right. I mean, if you find out, going back to the first question, if I can show this is non-abelian, I think that's already, a great achievement, right?
Yeah.
To make a qubit is just going to get 10 times harder, right? And the reason is that on top of everything else, my runners are not infinitely long, right? The coherence lengths of my runners are actually disrupted by the quasi-particle poisoning. Because once basically we lose the parity in our manifold, the topological protection is gone, at least the way that we have defined it. And that basically is a random particle that comes to the gap. Niobium tinitride is one of the worst because it's a granule superconductor. If you want to get the best quasi-particle protection, you go to aluminum. But then aluminum doesn't survive the field. So I would say this is a toy experiment for non-abelian physics if it's there. And if you want to make a qubit, you basically have to drive this back to the zero field. And again, I guess there was a talk by some quantum Hall anomalous physics or some material that at zero field can work with things. And then you can bring aluminum back and then go from there. But those materials are not as ready, I would say. And then here you have a very, very established quantum Hall physics, which is understandable. So it makes the interpretation a little bit easier. But once you work at 10 Tesla, I mean, there is almost no hope for making a qubit either way.
Thank you. Okay. Well, more questions? Well, if not, then we have to thank the speaker.
Thank you so much. Thanks.
Thank you very much. And now we are going to the conclusive talk at our session, which is Michael Nicholas. Insights in the superconducting phase diagram of strontium rubidium oxide from thermodynamic measurements under uniaxial pressure. Should be quite experimental.
Do you hear me? Okay, so first I want to thank for the invitation, and I'm happy to be here after last year where I could just give a virtual talk. So I will talk about our insights on the superconducting phase diagram of strontium rusinate from thermodynamic measurements under uniaxial pressure. And okay. Good, I will first give a brief introduction and then show you two experiments taken on the same sample, basically a heat capacity measurement and the measurement of the luster-caloric effect, and at the end I will summarize. So when we look at different classes of unconventional superconductors, for example heavy fermion, high TC cuprates, iron-pnictides, or even the organic superconductors, we always find a magnetic phase in proximity to the unconventional superconducting phase, independent of the underlying physics in these materials. So one outlying example here was strontium rusinate, where there was no indication of a magnetic phase nearby so far. But I will show you that this changed. Oops. Okay, so what are we doing? We are using hydrostatic or uniaxial pressure to tune quantum materials, because in that way we can do a clean tuning without introducing additional disorder by substitution or doping, or we are also not polarizing the material by using the magnetic field as tuning parameter. And in particular, uniaxial pressure can also break lattice symmetries. For example, when we have a tetragonal system, like in the case of strontium rusinate, when we apply uniaxial strain along one of the axes in the plane, we break the symmetry and go from a tetragonal to an orthorhombic material. So strontium rusinate was the first non-cuprate layered perovskite superconductor. In very clean samples, one finds a TC of 1.5 Kelvin, and you need only a very small amount of disorder to destroy superconductivity in this material. It's an unconventional superconductor. It's important to know that in the normal state, under ambient conditions, is a Fermi liquid. And, I'm sorry for that. And basically until 2019, the most discussed pairing symmetry was P-wave. And that is actually when we started our experiment. So that's what we initially wanted to look at. When you expect a P-wave symmetry and you break the tetragonal lattice symmetry and go to the orthorhombic, you would expect that you have here this splitting, and you would obviously then see two transitions in heat capacity. In resistivity, of course, when the sample has zero resistance, you just see nothing anymore, and that's why we started the whole investigation. However, it turned out by a study of Stuart Brown's group that the P-wave symmetry is excluded. So originally, this P-wave was based on night shift in NMR measurements that were experiments from Ishida in '98, where he found that the spin susceptibility did not reduce in the superconducting state, what you expect for odd pairing. And here I show you data which Ishida repeated 25 years later on the very same crystal. And it turned out that basically there was a heating effect. So basically the NMR, the signal putting on the sample was too large, and that is why the spin susceptibility stayed constant. So what basically the new results with the smaller excitation energy showed that indeed there is a drop of in the night shift. And that basically excludes P-wave pairing. However, the MUSR results and care effect, which were also repeated, still showed that time reversal symmetry is broken in strontium rusinate. So that stays. Okay, so what was known from susceptibility and resistivity measurements, when one's applying uniaxial strain along the 100 direction in the plane, one observes large enhancement of the susceptibility, which peaks around compressive strain of minus 0.4. And that could be explained by tuning the materials through a Van Hove singularity. So basically, we just have to look at the gamma band here, and when we apply strain along the 100 direction, basically this band is elongated and basically going through this Van Hove singularity, and then we have here this band is opening. And that was actually confirmed by APES experiments, where you see here this closed band, and then at higher strains it's opening. And basically we have a strong response under uniaxial strain. One can tune the material through the Van Hove singularity. But of course the question is, what is thermodynamic properties in this material? So this could be also just a surface effect, for instance. And one is also expecting at this Van Hove singularity, of course, strongly enhanced density of states. And that should be also a signature in the heat capacity. So that was basically the setting when we started our experiment. And let me just show you what we did here. We had this uniaxial strain device, which was developed by Clifford Hicks. And we have here 3 piezo stacks. And in this design, basically, these, when you apply a positive voltage to them, these are expanding, and this one here is compressing. And in that sense, when you cool down the device, you compensate for the thermal contraction, so you don't break the sample just by cooling down. And what is also nice in this device, the sample is much shorter than the piezo stack, so you have a gearing effect and can apply much larger strain than when you would just glue the sample on the piezo stack, what was done before. And So as I said, our approach is we wanted to measure heat capacity, and obviously the sample is glued well to the rig, so you can't do just a adiabatic measurement or a relaxation measurement. So we had to set up an AC heat capacity measurement, and with that one can adjust the frequency and find the right frequency that we can carry out the experiment by adjusting basically the coupling from thermometer to heater and to the bath. And here we have three, when we change the frequency, and here plot the response of the AC amplitude. In the low frequency range, most of the heat is lost to the bath. At high frequency, only part of the sample thermalizes, which in our experiment will become crucial. And in principle, the best window is here in the middle, where the heat capacity is proportional to 1 over the oscillation amplitude. And that is how this design look like. So we have here a thermocouple glued to the sample, and that is a small heater. And basically, the heat is flowing through the sample. Here it plays also a role the orientation of the sample, but that's too detailed. And when we now just do frequency sweep, we indeed see that we come in this region where we have the plateau, which we want to have. But it's not the best to stay in the middle of the plateau, so we want to go to the high frequency edge, and that is because when we strain the sample, obviously more or less homogeneous strain we just have in the middle of the sample, and here the strain is building up. This you see, for example, at this low frequency, where we still see a signature from the unstrained sample, and here we have the strained part. We go to higher frequency, and at 1.5 kilohertz, we just see a single transition. When we go further up, we have a much worse signal-to-noise ratio. So one has to play around a bit with the frequency one is operating that. And due to this coupling, unfortunately, one gets only relative values of the heat capacity. And that is what we observe. We can really follow the transition. So we have a thermodynamic evidence that TC is maximum under uniaxial strain. It's bulk superconductivity. And even so, that's only relative data. We can say something about the jump in the heat capacity, because that's basically at the same temperature. And we see that the jump size is increasing with increasing strain, and it's getting the maximum value as the Van Hove singularity. And that's also basically excluding, to some extent, that there is a node at the direction, at the 100 direction. So, but that was data which is already a little bit older. Let me now come to a much more tricky experiment. Basically, with the same setup, we can measure the elastocaloric effect. So we just neglect the heater here. We still use the thermocouple. And in addition to this DC voltage to apply the strain, we put AC voltage oscillating amplitude on this inner stack. And in that sense, we have here this oscillating strain. And then we measure the temperature. And what the elastocaloric effect is basically analog to the magnetocaloric effect here. And so we apply delta epsilon, the oscillation of the strain, and we measure the oscillation of the temperature. And in that way, we have direct access to the strain derivative of the entropy. And that is a quite important property. And as I said, that was really done on exactly the same sample, so we can do simultaneous heat capacity and elastocaloric effect measurements. And to look at this, one can consider basically this elastocaloric effect as a virtual heater. So when you just write down the differential for the entropy, you can consider the C dt dt, the time derivative of the temperature as heating power. And that explains basically that we have the same like we had before in case of the AC heat capacity measurements. I don't want to go too much in details here to save time. And we can do the same. We have again these three regions, and we can adjust the frequency for the right measurement window. And then you see here one frequency sweep, and we then sit at 1.5 or 4.5 kilohertz to do our measurements. And as I said before, the heater is still attached, but we are not using it. And now I show you strain sweeps. So basically here at 8 Kelvin, we see that we have a zero crossing of the temperature oscillation at the Van Hove singularity. So basically that indicates that we have a maximum in the entropy. So we have because here we have a negative slope, and when we then go to lower temperatures, we see that here an additional feature is appearing. This I will discuss later on. So that is related to a magnetic phase, but we see that here the zero crossing is almost not changing, and then the last temperature above superconductivity. And when we then, I just clean the picture a bit, go below, we see that here we have a reversal of the ECE signal. So we have still the zero crossing, but the second derivative is changing. So we have, instead of a maximum in entropy, we have now minimum in entropy. So we have a quench of the entropy. And so let me just summarize here the experimental facts. So we have the entropic signal by entering in the superconducting state is well pronounced. We have a maximum entropy at the Van Hove singularity in the normal state, which is quenched and turning into a minimum below TC. And away from the Van Hove point, we have basically a reversal of the basically the signal almost reverses size. What's now important to compare this with literature, we can look at the Grünizer parameter, which is basically just delta T divided by delta epsilon times 1 over T. And from that we learn, as expected for Fermi liquid, at low strains the curves fall all on top of each other, and at the Van Hove singularity of minus 0.4% strain, it diverges, and at higher strain, the Grünizer scaling is poorly obeyed. When we now compare that with calculations by our collaborating theorists, so from Markus Gast and Jörg Schmaljan, they were setting up a tight binding model, and basically they could also, to the numbers here in the same range, could reproduce the behavior at the Van Hove singularity. But of course, I don't see this feature here at higher compressive strains. And they also find this reversal of the signal, which is found in the experiment. And what is important here, they can only explain the experimental findings assuming a full gap superconductor at the 1, 0, 0 direction. So that excludes that a node cannot be in this direction. That is, for example, excluding dx square minus y square symmetry for strontium rusinate. And yeah, as I said, it suggests a full gap superconductor. To make this a little bit more colorful, so we can do a color map, and here the white lines are where the elastocaloric effect is 0, and that is showing this line at the Van Hove singularity that has indeed some curvature, which is also reproduced by the theory, but it's not yet clear why it's not a vertical line. We also see this entering into the superconducting state. And we have here another line which I will discuss in the following. From MUSR experiments, we have here one single point, and MUSR have shown that this phase is most likely antiferromagnetically ordered, so it's clear that it's a magnetically ordered phase. And we found that this is suppressed to zero temperature, close to the strain where superconductivity disappears. I just want to show you also some temperature sweep data. And here you see one example which I want to point out. When you look at zero strain, you almost see here no signal at all. And that is basically kind of obvious because here TC doesn't show any strain dependence. So measuring of the elastocaloric effect makes only sense when you really have a strain dependence in your feature. So initially, basically, you have here no different contrast between both the superconducting and the normal phase. You can do more with this data using an iterative method. You can calculate the entropy just using the initial entropy, which is known from heat capacity, and then you run this 3, 4, 5 times, and then you end up with an entropy curve like that one here, and you see that there is a drop in entropy at this phase transition to the antiferromagnetic phase, and that we indeed find here at different temperatures. At 7.5 Kelvin we don't see that, but then we see this drop appearing and it's shifting to lower strains, and we can even quantify that. First of all, it looks more like a first order transition, even though it's quite broadened. From the decrease, we can estimate a drop of 3 millijoule per mole Kelvin squared, which is 8% of the electronic entropy of the unstrained material. And it's a similar value what is found at the 3 to 7 strontium rusinate, which is magnetic. And so it's quite comparable to that one. And this reduction of the entropy in the magnetic phase is also in line with the conventional expectations of gapping of the Fermi surface. Then we also looked back to the heat capacity data and also made this colorful plot. And sometimes these plots are really helping. And there's also features seen at this transition line to the magnetic state. So, and basically, we indeed found some similarities of strontium rusinate, which was previously not appreciated, to the cuprate, mictide, organic or heavy fermion superconductivity, superconductors where also antiferromagnetic phase is close by, whatever this means. So this work was, of course, only realized with many collaborators, where I want to especially point out Yusheng Li, which did all this experimental work and did a lot in optimizing it to really get out this data, which was really highly challenging. So the first part of the heat capacity was done as part of his PhD thesis, and then when he came back as a postdoc, he worked further on the elastocaloric effect. And last but not least, I put up the summary here. Thank you very much.
Thank you very much. Very nice talk. Okay, immediate question.
Very nice talk. 2 quick questions. First, the magnetism comes from ruthenium, I suppose. Is it correct? Because you say before it was not appreciated, the magnetic phase, but
it was not found, so it was not really seen.
Yeah,
so there is just. So
I'm asking, does it come from ruthenium atoms, or who brings the magnetic moments?
Probably, but we know that's the magnetic phase from the MUSR, so it's just a single point in a strain experiment, and that it's really to follow the phase line that we could only do with our experiment here. So that is what kind of magnetic phase it is, we don't know yet.
Okay. Now the main question, you have shown very nice curves across above and below TC, let's say. What is your, let's say, best bet? What is the normal state and the superconducting state in view of this new, because the P is excluded now. So do you have an idea? Or?
So we had just some internal retreat, and I was just making some fun with Andy McKenzie and tell you we are excluding more and more order parameters, and at the end we will conclude that it's no superconductivity anymore. So it has to be. But at the moment, different method excluding different order parameters, and I think it's really difficult at the moment to just jump on one.
Okay, thank you. Another question, please, from here.
Hi, so I understood quite well that you have an antiferromagnetic phase, you have a superconducting dome. What was not clear to me in this similarity is, do you have a pseudogap state?
I can't, where should it, so probably not, but it's not a high TC, so I would not expect a pseudo.
Well,
so,
above the dome you can have a pseudogap state even if it's low TC.
Yeah, but there's no indication for any pseudogap state.
Okay, yeah, thank you. Because, okay, the question, they can just support the question because some of these usual superconductors, they showed something looking like pseudogap, the same titanium nitrate, for example. And, well, it was not investigated in terms of pseudogap, but it was something like that, measured experimentally. So that's where the question is coming from. But anyway.
I mean, this material was quite well investigated and there was no indication for any pseudogap.
Okay. So there were some measurements above TC.
Well, I showed some measurements above TC.
What I mean that in titanium nitrate, there were some measurements, STM measurements above TC, and they've seen something like, okay, pseudogap, which was not interpreted like a pseudogap at that time.
I mean, you saw the device. This data is taken under uniaxial strain, and so far no one was adapting that in a STM.
I see.
So that is not, now I got your point, so that is not done yet.
Okay, thank you. More questions? Well, if not, let's thank the speaker again and give them the certificate. And let's thank all the speakers of the session once more time. Sorry? Just, please.
Okay, I would like to remind you that please vote for today's best presentation. Oral presentation, yes. Yes, and excluding half plenaries and plenaries.
Thank you.
And the next one is please sign for yourself for tomorrow boat tour.
Okay, thank you. So, what's your plan for dinner? When do you leave?
I leave on Thursday.
On Thursday,
Yeah, she leaves tomorrow.